Hello, everyone. Welcome to CVPR 2021's Computational Cameras and Displays workshop. Although we can't be together today, we are so happy you're joining us remotely for a day of exciting research in the area of computational imaging and photography. We have an excellent program today, 10 fantastic invited speakers from around the world that will be speaking about their work, along with spotlight talks that will quickly show you a glimpse into other work being done in the area. We will also have a virtual poster session this afternoon over Gatherly. Please see the CCD website for instructions on how to join, and we'll also go over instructions again directly before the poster session. We are so grateful to our speakers for joining us live in this virtual setting. After each speaker, we'll also have a few minutes of live QA, so please ask your questions in the live YouTube chat. And thank you once again for joining us today. Before we get started, I just want to introduce ourselves, the organizers of this year's CCD workshop. My name is Achille Kadambi. I'm an assistant professor at UCLA. I've had 3 other amazing organizers that have helped put together today's workshop. Tali Deckel, assistant professor at the Weizmann Institute of Science. Emma Alexander, a postdoctoral scholar at UC Berkeley. David Lundell, a postdoctoral scholar at Stanford University. We hope to get to know more of you throughout the day, but in the meantime, let me pass it off to Emma.
Thanks. Throughout its now 10 years as the Computational Cameras and Displays workshop, and for almost a decade before that as the ProCams workshop, CCD has aimed to bring together researchers in academia and industry working in the field of computational imaging. The workshop is a chance to hear from both senior researchers and rising stars in the community, and to present and learn about new or recently published work. Our community is broad and diverse, with relevant topics encompassing new types of displays, VR and AR systems, sensors for autonomous vehicles and robotic navigation, 3D sensing technologies for applications from mobile phones to industrial assembly lines, and applications in remote sensing, medical imaging, and more. This year is a little unique in that we're coming together virtually, but we're still really excited to be able to meet together, share our research and ideas, and move the field forward.
We have an incredible lineup of keynote talks and invited speakers today. There's a great breadth and depth of topics spanning the areas of computational cameras and displays. We're looking forward to hearing from outstanding keynotes from senior members of our community, and we'll have a young faculty keynote from Ayush Bandari and invited talks from rising stars in the community, Chi Gua, Regina Eckert, Vivek Bhumanathan, and Sheila Seidel.
We have a terrific schedule from 8:45 a.m. to 5:30 p.m. Pacific time. We highly encourage you all to participate in our Gather League poster session in a few hours, where you'll have the chance to explore freely and talk with other participants. Thank you again for joining us today, and another reminder to please place your questions in the live YouTube chat during the presentations. We hope you enjoyed the workshop. Hi, everyone. I'm Tali Deckel, and I'm thrilled to be here and open the day with our first keynote speaker, Antonio Torralba. Antonio is a professor of electrical engineering and computer science at MIT. He is also the MIT director of the MIT IBM What's on AI lab and the director of the MIT Quest for Intelligence, which is an MIT initiative to discover the foundations of intelligence. He made so many fundamental contributions to the field of computer vision, image understanding, deep learning, and received so many different awards that I cannot list them all here. His title for his talk today is Pixels at in Your Feet, and I can't wait to hear what it entails. So Antonio, the stage is all yours.
Well, thank you, Tali. I hope you can hear me well. And so let me tell you about something that I'm very excited about. And it's not the traditional line of work that I've been doing in my group for a long time, working mostly on vision. This time is something slightly different. So let's see if the slides move. Okay. So let me start just with reminding you, or if you don't know, what was James Gibson's dream of direct perception. James Gibson was a cognitive psychologist that had the theory that you don't really need to do complex inferences about what do you see in the world in order to recognize objects and understand scenes and affordances. In fact, his hypothesis was that the visual stimuli is so rich that it already contains all of the information that you need to take the decisions that you have to take. It is not necessary to have a complex internal mechanism to infer all of that information from the visual input that you have. So, just to illustrate a little bit, the idea is that if I show you two stimuli and I ask you which one is the simplest, so let me show you the first one. So here is one simple stimuli is just composed of lines, and it seems like a person in front of a table, and there is some object on the table. And then I can show you like a real image with lots of pixels and also a person in front of a table having coffee. And the one on the left might seem as a very simple stimuli. It's very reduced. It can be represented with a very low dimensional code. All the information that you need, can be clearly represented. While the stimuli on the right is a lot more complex. It contains a lot of things, and just representing that the stimuli is very challenging. And in fact, it's been the topic of research from the community for many, many years, many decades. So one could think that the stimuli on the left is the simplest one. But James Gibson's theory is that, in fact, the one on the right is the simple one. It contains so much information that it doesn't matter what you do with it. There is always enough redundant information that will tell you something about what you're looking for. While the one on the left is so impoverished that it's very difficult to do inferences about it, because small changes could change your interpretation completely. For instance, I could just move around a few lines, and completely change the meaning of this stimuli, and I just moved 2 lines. So it's just a very complex stimuli, in fact, the one that seems simple. So I think that nowadays we are in a very similar situation than the impoverished stimuli that Gibson was talking about. So when we think about robotics, for instance, here is a picture of the Atlas robot used during the DARPA challenge. And some of the worries about making a robot is what is going to be the computing power that you can put onto this machine, what is going to be the energy consumption, and of course, how do you control the robot, and how do you have all the dynamics and all these things right. And there are a number of problems. One of the important things in the robot is going to be the sensory capabilities that the robot has, and they are loaded with sensors. They have LiDAR sensors, stereo cameras, pose and velocity sensors, joint sensors. There are pressure sensors on the feet. It's just full of different sensors trying to make sense of what the external environment is. But if you compare this with the researcher that is standing on the back there, what is that the researcher is doing? What are the sensory capabilities of this researcher? Well, it has more than 6 million color photoreceptors, 100 million rods. It has 100,000 touch sensors. of different kinds that detect mechanical properties, temperature, pose, and so on. It has 10 million odor receptors, 10,000 taste cells, 2 ears. In fact, that researcher there, that's a really rich set of input sensory modalities. The robot, even when we think that it's loaded with sensors, it's really not. It really has no sensing capabilities whatsoever. Like, you can touch this robot anywhere, and the robot will not know that anyone is touching it. So we are in a very poor sensory input modality right now. And in fact, when we think about computer vision or many other aspects of AI, we are really on an age of thinking of perception as computation, where all the emphasis is about putting more and more computing power into your machine, building bigger representations, and adding more cells and more layers to your network, and that's what it is all about right now. The game, it's just thinking of how you are going to perform computation in the most efficient way and do as much computation as you can. So in fact, sensing, on the other hand, is something that is kind of left aside. So for instance, in computational photography, there have been a lot of advances on making new type of sensors that will sense not just RGB values, but also depth and so on. But the same thing is not happening with many other sensory modalities. So the picture that I'm showing here is a little bit like kind of the relative importance that sensing and computation have in our communities right now. It's all about computation. Sensing is given to you. You will use a camera that is already given to you, and you don't have to worry about it. And when new developments will happen and new type of sensory modalities you will have available, then you will use them, but all your effort is on the computation. And what I want to argue is that really we should kind of reversing this picture. Computation is very important. There is no doubt about it. But I will argue, just to argue something different, that sensing is more important. In fact, going back to James Gibson's dream of direct perception, where everything is available on your stimuli, on your input stimuli, if you have sensing that is very dense and very rich, I think that a lot of the computation can be hugely simplified. And by sensing here, I don't mean just better cameras, because cameras are very good already. I really mean something more general. I really mean about everything. Just like humans, we have many different sensory modalities, and we sense the world through many different inputs and not just pixels. And that allows us to do all kinds of things. And many of those things that we do, they could be done only with vision, but they just are harder. I think that is, if we have many different modalities that are rich, then things will become easier, maybe. And I argue that current robot systems, for instance, even though when they say that they have pressure sensors and touch capabilities and so on, it's still really, really far from our tactile capacities in the human body. In fact, if you look at the progression of, for instance, cameras through history, there is a long history since cameras started many, many years ago, many decades. And until now, the advances have been enormous. But it's also because the community has put so much effort into building cameras and making always the next generation. And in fact, the same thing happens with microphones. If you think of sensing sounds, history is also very, very long, almost as long as the history of cameras. And we have really nice recording devices nowadays. It's probably not as advanced as cameras are, but microphones are really, really very powerful. And there are microphones that are really good. However, if you think of the human brain and how it allocates computation to different sensory modalities, vision is certainly the most important one. Around 30% of the brain, in some of these estimates that people like to do, 30% of the brain is devoted to vision. However, there is another sensory modality that also has almost as much, and is touch, tactile information. Around 10% of the brain, of the cortex, is devoted to processing tactile information. And yet, if you look at the history of tactile sensors, well, I actually couldn't even find a slide like the ones that I found for cameras and microphones on the web. There is just not a history of tactile sensing. There is of course research on tactile sensing, but it's really very limited. And it's always like a niche area where very few people are working. And there are some really interesting products out there developing, selling sensors that detect pressure and other properties that are related to touch. But they are relatively low resolution and limited to specific body areas, and it's just not comparable to the quality of pixels in the eye, how well we are at building pixels in a camera. So there are a bunch of tactile sensors out there, and here is one example of a gripper, a hand with 3 fingers that has some pressure sensors. It has around 9, this has 10 pressure sensors, I believe. And so it's very low resolution. I mean, if you compare this with your hand, I mean, this is really nothing. So you could detect that you're touching something with this grip, with this hand, but you wouldn't be able to recognize what it is, for instance. And there is research on, of course, in the domain of robotics, of using vision to supply the information that you need in order to grasp an object that now is not provided by touch because there are not rich touch sensors. So RGBD cameras, for instance, are commonly used, but then you have, of course, occlusion issues, accuracy problems, and so on. There are also contact sensors. There are a number of them. There are mechanical sensors, but generally they are very limited in number. So it's just going to tell you if you're touching something or not. And then there are also optical sensors, which generally are much higher resolution, but they are limited to a very small region of the skin of the robot. One really nice touch sensor has been developed by Ted Adelson from MIT. Ted Adelson, who has been working in computer vision for many, many years, has been transformed into a tactile sensing person for the last decade. And he introduced this really cool sensor called gel side. And gel side, what it is just a surface that is covered with a gray paint, but it's flexible. So now when you touch some object, this surface will deform and it will follow the shape of the object. And then inside the sensor, there is a camera. And the camera has 3 lights, red, green, blue, so that it produces information that allows you to very easily measure the depth gradient of the image. So what you see here on the right is an image produced by the sensor inside. So it transforms the problem of detecting touch into a problem of measuring pixels. At this moment, it's become a vision problem, but it's based on a signal that you measure upon contact. So it's not the same thing that you will get from a camera. So in collaboration with a number of colleagues at MIT, part of the fabrication group with Wojtek Matusik, we have been exploring this field of trying to put pixels in your skin. And our idea was we want to develop a sensor that will allow us to measure touch signals, create images that are formed by pressure signals. But we didn't want it to go into the field of robotics. So we didn't want it to have to build a skin for a robot. And then, because then we have 2 problems. We have the problem of sensing and we have the problem of control of the robot. So these are 2 hard problems and we wanted to separate them. So we wanted to create a passive sensor that will allow us to measure touch. So what we did was to create, like in this case, is a glove that you can wear and it will record pressure signals as you handle objects with your hands. So in this case, the robot becomes the human, and this sensor is just a passive sensor, just like a camera would when you're taking pictures or doing computer vision on images captured with a camera. The camera is just a passive sensor. You're not controlling what the camera does, but still you can do a lot of things. So we wanted to be in that setting. So the first question that we had was, what is the resolution that the sensor needs to have? And many years ago, I did a study on what is the minimal amount of pixels that you need to have on a picture so that the picture is recognizable. And here on the right, what you see is a set of human experiments where I asked participants to recognize the content of an image and then evaluated the percent correct on that recognition task as a function of the image resolution. So these are very small images. So you can see the thumbnails on the right, on the bottom right. And starting with 4x4, people are just very bad at recognizing things. But as you increase resolution, things get much better. And in fact, at 32x32 pixels, people reach already 80% recognition rate when the images are shown in color. So that's a pretty high performance. So this is kind of a minimal image. Below 32x32, you really don't have enough pixels. And most of the time, the image will just appear as a set of non-defined blobs. But at 32x32, recognition seems to be quite good. And in fact, you can even segment things. Like here, what I did was a task where I asked people to segment objects in these very small thumbnails. And here is an image of 12x12. And if you ask people to segment what is here, no, people are just not capable of segmenting anything. At 16x16 pixels, well, people can make some guesses. And here is one of the participants that says, okay, maybe there is a bookshelf over there. At 24x24, things start to become a little bit clearer. So here, the person said, okay, well, there seems to be a closet and a window on the back. And then maybe here there is a bed in the middle. At 32x32, things start being a lot clearer and people just start labeling all kinds of pixels. And they say there is a man lying on the bed. There are some shoes at the feet of the bed. There is a poster there with a skyscraper. I think that at this point they are just a little bit imaginative. And this is the original image of 256. So you can see that most of the objects were right. There was no man lying on the bed. But the point here is that 32x32 seems to be a resolution that starts getting pretty close to what you need to recognize things. So we created a glove with 555 sensors, which is kind of halfway to the tiny image that is the minimal image that you need to recognize things. So this sensor now is, here I'm showing just the map of all the pixels that are placed on the hand, and we will use this to record tactile signals. So the way that we created the sensor is by using a force-sensitive film that is a layer, this black material, and on top of it, there are on the bottom there are two conductive threads that are orthogonal to each other. And this force-sensitive film, what it does is that when you press on it, so this force-sensitive material is actually a semiconductor, so it can conduct current. So if you have these conductive threads on top and the bottom, there is some connection between them through the resistance imposed by this film. And this resistance will change as a function of pressure. So when you press here, the resistance will decay and the connection will become stronger between the two orthogonal conductive threads. This is a typical strategy actually used in lots of different pressure sensors. The point here is that we are making this with the shape of a glove and trying to capture this very high sensitive, high resolution signal. So these are just different attempts that we had at the beginning of creating this force sensitive material and just different arrays of different resolutions. So this is basically how it works. You have, you have two orthogonal lines of connections and you will pass current. So let me show you the circuit in a moment. So the way it works is you look at the resistance that exists between two different lines orthogonal to each other. And that resistance, even though there are lots of connections, when you look at two individual threads, the connection is more or less the strength of the point of contact between these two lines. And that allows you to measure pressure. This material is very flexible, so you can, it will adapt very naturally to the hand, and you don't feel like you are wearing much when you are wearing this. So this is the type of signal that we will record as you are holding the object. You can see, you can see a little bit the shape of different portions of the object as you are touching it in different ways. The signals, sometimes they don't look super clean also because the hand doesn't always touch what you think is touching. Sometimes there is no full contact between your hand and an object. There are some parts of the hand that are actually not in contact with the object. Here there are some more examples. One really interesting thing about this sensor is that I find really fascinating is that this is a sensor that is changing shape all the time. When you have a camera, the camera always has the pixels in the same locations. It always captures images in the same way. This sensor is not like that. Your fingers are moving, the separation between the fingers is changing, and the image that you capture is captured by a sensor that now is dynamically interacting with the environment. And it's deforming, the sensor is deforming. So imagine that you have to capture images with a camera where the lens and the sensor, the sensor itself was changing shape constantly. Perception will be a much harder problem. On the other hand, also, there might be interesting opportunities that will open up. In fact, we have seen in computational photography many situations where being able to modify the position of the sensor and the lenses very quickly allows you to do things that you couldn't do otherwise. So this flexibility might add actually interesting opportunities for sensing. So here there are just some other examples. Another interesting thing is this sensor also, you can actually look at what are the natural image statistics of this signal. And here what we are showing is when the mouse is hovering over one sensor, is showing what are the pixels in this image that correlate highly with the sensor that is being selected. And this correlation is computed over many natural graphs. And you can see that, for instance, the fingers are correlated with each other. Even far away points might be correlated because they will get close in a space, or they are coordinated, and therefore creating all these strange and interesting correlations between pixels in this image that are really far away. So these statistics are very different from the type of statistics that you find on natural images, where the highest correlation is always between nearby pixels. So now with this type of sensors, you can do the standard things like recognizing objects. And here we have a set of 30 objects that we can recognize based on the signals that we measure from grasp. Another really interesting thing is that the touch signal itself, even when you are not holding any object, is still measuring things, because when you bend your hands, you are touching yourself, and there is still, you still feel something in your hand. And the signature that is being recorded by the touch sensor while you are moving the hand tells you information about the pose of the hand. So you can kind of infer the pose of the hand without needing to have pose-sensitive sensors. You can directly sense it from the touch signal. It's not very reliable, it's not very robust, but it's certainly there. You can do other things like estimating the weight of an object, something that you cannot just do purely from vision, at least not with few images. But this is still very limited, no? We are still only doing touch sensing on the hand. And if we really want to accomplish Gibson's dream of being able to infer a lot of things directly from our stimuli, sensory input, we need to have much better coverage. So we wanted to go to the next level and try to build like a full scheme for a robot. So in order to do that, we introduced a different technology. And what in Wojtek Matusyk's lab they did was to create functional fibers. These are fibers that you can use to make clothing, but each fiber is coated with a piezoresistive material that makes the fiber also to be pressure sensitive. So now when you have two fibers that are crossing each other perpendicularly, when there is pressure between the two, the resistance, there will be a contact created between the two fibers, and the resistance, the intensity or the strength of that connection between the two fibers will be dependent on the force that is being applied between them. So the nice thing of using fibers is that now suddenly you can start thinking about knitting all kinds of materials, all kinds of clothing and skin. And here, I mean, there are a number of difficulties because you have to put these two fibers that are orthogonal to each other. So what you need to build basically are two layers of clothing, one that will have lines in one direction and another piece of clothing that will have lines in the orthogonal direction, and then you put the two on top of each other. So this is just a picture of the two layers of clothing, one that will be the outer layer that has lines in one direction, and the other one that is the inner layer that will have lines in the orthogonal direction. And then we started making all kinds of clothing. And so Alisa has been developing these fibers and characterizing them and building all these different skins and then doing all kinds of cool things with them. So here there are, 4 examples of the types of things that you can do. You can, again, make gloves like we had before, but now with these functional fibers. But you can make, jackets and socks and all kinds of things. So in particular, well, here is an example of putting skin on a KUKA arm and recording the signals that allow you to detect contact. Right now, these robots, the only way that they have of knowing that there is contact between them and an external object is because something is changing in the dynamics. But here now you can directly measure that contact and therefore probably react faster. Here is an example of the vest. And you can see the signal that is being recorded on the back as the person is moving around. But one really cool thing was socks. And this is about putting pixels in your feet and all the kind of cool things that you can do when you have this. So these socks are not normal socks. The bottom of the socks is covered with hundreds of touch sensors. So now we can try to do cool things with them. So for instance, could we use them to estimate pose of a person? And pose is something, people have been working on pose for a long time. And there is some really interesting work actually, for instance, on of course, in computer vision and using other types of sensors. There was also some interesting work about using pressure maps on a bed for people identification, gait analysis, and pose estimation. But here we want to do something more than that. So can you use your footprints to tell your posture? So here Alisa is wearing 2 socks. And what we did was to record simultaneous data with a mock-up system and with the tactile socks at the same time, while performing different actions. And then walking around in the building and doing all kinds of things just to have a very rich signal. So here is an example of the signal that is being measured. So here you see the 2 feet, and in this case, the person is just walking. And what you see here are the images captured by the pixels at her feet. And now what we want is we want to be able to build a system that will take this as input, and it will try to predict the signals measured by the mock-up system. So can we just tell from the signal that is recorded on the feed what is the posture of this person? And the model is very simple. I will not stop here. I mean, just it's a 2-branch neural net that will take as input the 2 images. I mean, just fairly standard. And at the end, it just predicts the joint angles of the pose model. And it works fairly well. So here is the result of the estimation. So on the left, you see the tactile input. In the middle is the ground truth signal recorded by the mock-up system. And then you have the prediction made from the signal measured from the tactile signal. So here, temporal integration is very important. The temporal signature of the tactile signal tells you something about what is the history of the motion, and that's what allows you to predict the pose of the person. It works very well for the legs. Of course, as you're getting farther and farther away from the feet, it doesn't work so well. You can still detect, surprisingly, some properties of the torso, like this type of motions, but the arms don't work very well. Here is the arms are kind of working because in that type of motion, that was the pose. But here in this case, for instance, you can see that the prediction of the arms is just some prior. It's just not seeing the arms in this case. Another very interesting problem with the skin is how do you calibrate the skin? So we have all these sensors, but they're all kind of different. And these sensors are not so well done as pixels in a camera, so they need to be calibrated. So one way of calibrating the signal was we use a scale, and we put different shapes on top of the scale, and we started pressing on those shapes. And the goal now is, instead of trying to calibrate pixel by pixel, which will be a lot of work, what we want to do is we want to build a system that will self-calibrate itself from this signal. So what we want is to build a system that will take all of the sensor readings. It will go through a very shallow neural net with 3 layers, with very small receptive fields. And the output should be such that when you sum all the values of the output, it matches the value predicted by the scale. Because the neural net is very shallow, it cannot really transform the signal dramatically. But because it has to add up to the measure of the scale, the best way, the way in which at the end it will converge, is by trying to calibrate each pixel so that when you sum the pressure measured by all the pixels, you are getting the actual weight or the amount of force that is being applied by the hand. And we did extensive analysis of that. I mean, this is just the neural net. It's very simple. And then at the end, we test also if the individual pixels were correctly calibrated, and it works fairly well for this case. And the same thing can be done with the feet. You can press on a scale with your feet, and we do the same game. We try to build a very shallow neural net that will transform the pixels recorded by the feet so that the sum is equal to the weight measured by the scale. One interesting thing is that once you have calibrated the hand, you don't need to calibrate the other parts of your skin. You don't need to play necessarily the same game everywhere. In fact, we can use teacher-student architectures now to learn to calibrate the rest of the body. So in the same way that we can use vision systems to do all kinds of things, to measure all kinds of properties in the world, we can use this vision system to actually calibrate the hand system and to also infer, force the hand system with the tactile input to make the same predictions than the vision system is making. But once we have calibrated the hand, we can use the hand to calibrate the rest of the skin system to make the same predictions. And in fact, so the interesting thing here is that once you have a sensor that is really good, like vision, you can use vision to teach the hand and the hand to calibrate the rest of the skin. So here's an example of how can you calibrate the rest of the skin. So here Alisa is wearing the glove and is touching the vest that is full of sensors. And one thing is that the pressure measured by both the glove and the vest should be equal, because both, if they are in contact and there is no motion, there are no accelerations, then all the forces should sum up to 0. So you can train a neural net to make sure that the output from the vest is equal to the output from the glove. So the sum of all the values should be equal. And you can use this to correct missing pixels, to remove outliers, to calibrate every sensor, and so on. So this is kind of how it works. And you can see on the bottom, here you can see in the bottom the signals measured by different pieces of the skin, and how the glove is using to calibrate this. So Alisa will be showing actually another cool extension of this type of sensing techniques with a carpet that can be used to predict all kinds of actions and activities that a person is performing on the carpet. And the carpet actually is very powerful because as it is a static sensor in this case, it allows you to do things that are much, much harder to do with the socks or with the other parts of the skin that I have been showing. And Alisa will have a poster during CVPR, so I strongly recommend you to go if you're interested in. But here, what I wanted to conclude is that we have been working for a long time in putting pixels in cameras, and there have been a lot of advances in making cameras, in computational photography, about extracting new type of measurements and properties from images and new sensors. And I think that there is a very interesting opportunity of extending all of those ideas that we have been learning to trying to measure other things than pixels, than light. And in particular, touch is a very underutilized and understudied field. And it really needs the help from the entire community. I think that if a lot more people were working in this area, fast and advances will be made. And there are, I think it will open the door to have robots that are more versatile and flexible and robust than what we currently have. So thank you so much for your attention. And if you have any questions, I'm happy to take them. But Tali, you are muted.
I'm muted. Thank you, Antonio, for the amazing talk and inspirational talk. As always, we do have a couple of questions on the live chat. So Meg is asking, thank you for the talk. Apart from pressure, can the glove infer different textures of an object? For a poor resolution input image, the texture combined with this image could provide better.
Yes, yeah, that's an excellent question. This sensor can detect coarse properties of the texture. And for instance, if you are sliding the glove over a surface, then you can measure finer properties, because now it's like you have, even though you have small resolution, as the sensor is moving, you will capture like high resolution signal. But there are other sensors that will be probably better, like gel side. You could imagine actually a combination of gel side with this type of sensors. The sensors are good for large coverage of skin areas. Gel side is great for really fine resolution at your fingertips, for instance.
Okay, thanks. And another question, how does localized temperature impact the measurement of the sensor? Can that be a useful input? Is it possible to sense cuts and scratches on the sensor array?
Yeah, that's a great question. Yeah, there is some sensitivity to temperature. We have characterized how the resistance works and so on, but we haven't really exploited it to measure temperature, for instance. There are sensors that probably you can build that are better for sensing directly temperature. If there are cuts in the sensor, so what will happen is that you could detect that because you will see dead lines. Strange lines will appear on the image that don't follow natural image statistics. So the calibration process, actually, these dead lines appear from time to time. They are there, and the calibration process can get rid of them. But yes, you could detect this.
Okay, another question. How do you account for self-touch when calibrating the vest with the glove or vice versa?
Well, when you are calibrating, self-touch is really what is being used for calibration. So, when you're doing self-touch, you know that the sum of all the forces should be equal to 0. So you should measure whatever points of contact there are. And this is just assuming that the only things that are in contact with your skin is yourself. But the sum of all of these forces should sum up to 0.
Okay. I have another question. So I'm wondering, this opens a whole new world of possible applications. And I'm wondering if you have in mind some application that kind of like also combines pixels from camera, like light. Can this kind of like provide complementary information to what we can have, from image sensors? And I'm curious to hear if you have such applications in mind.
Yes, we do. And so we are working on some of them. And we had also a paper a year and a half ago, maybe, using vision and touch to do, for instance, cross-modal prediction, where you have images captured with a camera and you try to predict what you will feel, and then the opposite too. And that will allow you to do things like learning materials and so on. But this is still an open area of research, so we have done very little.
Okay. And in terms of like possible resolution, because it does seem that with the fiber, the resolution is kind of like limited. Does the conclusions from your pixel work translate into this domain, or you think that the major kind of like obstacle in the way was going to be like resolution?
Yeah, I think resolution is addressable. I think that the problem with resolution really is that when you are making these circuits to address different pixels, these circuits just get a little bit more complex. There is nothing special to them, like cameras, our screens can address a lot more pixels and have no problem with that, but of course there is a big industry behind that. Here there is not such a big industry and it's just more tedious. There is nothing in the fibers can actually be, we could make them denser, we could put more of them, but then addressing them it requires working harder on the circuit.
Okay, I think, we don't have further questions. Antonio, thank you so much. It was a pleasure having you here.
Thank you so much.
Thank you. And now we turn to our spotlights videos. We're gonna present some of our spotlight poster presentations next.
Hi, I'm Berthy Feng, and our project shows how you can estimate interior material properties of objects given only monocular video of their surface motion. Given the monocular view shown here of the subtle motions of a bunny, we're able to estimate its spatially varying Young's modulus and density values. Even though we only observe one side of the bunny, our method recovers material properties of sides that were unseen in the video, as well as the interior of the object. Our approach is based on the idea that vibration can be decomposed into modal motion. Modes and their resonant frequencies are related to material properties via an eigenvalue equation involving the stiffness matrix K and mass matrix M. Given a known geometry, we solve an inverse problem to recover K and M. However, this is an ill-posed problem, because in monocular video we can only observe the projected motion of part of the object and a tiny portion of its modes. We begin with an input video of an object vibrating. This physics-based simulation shows a cube moving under damped free vibration. We apply phase-based motion processing, followed by a pixel-wise FFT along the time axis, to produce a log power spectrum of motion amplitude. For each peak, we extract the corresponding image space mode. Assuming we have a good mesh model of the object, we sample the visible mesh vertices in the images. Given these sampled 2D image space modes, we solve a non-convex optimization problem to estimate a 3D volume of material properties. In this example, by utilizing the image space modes that are observable in simulated videos, we're able to identify an interior defect. In addition to synthetic experiments, we demonstrate our method on a data set of real videos of drumheads. In this example, the drumhead has a stiff region in its center, a defect that was introduced by painting gel onto the underside of the drum top. For more information, please visit our archive preprint. Thank you.
How can you acquire microscopic images in a dynamic environment such as underwater? It is possible to acquire a single plane image, but it will have a very shallow depth of field. Acquiring a focal stack will result in motion blur due to the long acquisition time. One-shot imaging, where the focal stack is scanned during a single exposure, was suggested as a way to shorten acquisition. The one-shot image has to be deblurred in post-processing, and previous methods suggested simple deblurring based on restricting assumptions that led to a limited range. We suggest using a deep neural network for deblurring and show a tenfold increase in the depth of field with a minor increase in the acquisition time. We train the DeepNet on a simulated dataset, and it results in a more flexible system with larger depths of field. We will show more exciting results in our talk.
Typically, inverse problems assume measurements y relate to unknown sources x through a fixed forward model f. In seismology, earthquakes nucleate under the surface in unknown locations. What we can measure are the arrival times from the earthquake source to a receiver on the surface. Measurements are related to the source and receiver locations through an Earth's velocity structure, which determines the forward model f. To solve for unknown source locations, f inverse, the inverse of the forward model, can be used. However, seismic inversion is ill-posed, making this challenging. Even more difficult is the fact that the Earth's velocity is unknown. Using an incorrect velocity model for inversion results in poor earthquake location estimates. Instead, we propose to solve for the Earth's velocity while simultaneously solving for the earthquake locations. We introduced DeepGEM, a new neural network approach to solving blind inverse problems. DeepGEM mimics expectation maximization optimization to solve for the unknown parameters of the forward model, in our case, the unknown Earth velocity structure. Please see our poster for more information on the structure of our network and how we use normalizing flow networks to better approximate complex distributions. Here we show results from a simulation with receivers only on the surface. We would like to identify the anomaly. Here is the true Earth velocity, the baseline reconstruction, and the DeepGEM reconstruction. Unlike the baseline, which was run by a seismologist, DeepGEM is able to reconstruct a smooth gradient as well as the anomaly. Even with a few number of sources, as shown with 9 sources, DeepGEM does a good job of recovering the true source location as well as reconstructing the velocity, where mean squared error is shown in each reconstruction. We show that our method is able to recover a variety of Earth velocity models, even when noticeable structure does not appear in the center of the region of interest. We have shown a method for solving blind seismic tomography. We believe our optimization framework is general and can be extended to other blind inverse problems that have differentiable parameterized forward models, such as blind deconvolution. Thank you.
Hi, this is Abhinam from Purdue University. I'm here to give a brief intro into our work on HDR imaging using quantum image sensors. Generally, when we are imaging a HDR scene, we use exposure bracketing, where we capture multiple low dynamic range images at different integration time, which are then fused to obtain the HDR data. Quantum image sensors have the ability to oversample the scene because of their significantly higher frame rate. This higher frame rate is possible because of the ability of QIS to work with lower bit depth in the ADC. In this work, we systematically show that when we use exposure bracketing with QIS, we can achieve dynamic range far greater than a standard CMOS image sensor, and we can achieve it in fraction of the time taken. We answer 2 major questions in this work. The first one is, can we quantify the dynamic range advantage provided by the QIS? The second one is, what reconstruction algorithm should we use for the HDR reconstruction of QIS data? We start by first deriving an analytical expression for the exposure referred as SNR edge for both single bit and multi-bit QIS. This expression takes into consideration sources of noise such as read noise and dart current, which were ignored in the past works. We verify the correctness of the derived expression by testing it out on real data. We then use this expression of SNR edge to quantify the dynamic range of QIS and CIS. We can clearly see here that QIS has extremely better dynamic range compared to the CIS. We then move on to a second question on HDR reconstruction for QIS. Our theorem 2 provides the optimal linear weights for HDR reconstruction of QIS data. Based on this, we propose an optimal recursive algorithm for HDR reconstruction. We also conduct real experiments to verify the dynamic range advantage provided by the QIS, and also the effectiveness of the proposed reconstruction algorithm. Thank you.
Hi everyone, my name is Atul. I will be talking about passive interphoton imaging. A camera pixel is like a light bucket. It collects photons for a fixed exposure time. 2 things limit the dynamic range: strong noise in dark conditions and saturation limit in bright conditions. This is a fundamental limitation if we only rely on the number of photons. Instead of measuring only the total number of photons, what if we exploit the time dimension of photon arrivals at each pixel? For a dark scene point, there will be very few photons, so the average interphoton time will be large. As the pixel brightness increases, the average interphoton time becomes smaller. So the key idea is that pixel brightness is inversely proportional to the average interphoton time. Note that this scheme has no saturation limit. But how do we measure this interphoton time in practice? We use an image sensor called Single Photon Avalanche Diode, or SPAD. SPADs have the unique ability to precisely time tag individual photons. We call our method interphoton SPAD, or IP SPAD. Let's look at an experiment result. This scene contains a dark tunnel with a bright halogen lamp outside. A conventional camera requires multiple exposures to cover this extreme dynamic range. Quite remarkably, the eyepiece pad captures this entire dynamic range of over 10 million to 1 in a single shot. You can read the dark text and see the bright halogen lamp simultaneously. Here we show the other extreme, where the eyepiece pad captures very few photons in each pixel. With some denoising, we can reconstruct images with just 1 photon per pixel. Interphoton imaging can provide extreme dynamic range beyond the capabilities of conventional image sensors.
Imaging Black Hole Dynamics by Aviad Levis, David Lee, Joel Trupp, Charles Gammy, and Katie Bauman. In 2019, the Event Horizon Telescope collaboration produced the first ever black hole image. This image was computationally constructed from measurements of synchronized telescopes collected over the course of an entire night. Key to this result is the underlying assumption that M87 is static during acquisition. In this work, we present an approach to infer dynamic properties of sources that evolve during acquisition. This is particularly important for studying the black hole in the heart of our own Milky Way galaxy, which rapidly evolves on the timescale of minutes. Images from the Event Horizon Telescope are reconstructed from interferometric measurements. A key challenge is that we are only able to measure very few spatial frequencies while the source is evolving. In this work, we present an approach that allows us to use these extremely sparse measurements to extract statistical properties of the gas surrounding a black hole. We model a video as a composition of a static image and random dynamics. Random dynamics are given as a solution to a stochastic partial differential equation. A key challenge to estimating the dynamics is that pixel values are driven by an unknown random source, which we do not want to estimate. We tackle this fundamental challenge by deriving a projection-based loss that is robust to the input random source. Please see our poster for more details. In simulations, we use synthetic EHT measurements and jointly recover the unknown static image and dynamic parameters. Finally, we show that we can handle model mismatch and that the SPDE model can capture complex dynamics of physically realistic black hole simulations. These results demonstrate promise for applying our approach to analysis of future EHT measurements.
We present ACORN, Adaptive Coordinate Networks for Neural Scene Representation. Neural implicit representations, or coordinate-based networks, have emerged as a new paradigm to represent signals. A coordinate network takes low-dimensional coordinates as inputs, such as a position in a volume, and outputs a low-dimensional signal, such as the occupancy, or the sign distance function at that point. A challenge in using these representations for large-scale volumes is the number of forward passes they require. Even for a moderately sized volume with a side length of 1,000 voxels, querying the entire volume requires a billion forward passes through a potentially large neural network, making training and inference computationally inefficient and time-consuming. ACORN can fit signals better than simpler architectures like Siren or local implicit representations, and ACORN is significantly faster to train, as shown for fitting this 16-megapixel image of Pluto. While fitting the image, ACORN simultaneously optimizes a multi-scale decomposition of the image, which allows fitting detailed regions more efficiently. ACORN fits this image to 30 dB peak signal-to-noise ratio in 60 seconds, while Siren takes over an hour of training time to achieve similar quality. ACORN relies on a hybrid architecture using an adaptive block coordinate system that is optimized online during training to reduce fitting error. A global coordinate for each block is mapped to a feature grid by a fully connected neural network. Then, to recover the signal at a point within the block, we interpolate a feature vector at the corresponding location and decode the signal with a lightweight decoder network. Using this hybrid architecture that combines an implicit representation, explicit features, and an online multi-scale decomposition, ACORN is well suited to represent large-scale signals.
Imaging photoplethysmography, IPPG, is a set of techniques for measuring the blood volume pulse from light reflected from the skin using cameras. These methods have the potential to enable low-cost measurement of important vital signs, including heart rate, blood oxygenation, and respiration rate. While these methods hold great promise for low-cost and scalable physiological monitoring, physiology video datasets are hard to collect because they usually require high-quality videos, which require large storage, access to a ground truth sensor, and privacy concerns. This makes it hard to train machine learning models in IPPG applications, and most recent work still uses non-machine learning methods. A common solution to the problem of limited data is data augmentation to synthetically create new training data by manipulating the original training images. But standard augmentations, such as flipping the images, don't affect the IPPG signal that we are interested in, and they may not be very useful for training models for physiology. Instead, we can use video magnification to create data with different IPPG signals. This highlights features relevant for IPPG, making it easier for the model to learn which regions to focus on. To clearly illustrate the advantages of training the network with our augmentations, we created a large domain gap between the training and test sets, where we trained the network on very easy stationary videos of light skin type subjects, and we test on hard videos with large motion and dark skin types. Training the network to measure heart rate from videos with our data augmentation dramatically improved cross-dataset generalizability on both large motion videos and videos of subjects with darker skin types.
Hi, we present a novel few-shot HDR degaussing method utilizing unlabeled images. Collecting large-scale HDR degaussing dataset with ground truth is challenging because each sequence has to be shot twice with and without motion. They are limited in the diversity of camera parameters. Another major difficulty is the post-capture manual examination. All samples must be carefully examined for any unwanted motion in the static exposure stack. We address the above limitations by using very few labeled images and many unlabeled images. In the first step A, we train a network N with few labeled images L and static images S, along with many unlabeled images U. We use supervised loss function for L and S and self-supervised loss function for U. In step B, we use pre-trained network N to generate HDR output for the U set. In step C, we generate static varying exposure images from the generated HDRs. Then, we introduce motion between the images by transferring the optical flow from U. The generated synthetic dynamic varying exposure images are a matching input for the generated HDRs. Finally, in step D, we retrain the network N with paired inputs L and P using supervised loss function. Quantitatively, we show that our approach trained with only 5 labeled examples outperforms fully supervised methods in 6 out of 10 metrics. Our approach, trained with only 5 labeled examples, has less artifacts than existing approaches. In summary, we present the first zero-shot and few-shot HDR degaussing method with unlabeled images. We have presented a novel method to generate labeled dynamic training data from unlabeled data. Our approach, trained with only 5 labeled dynamic samples, achieve comparable, if not better results than the state-of-the-art methods. Thank you.
Hello everyone. Today I am presenting our new work on color contrast enhanced rendering for optical see-through head-mounted displays with optimized display power. The optical combiner of OSD-HMDs blends the rendered pixels with the physical background. This essential property of combiners often causes a color blending problem, which hinders the ability of clearly observing the virtual content in mixed reality scenarios, especially when the virtual and real scenes show low color contrast. Additionally, the compactness requirement of HMD's form factor usually results in limited battery capacity, greatly affecting user experience. It is essential to incorporate the energy-saving problem while solving the color blending problem. So, we propose a novel real-time color contrast enhancement for laser beam scanning OSD HMDs, aiming to improve the distinction between the rendered image and the real background based on the opponent colors theory. To further increase the perceptual color contrast, our work utilizes one characteristic of the human visual system that the color of one region induces the complementary color in the neighboring region, that is, the simultaneous color induction. We also exploit the luminous efficiency function to theoretically minimize the power consumption of laser beam scanning type OSD HMDs, requiring no hardware changes. Similar to the previous work, we manipulate the display light in both chromaticity and luminance to enhance the color contrast. By contrast, we introduce a new constraint, named power constraint, to reduce display power as much as possible. In particular, we shift the complementary color of the surrounding background toward the direction of the green laser under power constrained, and then apply the remaining 4 constraints like the previous work. Here is an example indoor scene perceived from the HoloLens 2 by participants in a daily environment. We note that the white coffee cup looks a little bit greenish because its color is shifted toward the color of the green laser. This is the result of our 2 alternative force choice subjective experiment. The participants were asked to compare a color contrast enhanced rendering with the original one. We find an optimal configuration for both color contrast enhancement and power consumption reduction based on this experiment. Thank you for watching.
In this work, we focus on a class of computer vision applications where the goal is to capture high-speed videos of sparse scenes. By sparse scenes, we refer to applications where the scene's points of interest occupy the image plane very sparsely. In these applications, capturing the full 2D sensor for every frame is wasteful and limits the maximum achievable frame rate. In this work, we present a more efficient approach for high-speed imaging of such sparse scenes. In this approach, instead of capturing the entire image at slow rates, we only sample small portions of the full sensor image at high frame rates. To encode the position of all scene points, we place a diffraction grating in front of the lens, which spreads the incident light for every scene point such that it intersects the sample part of the sensor. Then, using a convolution-based image formation model, we decode the full resolution image based on the color and intensity of these sparse measurements. We demonstrate our approach in several application domains, including high-speed motion capture of fast-moving markers, such as darts fired from a toy gun, or an actor performing a fast rope-skipping exercise, particle image velocimetry, where the goal is to reconstruct the fluid flow by imaging these white tracer particles, and recovering a high-speed video of combustible particles like the sparks generated from this sparkler. So please visit our poster for more details and additional results.
We present Coded Stereo, an end-to-end learning-based stereo system to enable large depths of field 3D reconstruction. Traditional stereo vision suffers from a fundamental trade-off between light level, exposure time, volume of reconstruction, and noise. In the light-limited environments, a small aperture severely limits the light throughput, leading to noisy captures and resulting in low-quality 3D reconstructions. On the other hand, increasing the aperture will let more light in, but reduce the depth of field as a trade-off. To overcome this trade-off, one naive approach is to replace each of the cameras in a stereo system with an EDOF camera, and then estimate disparity maps directly from the EDOF pairs. However, this approach does not show significant improvement due to the inconsistent features in the reconstructed EDOF pairs. Here, we propose Coded Stereo, an end-to-end learning-based technique to overcome this limitation. Different from the naive approach, for both fields, the face mask, the EDOF texture reconstruction, and the stereo disparity estimation are all trained together end-to-end. The learned face mask creates a numerically invertible blur, allowing us to recover sharp image texture and stereo correspondence over a significant extended depth of field than conventional stereos. Here we show the real experiment results using our prototype. From the captured image pair, our method can reconstruct both RGB image and disparity with high accuracy in a large depth range. We further compare our method to conventional stereo system with the same aperture size. Our method outperforms conventional designs in a high-quality reconstruction with clear details and sharp edges. Please refer to our paper and website for more details.
When a lens maps a point in the world to a point on the sensor, a diffuser maps each point to a pattern. Since each point maps to many points on the sensor, we can leverage compressive sensing to recover the full scene from a subset of pixels. framework has shown that we can encode video or hyperspectral content into different subsets of pixels and then recover a full video or hyperspectral data cube without much loss in resolution. The Lensless reconstruction algorithm is an inverse problem where we solve for the scene image X, given the measurement B in the forward model A. Current model-based method use convex optimization with a handpicked prior to solve for the scene image. Deep learning-based method can achieve higher image quality but requires labeled image pairs, which are impractical to obtain for 3D lensless imaging. We propose an unsupervised deep network to utilize the capabilities of deep network without requiring any training data and can be applied to many lensless applications. With UDN, an untrained network is used as an image generator. A forward model follows, producing the corresponding simulated measurement, which is then compared with the captured measurement to update the network. Here's the progression showing that the network gets better at producing the scene image. This framework can also recover 3D data cube from a 2D measurement by replacing the 2D erasure with a 3D encoding function, showing how the 3D data is encoded onto the sensor. In simulation, compared to other model-based methods, our method produces sharper images, fewer artifacts, and better perceptual image quality. With experimental data, our method achieves better image quality in both applications. To conclude, we propose an unsupervised deep network that produces high image quality without any training data. Our approach is limited by the long reconstruction time and with the recovery resolution limited by the GPU size. Thank you for your attention.
Common structuralized systems have a camera tethered to the projector. This paper frees the camera and allowed it to move in the scene in an unconstrained manner. Our system both localizes the camera and recovers the 3D scene in a world coordinate system from a single image. We call this system FreeCam 3D, and it has many applications in augmented reality and indoor localization. There are two key ideas in this paper. First, encoding depth in the projector defocus with an optimized face mask. Second, using a pattern with unique and rich local texture for spatial localization and depth estimation. Together, these two ideas permit us to decode the 3D positioning of the scene from a snapshot. We do this by adopting a fully differentiable learning-based pipeline. Here, we recover 3D point cloud along with the camera pose. Thank you.
Hi, this is Zihui. I'm presenting our recent work, end-to-end sequential sampling and reconstruction for MR imaging. A central challenge in MRI is the slow acquisition process, which leads to high cost, patient discomfort, and significant reconstruction artifacts. The accelerated MRI mitigates this challenge by only measuring part of the case space to reduce acquisition time and recovering high-quality images with a reconstructor. Recently, there has been an increasing research interest in using deep learning methods to optimize the subsampling pattern. In our work, we propose a framework that provides adaptive sampling patterns for individual patients. To do this, we first sample a few measurements to get a rough reconstruction. Then our learned sampler will sequentially estimate the next best measurements to take based on the intermediate information from the previous step. We also jointly optimize the deep sampler and reconstructor through end-to-end training. Here, we show the full acquisition process and final reconstruction of our 4-step model with left and right rotated knee images as inputs. The pink areas are the selected measurements. We can see from the pointed column that our model is aware of the input rotation and can sample measurements accordingly. Note that our model is not trained with rotated images, but still learns to adapt to rotations. Our reconstructions are often more accurate with more detailed local structures than other baselines. For example, the white areas pointed by these arrows are wiped out by other methods, but accurately reconstructed by ours. Thank you for watching. Please check out our website for our code and more details.
Hi, everyone. I'm very excited to introduce our second keynote speaker, Noah Snavely. Noah is a professor in the computer science department at Cornell Tech. He's also running a research group at Google Research in New York City. Noah's groundbreaking and inspirational work in computer graphics and computer visions generally aims at reconstructing, synthesizing, and understanding our world through massive, unstructured photo collections. You recently received the Helmholtz Prize for Building Rome in a Day, which we all know, and many other awards, such as the SIGGRAPH Significant Award and the NSF Career Award, and many more. Today he's going to talk about on reflection, and please, Noah, take it off.
Thank you, Tali. This is so cool. So it's so good to be here. It's great to see you all virtually. Hope you all are having a good day and a good CVPR so far. So as you can see on the screen, there's a small warm-up activity. So please get something to draw on, like a piece of paper or a tablet PC, and imagine in your mind's eye a clothes hanger, like what you use to hang clothes on, like a shirt or whatever, and then draw what you see in your head. And you can, I'm gonna just change to the next slide, but I guess all of you in virtual YouTube land, this is your warm-up activity. Okay, so so I'm gonna talk about a talk I'm calling On Reflection. It'll be clear why in a minute, but I'll say this is this is a somewhat philosophical talk, but I promise you will relate to computational cameras by the end. Let's get started. So, one more just bit of housekeeping. I'll use Slido. This will be an interactive talk. So I think despite you being wherever you are watching this talk, please go to slido.com and enter the code NOAH. And that will get you into Slido, and this will come in handy later when I ask you some questions. Okay. So yeah, imagine you're Alice from Alice in Wonderland, and you come across a looking glass, a mirror, that you can pass through, that takes you into the mirror universe, right? So this is what happened in Through the Looking Glass from Lewis Carroll. What would you see in this mirror universe? Well, there's a room you can see through the glass, through the mirror, that's just the same as our drawing room, only things go the other way, right? So like everything is reflected, everything's reversed. And so imagine, well, maybe if you're Alice and you wake up one day and you're not sure, you don't remember if you're in the real world or the mirror world, how would you be able to tell them apart? Okay, so this kind of idea of mirror universes or reflections has been a recurring theme throughout literature, especially in science fiction. This is a topic in a lot of stories. One of the favorites is this story from Arthur C. Clarke from 1950 called Technical Error, where the synopsis is, the first power plant to exploit superconductivity has been built, and worker Richard Nelson is laterally inverted following an accidental short circuit in the facility. So meaning he's like reflected left, right. His whole body is mirrored. Nelson finds himself wearing his wedding ring on the wrong hand. Written texts appeared mirror inverted, and coins in his technical diary have been affected. Nelson begins to starve because normal food does not nourish him, since most biological molecules are chiral. Chiral meaning they have a handedness, and they only work correctly with one of the handednesses and not the other one. Okay, so authors have been fascinated with this. I'm very intrigued by this idea of mirror universes and how it connects to vision and computation. So let's try this for real. So imagine you're Alice and you are trying to tell if you're in the real universe or the mirror universe. Okay, so here's a test for you. Take a look at this image. This is either a real image or a mirrored image, meaning I've either showing you an actual image or a left-right reflected image. So see if you can tell the difference. So this is where you should go to slido.com and enter code NOAH. This is a live quiz. And I'll give you 20 seconds to lock in your answers. Hopefully people are able to do this, or else I'll see that 0 people have entered an answer. But we'll see how well this experiment of interactive Slido works. Okay. Oh, so Actually, no one entered an answer. So hopefully, if you have a technical difficulty with Slido, please let me know. But so
Noah, I think you can join me now. Let me introduce you all over again. So again, I'm very excited to have Noah here. Noah is a professor in the computer science department at Cornell Tech. He's also running a research group at Google Research in New York. Noah's groundbreaking and inspirational work in computer graphics, computer visions, aimed at reconstructing, synthesizing, and understanding our world through massive unstructured photo collections. He recently received the Helmholtz Prize for Building Rome in a Day, which we all know, and many other awards such as the SIGGRAPH Significant Award and the NSF Career Award for all his fundamental contribution to the field. Today he's going to talk about on reflection. So Noah, please take it off.
Thank you, Tali. This is so cool. I'm going to start assuming no one saw anything because we got doing another redo. So I'm going to say, please draw a clothes hanger. Draw what you see in your head when you think of a clothes hanger. And yeah, please, this is new technology. It's good to have this opportunity to talk again. Okay, so I'm going to talk about on reflection. It'll be clear why it's called that in a moment. But this is a bit of a philosophical talk. I promise you it will relate back to computational an interactive talk. So the interactive does not work so well, but so I want you all to go to slido.com and enter code Noah, enter the quiz. At a certain point, you'll be asked some questions that you'll answer on slido.com.
No, I think you can join me now. Let me.
Cool. Okay. I think there was a small technical problem there. So I'm just going to continue where I started. So like I was saying, imagine you're Alice going through the looking glass, and what would you see on the other side? Or imagine that you wake up one day as Alice and you're not sure if you're in the real universe or the mirror universe. How could you tell the difference? So this has been the premise of a lot of, well, especially science fiction stories, this kind of fascination with mirrors and with reflections. One of my favorite examples is a story from Arthur C. Clarke called Technical Error, whose synopsis is as follows. The first power plant to exploit superconductivity has been built, and worker Richard Nelson is laterally inverted following an accidental short circuit in the facility. Nelson finds himself wearing his wedding ring on the wrong hand. Written texts appear mirror inverted, and coins in his technical diary have been affected. Nelson begins to starve. Normal food does not nourish him because most biological molecules are chiral. So his body's been flipped, like mirror inverted, And because chiral meaning asymmetric, like the flip version is not the same as the non-flip version. So amino acids, for instance, don't work the right way if you mirror invert them. Okay, so now let's try this result. So imagine you're Alice. You're wondering if you're in the real universe or the mirror universe. So here's an image. I want you to either this image is a real image, or it's an image that I've mirror inverted, flipped left and right. And I want you to try and tell which it is. Okay, and so we'll go over to Slido. Oh, okay. So good. I see some names here. So you'll have 20 seconds to try and answer this quiz. Is this image flipped or not? This is so cool. Hopefully the lag isn't so long that you can't actually participate, but we'll see. All right. Okay, 60% said yes, 40% said no. The answer is actually no. It was a trick question. So how would you be able to tell? So actually I cheated. I blocked off some of the obvious cues. There's some text in the background here that I masked off. So text is the most clear cue, right? Text has a left and almost in any language has a handedness, doesn't look right when flipped. But there's also other cues like buttons. Turns out men's suits, at least in I think Europe and the US, button a specific way. Collars are the same. Maybe there's a cue in how he's holding this newspaper, etc. So this in general is a difficult problem, but the mirror universe does differ from the real one in ways that are both obvious, like text, and subtle, like how buttons go, okay? So, and there's something very fascinating about mirror flipping. And flipping an image vertically doesn't have that same effect, right? You flip an image vertically, it's very clear that like gravity is going the wrong way. But if you flip an image horizontally, it's like you're almost in the same visual universe, but not quite. Some things are just a little bit off. Okay, so I'm fascinated by this kind of concept, but why should we care in general? Well, symmetry assumptions are pervasive in computer vision. And so it's good to examine those assumptions and how realistic they are. And I'll talk about that in a second. But even though there's some symmetry assumptions we rely on in computer vision, the universe is inherently asymmetric, even down to camera hardware, as I'll talk about in a few minutes. So there's actually a lot of beautiful examples of symmetry being used in interesting ways in computer vision. So one of my favorites is this. When I saw this for the first time, I was blown away. This is an example from the view morphing paper from Steve Seitz and Chuck Dyer in SIGGRAPH 1996. And if you think about the Mona Lisa, because the Mona Lisa is, the person is largely symmetric, you can create a second view of the Mona Lisa by taking a mirror flip, right? So now it's like you have a new image from a different camera viewpoint. And so you can do things like animate all the views in between and generate a frontal view of the Mona Lisa, right? And that's just magical. I really love this. Okay, so yeah, the idea here is, this assumption is that if you have an image of a symmetric object, you really have two images. And that's powered some recent work too, including the best paper award from last year's CVPR. This unsupervised learning of probably symmetric deformable objects from Shangzhe Wu et al. And so you can, because you get a second image for free, you can do things like use that image to supervise learning of 3D shape and illumination from single images. This is just marvelous and magic. And so the idea is you get something for free from symmetry, like an extra image. By the way, we also use this kind of thing with Shangzhe in a work that appears at this CVPR on extending this to radially symmetric objects. So objects that are surfaces of revolution, we take single images of objects like vases, and using the stronger radial assumption symmetry, learn to infer from a single image shape and material properties and lighting. So you can generate new viewpoints and relight them. Okay, so these symmetry assumptions are very powerful. And maybe the most important way symmetry is used is in data augmentation. So left-right flipping is a very common data augmentation operation in things like learning object recognition. So you take your ImageNet images and flip them to get twice as much data. This even goes back to the older work on deformable parts models, where if you look at Ross Gershik's old code by this point, they do left-right flipping as a data augmentation approach. So if this is your data set, you can instantly get twice as many images to learn from by flipping them, by left-right flipping them. And that seems very powerful. But is that really for free? The assumption here is that flipping an image, somehow you're still in the same visual universe, or you're still close enough to the visual universe that you can use it as a valid image. But is that really true? So here's an image. If I flip it, clearly it's no longer really a valid image because the text is going backwards. Except that, okay, this is an image actually taken in a, slightly dirty mirror. So this is actually a true image and not a flipped image, which, the mirrors exist in the world, which somehow makes this problem even more deliciously interesting to me. But clearly the universe is not, despite the existence of mirrors, the universe is not quite flip invariant. And there's lots of examples of this. So I've been collecting lots of examples of ways in which the universe, the visual universe is asymmetric. And I'll show you some of my favorites. Okay, so one of the first that got me really interested in this topic is, comes from this episode of Radiolab called Mirror, a science podcast. And they showed this, they brought up this example of this photograph of Abraham Lincoln. But first, let me just start with another Slido question. So one of these so here's two images of Lincoln A and Lincoln B. One of them is real Lincoln, and one of them is mirror flipped Lincoln. So can you tell which is which? Which one is the real Lincoln? Okay, so let's go to Slido again. Get ready. I'll give you 20 seconds. Hopefully this will work despite the lag, to lock in your answer of which is the real Lincoln. Okay, this is so cool. Okay, so 33% said A, 67, 2/3 said B, and the B's are correct. This B is the correct image. So despite the fact that both of these are somehow Lincoln, if you believe the world is visually, somehow flip invariant, to me, B clearly stands out as a image of what Abe Lincoln looks like. And image A looks very strange to me. It looks like, a sinister Lincoln or something. I'm not sure even how to describe it. But there's something off about that image. And that was what they pointed out in this episode of Radiolab. And they had all sorts of theories that I don't buy, like, the hair part looks better if you part it a specific way. What I think is going on here, and psychologists in the audience might know better, is that I'm just very used to seeing this image of Lincoln, this famous portrait of Lincoln. And Lincoln's face is asymmetric. He actually suffered from something called strabismus, which made one of his eyes kind of float independently of the other one. His nose is not quite straight. He has, asymmetric lips. He has this bump on his face. And maybe I've just internalized those asymmetries to where I cancel them out in my own head. But if I look at a flip version, maybe those asymmetries are exaggerated. I don't know. But I definitely have had this feeling with my own face. I grew up before cell phones were everywhere. I was very used to seeing my own face in a mirror, which is a mirror flip version of what my face really looks like, to where when I saw my face in a photograph, I would think it looked off. It didn't look quite right to me. And I think in the era of Zoom, if you ever see yourself not Zoom mirrored, your own feed of your Zoom image, it looks strange and uncanny. Okay, so I think both of these are, but you could say, okay, somehow this Lincoln is more likely than this Lincoln. Like somehow one of these two Lincolns is just more likely to appear in the world, and therefore somehow there's something inherently more settling about that version. Okay, but by the way, I experience a very strong qualitative difference between these two images, but I'm wondering if other people, so another Slido quiz. Do you notice a qualitative difference between these two images, or do they look the same? Do they give you the same feeling? Okay, I'll let a few votes come in. This is so cool. Okay, I'm really glad this Slido is working at least partly. It's a lot more fun to have some interaction this way. Okay, so yeah, most people do notice a qualitative difference. I think it depends on whether you're familiar with this portrait or not, though. I don't think there's really an inherent there's like a natural difference between these two images. I think it probably depends on whether you're very familiar with this portrait or not. By the way, there's some great work on the vein of computational cameras. Some of you may have seen this on what would taking portraits and rendering as if they've been taken with a modern camera. So like this portrait of Lincoln was a very, very old-fashioned technology. And so this time travel photography from Swan Luo et al. From UW devises a technique that can generate a modern version of the same photograph. And somehow, actually, I don't have such a strong feeling of difference between these two images, this output from their method. And it might be that maybe when you project it onto the space of faces, somehow the asymmetries get reduced. I don't know, but I don't have quite a strong sense of difference here. Okay, one more quiz. So because that example is maybe too easy, people know that portrait. Here's a person you may not be familiar with. So one more Slido question. Which one is I've flipped one of these two images. So which one is the real image, A or B? Which one is the real person? This is a kind of true test to see if there's some kind of natural asymmetry of the world that cues you into this. Okay, I'll give you 20 seconds to answer this quiz. Can you tell the difference? Can you tell which one is the real and which one is the flipped person? This is so cool. I'm very curious to see what happens here. Okay, so 100% say B. 100% of 3 answers, so not very statistically significant, but actually you're right. So not every time I've asked this question do people get it right, but I'm actually maybe there is something that cues you in, because B is indeed the correct answer. It's probably just too few samples though to get a real good statistically significant answer to this quiz. But good job, you three, for getting the right answer. Okay. Yeah, B is correct. And maybe it depends on the order in which I show the images. You know, I'm not sure this is a really valid scientific experiment, but very intriguing. Okay, so here's some other examples of asymmetry in the world. So this one is actually pointed out by Antonio Turalba and Alyosha Efros in their Unbiased Look at Dataset Bias paper. So it turns out if you do a Google search for mugs, the handle appears almost always on the right side of the image. Not always, like there's an exception. But so there seems to be this bias in the world of images of mugs. And this was also noted in work on canonical views. Like if you ask somebody to sketch a mug, the handle almost always appears on the right. And I think if you're a right-handed person, this is how you would naturally see a mug in the world, because then you could grasp the handle with your right hand. And they also might put the graphic on the mug so that I'm not sure if you're supposed to see it or the person you're with is supposed to see it, but the handedness of the person affects, you know, which side of the mug the graphic should be on. So this is a very intriguing asymmetry. And this goes back to the question I asked at the beginning. So if you saw at the beginning, I asked you to draw a clothes hanger. And I'm very curious to see how many people drew a hanger like this versus how many people drew a hanger like this, a left-hanging hook versus a right-facing hook. Okay, so here's one more Slido question. And hopefully this works where people actually did it and survived to this point in the talk where they can answer the question. But okay, so good, we're getting some votes in. My theory is that most people who are right-handed will draw the first image, A, the left-facing hook. Because if you're hanging up a shirt and you're putting in the closet with your right hand, I think you would see it with the left-facing hook, right? So I only thought about this when I was hanging up clothes the other day, but I think a right-handed person would tend to draw it. Okay, and this is valid. I don't know. I didn't ask people about handedness, but it seems like most people are answering how I thought they would answer. So that's very interesting. And indeed, if you do a Google image search for clothes hangers, most of the time, but not always, you see a left-handed, at least for product images, you see a left-facing hook, even though a right-facing hook is just it's equally valid. Okay. Okay, here's one more just intriguing finding about asymmetry in the world. This comes from a paper from Jennifer Sun and Pietro Perona. it turns out that when interpreting ambiguous images, they find that people have there's a well-known preference for interpreting light sources coming from above. So if you look at an image like this, where either some of these are inward facing and some are outward facing, bumps, or the reverse, and either the light is coming from the top or the bottom. And most people interpret this as light coming from the top. Just from an ecological standpoint, that makes more sense from what you're used to, even though the light from coming from the bottom is equally valid interpretation. And it's not just, this paper found that people don't just have the top, but also shift its light to the left. And they find that this preference is reflected in art spanning 2 millennia. So there's a small preference for images lit from the left. And that might be, that's a very unintuitive reason, but I'll just note that that image of Lincoln that I showed earlier has that property too of being lit from the left. And I'm actually very interested if this is a property of not just paintings, but photographs. Okay, so we've explored this idea of images in we've written, so this idea of geometry.
It's super choppy.
It's super choppy.
Yeah.
Should I turn off my video?
We can try.
Okay, I'll try turning off my video, see if that. This is so cool. I know that this is like, I don't know, the world we live in. Let me know if I should pause or keep going, Tali.
Okay, keep going.
Okay, this is so cool. Okay, I turned off my video, so hopefully that will help things. So geometric chirality. An object is geometrically chiral. The canonical example is a hand. A right hand is chiral because if you flip it, a chiral object is one that if you flip, you can no longer align it with itself. So this idea was coined by Kelvin in the 19th century. I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. So if you flip a right hand, if you mirror flip a right hand, it becomes a left hand, and you can't rigidly transform a left hand back into a right hand. Okay, so that's chiral. And so other examples of chiral objects include corkscrews, golf clubs, and it turns out molecules. Molecules have a chirality. Certain molecules that if you get a molecule that's complicated enough, it will have chiral. So a famous example of this is the molecule that makes spearmint spell like spearmint. If you left-right flip it, becomes the molecule that makes caraway smell like caraway. So your nose is smart enough to tell the difference between the right-handed and left-handed version of these two molecules. Okay. So that's geometric chirality. We, in our paper, talk about a different notion of visual chirality, which has to do with distributions of images. So consider the natural occurrence of different images in the world. Okay, consider the natural occurrence of right hands and left hands. Well, if you just made if you were to come up with a probability distribution of all images, well, left hands and right hands are pretty much equally likely in the world, right? They're kind of equally probable to appear in images. So, okay, if you imagine, okay, here's a plot of a distribution. If you imagine, left hands and right hands being 2 points in this two points in the space of images, their probability shown on the y-axis might very well be equal. So somehow the visual distribution of these two chiral objects is the same, despite that they're geometrically chiral. But maybe if you think about a thumbs up right hand and a thumbs up left hand, maybe the distribution of these in the visual world is not equal because maybe more people are right-handed, so they'll be more likely to give a right-handed thumbs up. So here's two flip may not images visually chiral. The flip version is not as likely as the non-flip version. Okay, and we can define this as, suppose we can assign a probability P of X to any image X. The probability distribution P is visually chiral if P of X is not equal to P of T of X, where T is the horizontal mirroring operation. A distribution of visual data, a natural distribution of images is symmetric with respect to flipping. And the hypothesis is that the world is not visually chiral. Another example of this is Abe Lincoln's face is asymmetric. But are you just as likely to meet mirror Lincoln, or do faces tend to be asymmetric in similar ways? Okay? Do faces exhibit visual chirality? So we explore these kind of questions in our work. Okay, and we can explore this very simply by taking a bunch of images, flipping half of them, and training a classifier to tell whether the image has been flipped or not. If the world is visually achiral, not chiral, you shouldn't be able to tell the difference. You shouldn't be able to train a classifier to tell flipped versus not flipped. If the world is better than chance probability. So we gather, P.
Huh?
If there's some kind of boundary effect, get rid of that.
No, you
Okay,
were
then,
lost.
yeah.
You were lost in the past 10 seconds. Sorry about that.
We trained a class boundary.
Huh? This is so cool. I think my connection is a little bit flaky today. Sorry about that. So I'm just going to quickly go through this talk. Thank you so much for bearing with me here. Yeah, so we wanted deep learning networks are surprisingly good at telling whether images are flipped or not. We devised a method to figure out what they were learning. It turns out
they can learn things like shirt collars. Shirt collars, men's shirt collars and women's shirt collars exhibit chirality. Shirt pockets appear, on preferentially on one side. Watches, most people wear a watch on their left hand. Guitars are chiral in the way that they're held, even though guitar may be roughly symmetric, their way they're held is not. Cell phones, actually people taking images in mirrors with cell phones, thus, the Apple logo or the placement of the camera, even though these images are flipped optically by the mirror, they exhibit chirality. And faces. So it seems like faces actually are chiral, and somehow there's some cues in faces that seem to reveal chirality. So we trained this chirality test on FAHQ, data set of faces. It achieved surprisingly high accuracy. And even if you take that trained model and apply it to a different data set than was trained, like labeled face in the wild, you still achieve better than chance performance. And if you visualize what the network learned, it seems like what it learned is hair part. It does seem like there's a preference for parting your hair on one side. Beards also seem to be chiral, like maybe the way that they're groomed. If you're left-handed or right-handed, or if you're right-handed, maybe reveal some chirality. I know also hair is more likely, if you look at hair whirl, which is how your hair spins. This is my son, Charlie, when you could see very distinct hair whirl when he was younger. It's more likely for your hair to spin clockwise than counterclockwise. So maybe that exhibits itself somehow in photos. Eye gaze seems like a chirality cue. Either people who have strabismus, like Lincoln, preferentially have it in one eye versus the other, but there's also other things that could be manifesting chirality in images of faces, like asymmetric of placement of the lens, asymmetric preference of head pose in photos, maybe ocular dominance. You have a handedness, you also have an eyedness. It's like the eye you keep open if you're firing a bow and arrow. Maybe more people are right eye dominant, and maybe that somehow reveals itself in photos. I don't know the answers, but I'm very intrigued to know more about this. And finally, low-level cues. Okay, so now we're actually to computational cameras. We looked into, when we first trained these networks, it seemed to be discovering low-level cues, which went away when we did random cropping. And so we thought about, are cameras themselves chiral? And actually, I talked to Bill Freeman one day when I was thinking about this, and he revealed the answer, which is yes. And the reason that they're chiral has to do with, well, among other things, the Bayer filter that's inside, that's in front of your camera that lets you capture color images. So this is like the GRBG pattern of filters on top of your sensor. And if you look at it, it's chiral. If you flip it, instead of a green pixel being on the upper left, a red pixel will be on the upper left. And that is a subtle thing, but actually, so here's a Bayer filter and a flipped Bayer filter. They're not symmetric. And so I'm just going to skip ahead. It turns out that if you combine that with JPEG encoding, it turns out that bakes some chiral cues, very low-level chiral cues into any image. So every image at a very low level has baked into it whether it's handedness. And if you flip the image, you can tell from looking at these low-level cues that it's been flipped. So the upshot is every JPEG image in the universe captured with a Bayer image filter has very small chiral traces embedded in it. So even if the distribution of natural images were perfectly symmetric, we could still use such signals to tell if an image has been flipped. Okay, so that's that work. Why is this useful? Well, I think this is a way to think harder about how we augment data. Rather than just willy-nilly flipping images left and right, we could come up with better data augmentation schemes. You could use this for self-supervised visual representations. This task of, this kind of a proxy task of certainly we discover things like watches by just using the data itself. But maybe the fact that there is visual chirality can be used to develop better camera hardware that's adapted to this natural imbalance of visual distribution of images. Also image forensics. If you can tell whether an image has been flipped, that's another tool in your tool belt. Visual discovery, also detecting mirrors in images is a niche problem that has actually been studied some. So it's also just fun. I really like thinking about these kinds of problems and exploring them. So more generally, I think this is an instance of work that's been going on in the vision community that I think could be more prominent on using image collections to discover visual subtle visual correlations. This goes back to work like what makes Paris look like Paris, or work from Shiri Guinnessar on analyzing how faces and imagery in yearbooks evolve over time. The work from Timnit Gebru on using Street View to analyze the visual world. We've used this to discover fashion trends in imagery. So I really like this theme of discovering cool things about the world through lots of data, and hope more people will get excited about this kind of trend. So thank you very much. Thank you for bearing with me. And if we have time for questions, I can take them. If not, it was a pleasure talking to you. Thank you.
Thank you so much for the great talk, and I'm really sorry about all the technical problems that we faced, but thank you for, bearing with us as well, because we are way out of time and you have to leave. I think we can skip the Q&A part, and I just want to thank you again for.
Sounds good. Thanks, everybody. Thank you so much, Tali, Nema.
Thank you. Bye-bye.
So hi everyone. Today I want to tell you about our recent work on how to render spectral statistics and on how to use them for better imaging. So if you shine a laser on a scattering volume, like a piece of soap or a slice of tissue, it gets scattered multiple times, and we get constructive and destructive interference, which leads to noise-like speckle patterns. And it may look like noise, but actually it has strong statistical properties. And for example, the speckles shift when we tilt the illumination. This property is called the memory effect. And simply put, it means that light coming from nearby directions is scattered to produce highly correlated but shifted random speckle patterns. Now, this is a very interesting property, which has numerous applications in imaging. And a lot of the research that I was doing in the last years has to do with ways to simulate, model, and utilize speckle statistics. And I want to tell you about speckle statistics today. So speckles and their statistics are encountered in imaging settings ranging from biology to security, medicine, remote sensing, and astronomy. However, the development of these applications is hindered by the fact that speckle properties are not fully understood. And with a good way to simulate speckles, we can advance this research and design better imaging systems. So one important application of speckle statistic or speckle correlation is the imaging through scattering work of Katz and colleagues. So the goal is to recover a clean image of fluorescent sources that are hidden from the camera by scattering layers such as tissue. And the speckle memory effect makes it possible to remove the effect of scattering simply by computing the autocorrelation of the speckle image. And a model for speckle statistics can help us investigate under what conditions this image for scattering procedure will work, and also understand how to improve it. Another application of speckle statistics is an adaptive optics focusing. The goal is to change the shape of a wavefront so that when it propagates through a scattering layer, it will focus at a sharp spot, as if the scattering layer was not there. So finding the wavefront needed to achieve focusing is a difficult calibration procedure, which normally needs to be performed separately for each focus point inside the volume. And the speckle memory effect makes it possible to adjust an already calibrated wavefront so that it will refocus at different points within some smaller neighborhood. So a good speckle simulator can help us investigate how large this refocusing range is, and also what wavefront adjustment can increase its size and improve it. So, and then yet another important application has to do with material acquisition, meaning that we want to capture an unknown material in the lab and recover intrinsic characteristics of it, For example, we may want to extract nutrition facts of a food, vegetables, or detect tumors inside the body, and so on. And if we know to model speckles, we can capture the unknown material in the lab under multiple illumination and viewing conditions. And then we'll try to seek material parameters which will best explain the captured statistics. So with these speckle imaging applications in mind, I want to tell you today about two recent projects from a group. The first one deals with a new physically accurate way to simulate speckles, and it takes as input viewing geometry and material parameters, and allows us to generate speckles under different illumination conditions with consistent memory effect correlation. And we can compute how this correlation will decay as a function of different material parameters, for example, the function of the thickness of the material, the density of the scattering particles, their type, the anisotropy of the phase function, and so on. And it's physically accurate in the sense that it provides the exact same statistics as we would have got from an exact solution to the wave equation. So the second project is about using some things that we learned from the simulator to design better imaging system and see inside scattering tissue. And I will start with the simulator. So let's see how speckles are usually simulated in optics. So we consider a material like a piece of soap or tissue, and we zoom in, and if we zoom in a lot, we will see that it consists of a collection of scattering particles embedded in some surrounding material. So for simplicity, we'll do everything in flatland. So as a scattering medium is 2D and the sensor is 1D, and so are the speckles. So if we know the exact position of the scattering particles, and we also know where is the illumination and where is the sensor, then the straightforward way to simulate speckles is to just numerically solve the wave equation. But the field is a complex number, and with a camera, we only measure its intensity. Now, to collect statistics, we need to look at different parts of the soap where we have different particles and therefore different speckles. So these exact wave solvers are very accurate, but the problem is that they're also very slow, and in practice, they're tractable only for tiny volumes. And another issue is that this approach requires that we know that we specify the exact position of the scattering particles, and in most cases, we do not have access to this kind of microscopic information, and also often we do not care. And we prefer to describe materials in terms of their statistical properties, such as the density of the scattering particles, the type of the particles, and so on. So to compute speckle statistics using the wave solver, we can consider the following experiment. We have two illumination sources, and we can use a macroscopic material density to sample multiple sets of scatter locations. And for each sample particle position, we use a wave equation solver to compute two scattered fields for the two different illumination directions. So for example, if we look more closely at these two fields, we can see that the field from the blue and green direction are highly correlated but shifted versions of each other. And this is essentially the memory effect. So we compute the outer product of the two fields, which means that we average this outer product over all particle configurations, and this gives us the field covariance. So the ij entry of this matrix corresponds to the average of the blue field at sensor position I times the green field at another sensor position j. So essentially, we have an entry in the matrix for the expected product of each pair of entries in the blue and green fields. Now, notice that the covariance matrix has a strong diagonal, which is shifted from the main diagonal. And this offset is basically the memory effect, because the blue and green fields are most similar when they're appropriately shifted. So we can compute the speckle covariance with this approach, but solving the wave equation is very costly. And we also need to do it multiple times in order to collect statistics, to average. So our goal in this work is to compute such covariance matrices more efficiently, way more efficiently. So in contrast to classical wave optics, in computer graphics, we use Monte Carlo methods to simulate scattering. And Monte Carlo methods are based on tracing paths of rays inside the volume. And Monte Carlo algorithms are very fast and efficient, way more efficient than solving the wave equation. And another important aspect is that they only take as input some statistical description of the material, what is known as bulk parameters, rather than an exact particle position as we need to provide to the wave solver. However, classical Monte Carlo methods do not consider wave phenomena, and as a result, they only produce smooth intensity images of scattered light, which show no speckles. And in a sense, we can think of this smooth image as some low-resolution version of a high-resolution speckle image. So in this work, we've extended the efficient Monte Carlo methodology to accurately simulate coherent speckle effects. So since I have many things to show you today, I won't get into the details of this Monte Carlo simulator, but I want to show you some results and some things that we can do with it. So I'll start by showing you covariance matrices computed with our algorithm, and to convince you that it's physically accurate, I compare it to covariance matrices from the exact wave solver. So this is a setup. The scattering media is illuminated by a pair of lighting directions, and it's measured over a range of viewing directions. So in the first case, the two illuminators are both at angle 0, and now I will tilt the second illumination to 4 degrees and here to 20 degrees. So you can see how our covariance matrices are similar to those computed by the exact wave solver. And also notice that when the difference between the illumination direction increases, the dominant diagonal shifts. And this is essentially the memory effect. I mean, when the tilt between the illumination direction is larger, the shift is larger. The shift of the field is larger. Now, finally, I want to say that to compute the covariance matrix using the wave solver, we burn the cluster for a week, while with our algorithm, we can do it in just a few minutes. So the take-home message from this slide is that the speckle statistics that we compute with our Monte Carlo algorithm are physically accurate, and they are identical to the statistics that we compute with the very inefficient but exact wave solver. Now that we know how to render speckle covariance, we can also render speckle images with the same statistics. And for example, here we render speckle fields for two different materials. The first row is a material with an isotopic phase function, meaning that the probability to scatter in any direction is identical. And the second row is a material with a forward scattering phase function. And notice how the speckle shift when we tilt the illumination angle. And now it's well known in the speckle literature that the memory effect holds only for relatively small angles, and also that the exact extent of the memory effect can be very different for different materials. And with our simulation, we can see that. So for example, for the isotopic scattering case, in the third column, we can see that the pattern already changed a bit. But with the forward scattering case, the pattern is preserved even at this larger angle. So having speckle images, we can also compute how the correlation between speckle images under different illumination decays. And it tells us the decay of the memory effect correlation as a function of the tilt angle. Now, understanding the decay of the memory effect as a function of angle is a very important problem for many imaging applications. And since there is no good way to simulate it, people are really going to the lab to capture it. And now, there is one approach that researchers are using to provide analytical expression to the decay of the memory effect. And this is using diffusion approximation. But diffusion models are accurate only for in the diffusive regime when the number of scattering events is very high. And in practice, people have observed in lab experiments that the extent of the memory effect is often much wider than the prediction of diffusion theory, but the actual values can only be measured in the lab. Now, using our algorithm, we can efficiently compute the decay of memory effect correlation as a function of tilt angle for all types of scattering parameters. So for example, here we plot the correlation for different phase functions. So we start with isotropic phase function and we continue to a very forward scattering one. Now with the isotropic phase function, the curve matches the theoretical curve from diffusion theory. And this is just another validation that our approach is accurate. Now for the layer thickness used in this simulation, when the phase function is more forward scattering, the diffusion theory is invalid and the extent of the memory effect is much wider. Now, of course, even for a forward scattering phase function, you can match diffusion theory. You just need to make the material even thicker than what we considered in this experiment. Now, in the paper, we've evaluated memory effect as a function of many other material and geometry parameters. So our spectral rendering code is available online, and you are very welcome to try it and bug us with questions. Now, the original paper was already published in 2019, but since the original paper, we've extended the capabilities of this simulator in many ways. So first, in the original paper, we considered the illumination and imaging in the far field, meaning that we had a directional plane wave, and also we view it with a very far sensor. Now, we've extended this to simulate near-field sources, which are essentially located inside the material rather than far behind it. And also, we can image with a camera focused inside the material and not just with a far lensless sensor. These conditions are required in many practical imaging applications. For example, in tissue imaging, when we want to detect fluorescent sources inside the tissue and not far behind it. Another interesting case is correlation between speckle patterns generated when the same scattering slab is illuminated by different wavelengths. So here's an experimental measurement of what is called chromato-axial speckle correlation, which was recently captured by Zhu et al. And here's our attempt to reproduce this experiment with our simulator. Now, the material parameters here are only approximately known, not exactly, but yet our simulator can qualitatively match the empirical observations. Now, in another line of research, we attempt to bypass the simulator and derive an analytic approximation to the memory effect. So in a Monte Carlo simulator, we sample a large space of paths through the material, and these paths have various lengths. However, we show that in many practical cases, we can approximate the correlation by considering only single scattering paths, paths that scattered at a single point. And we show that surprisingly, even for thick materials where many light paths scatter much more than once, then still the correlation can be predicted and explained by these single scattering paths. And the advantage is that the contribution from single scattering paths can be computed in closed form, bypassing the need for Monte Carlo integration, so it's even faster. And we have a poster on this work today, and you're welcome to check it and learn more. Okay, so now I finished the first part of the talk about the physically accurate simulator, and I want to move to the second part and show you an application of some things that we learned from the simulator to develop a better imaging system, in this case, to see inside scattering materials. Okay, so we are interested in imaging algorithms that can see through scattering layers, which means that we want to create a clear image of an incoherent illumination pattern that is hidden from the camera by a scattering layer, such as tissue. Okay, so due to scattering in the tissue, the captured image looks like noise, and in practice it carries little similarity with the hidden illuminators. Yet a previous approach showed that remarkably, due to the memory effect, we can recover the illuminator's layout simply by looking at the speckle autocorrelation. Okay, so this is a very exciting algorithm, which has drawn a lot of attention. It really offers the potential to recover latent sources behind the scattering media when they are completely invisible to our naked eye. But yet, applying it in practice involves some problems. So the first problem is that the width of the objects that we can recover is very limited because the algorithm assumes that there is memory effect correlation between any two source points on the object, and in practice, the range and the extent of the memory effect is very small. A second problem, as it was not well studied in the past, is that the density of the illuminators that our algorithm can recover is very limited because the sources are incoherent with each other, and when more sources are accumulated, the contrast of the speckle pattern decays. Finally, most previous experimental realizations of this idea place the latent object in the far field, meaning that it's a few centimeters behind the scattering layer. And this is very different than what is usually required in a real biomedical imaging application, where we want to detect fluorescent illumination sources which are located inside the object rather than far behind it. And we refer to this as near-field sources. And in this work, we attempt to overcome these three challenges. So to this end, we first use our speckle simulator and some theoretical analysis to study the memory effect. And we show that in the near field, the memory effect is useful only for samples of modest optical thickness, and it's not useful for very thick scattering layers. Now, it's still interesting because even for modest thickness, there is significant scattering, and it's way beyond what you can see with a standard microscope. But it's important to understand this limit because then we can focus our research attention in this regime of modest scattering where there is a potential to make progress. And also, I'm just about to show that for the regime of modest scattering, there are additional properties of the speckles, of the scattering that we can exploit. So we note the tissue is usually very forward scattering, which means that when light scatters, most of the energy continues in directions which are still close to the original direction. And when the thickness of the scattering layer is modest and the number of scattering events is not so high, the light did not yet scramble completely, and it's still close to the original direction. This means that the speckle pattern is not spread over the entire sensor, but the speckle pattern has local support. Now, it's very different than the image considered by previous far-field approach, where the speckle pattern was very wide and spread over the entire sensor. Now, this local support property is very important, and it's going to be our key for the enhancement of seeing through scattering algorithms. So before I introduce our algorithm, I just want to briefly review the method of Katz et al. For imaging for scattering using the memory effect. So consider a point source behind the scattering medium. So a camera from the other side of the sample will see a bunch of speckles. Now, nearby illumination sources also generate speckle images. And the memory effect property implies that when the displacement between the sources is small enough, the speckle images are shifted versions of each other. Now, if the scene contains three incoherent sources, the camera measures the incoherent summation of their individual speckle intensities. This means that the image I is a correlation of a clean object O with a speckle from a single source that we denote as S. The image I is just a noise-like speckle, and we consider its autocorrelation. Now, S is approximately independent noise, and therefore its autocorrelation is approximately an impulse, making the autocorrelation of I approximately equivalent to the autocorrelation of the hidden object O. And therefore, we can recover O from the autocorrelation of I by using phase retrieval algorithms. Now, I will be referring to this procedure as a full-frame algorithm in the rest of this talk. Okay, so this algorithm was originally developed for applications where speckle images cover the entire sensor. But we argue that if the speckle images have local support, as they do under tissue imaging settings, then we can use this property to significantly improve over the full frame autocorrelation algorithm. So to see this, let's revisit how speckle correlation is usually computed. So we have a speckle image like that, and we attempt to detect which sources are present. So we consider different shifts of the image, and we compute the correlation between the original and shifted copy, which basically involves it basically means that we multiply them and sum. But now here is a key difference. Previous algorithm summed over the entire image. But if we know that the speckle spread is local, we also know that the correlation emerges only from this local region. On the other hand, the pixels in this blob are only noise, which will not contribute to the correlation. So if we sum only inside this green window, we can reject the other noise. Now, this may seem to you like a very simple change, but in practice, we prove that it results in an order of magnitude improvement in the signal-to-noise ratio of the correlations that we can detect, and it has a huge impact on the results that we can achieve. So to show the difference between local and global correlations, let's consider this example. So we can compute the full frame autocorrelation, and unsurprisingly, it's noisy. And in contrast, I show you here the local autocorrelation in 3 windows. So it's less noisy. And also, you can also gain some information about the desired shape. And you can see that the local orientation of the arc in each region matches the orientation of the arc. Okay, so let me move to some results. So we built 2 imaging setups corresponding to far-field and to near-field imaging configurations. And we use them to capture speckle images of illuminator patterns occluded by chicken breast tissue layers. So I'll start with results from the far-field setup, and I'll show that even in the far-field setting, if we image layers of modest thickness, then the speckle patterns still have local support, and we can take advantage of it. So when using a dense illuminator patterns, the original full-frame algorithm completely fails, whereas our local support algorithm successfully recovers the pattern. Now, we checked what is the densest pattern that the full-frame approach could recover. And for this example, it is 16 times sparser. 16 times sparser than what we could do with our local approach. So to understand why handling denser latent images is harder, we can zoom in on a small window from the input image. So when there are fewer illuminators, the speckle pattern has higher variance or better contrast. And this makes the autocorrelation less noisy, so the phase retrieval task is more stable, it's easier. And in our approach, we can handle denser patterns because the local correlations that we compute are less noisy than the full frame correlation, and we have better signal-to-noise ratio. Now, alternatively, the original full frame algorithm succeeds if we greatly restrict the spatial extent of the illuminators to this small region. Now, the reason that our algorithm can recover patterns with wider memory effect, the reason that our algorithm can recover patterns which are wider than the memory effect range is that it only relies on local correlation between nearby illuminators. It's unlike the full frame algorithm. Unlike the full frame algorithm, our algorithm does not require that the correlation exists between any pairs of sources. And in particular, it does not assume correlation between 2 sources at the 2 far ends of the pattern. It only relies on local correlation between nearby sources. Okay, so these results demonstrate that our algorithm provides an order of magnitude improvement in both the size and the density of the recoverable patterns. Now, here is another example from a near-field experimental setup. And again, also in the near field, our algorithm can produce significantly better reconstruction, and it works for a much denser pattern compared to the full frame algorithm. So I'm getting to the end of this talk, and let me summarize it. So in the first part, we've discussed our Spectral simulator, which is physically accurate, and it provides statistics which are equivalent to those obtained by the exact wave solver. But our simulator is order of magnitude more efficient, and it scales to much larger things. Now, this simulator allows us to understand better understand many properties of the spectral statistics and use them to develop better imaging system. And in particular, in the second part of this talk, we use some things that we learned from the simulator to develop a better algorithm for seeing inside scattering tissue. So our algorithm can detect denser and wider illumination patterns. And most importantly, we can detect near sources and not only far ones. And we've demonstrated the new algorithm with multiple lab results. Okay, so thank you for your attention, and please refer to our paper for more details.
All right, thanks, Anat, for that great talk. My name is David Lindell, and I'll be moderating the second session for the CCD workshop today. And I didn't get a chance to introduce Anat before the talk, so let me just do that now with a brief introduction. She's an associate professor in the Department of Electrical Engineering at the Technion. She did her PhD at the Hebrew University of Jerusalem as a postdoc at MIT, as well as assistant associate professor at the Weizmann Institute before she joined Technion. And she's also received numerous awards, including the Blavatnik Award, M. Bruno Memorial Award from the Rothschild Foundation, as well as the Pammy Young Researcher Award, among many others. So we're really delighted to hear from Anat, and we'll go ahead and jump into the Q&A session now. So thanks for joining us live for this, Anat. So I think I had, if there are any questions, go ahead and put them in the chat. I just have, maybe I can start off with a couple questions of my own. So I've seen some work recently on acousto-optical speckle correlation imaging, which seems really interesting. I was wondering if these simulators, how difficult or challenging is it to simulate speckle under these conditions when you have light passing through an ultrasonic focus, for example, that's frequency shifted. Is that something that's easy to do, or is that
not hard? It's the only challenge about ultrasound that you also have the time domain, like it's or sensitive to the path length. So it's something that at the moment our simulator does not model, like just a time domain. It's not super hard to extend it, just like time we have to get to it. But I think it can very easily be extended. And yes, I agree, there are many interesting applications in the ultrasound domain.
Yeah, absolutely. And so if you have, for example, like a pulsed laser that's has a broader spectrum than you would with a continuous source, does this, what implications does that have on the simulation? Do you now need to simulate these separate wavelengths and integrate over that, or are there challenges beyond that?
Okay, so there are a few ways to simulate it. So one way is just like to think of it as a time pulse, and then you need to estimate like path length sensitivity to keep track of your paths and send paths into different beams. The other way to simulate it is we already have a version which simulated in different wavelengths. So just like simulate the spectrum of your sensor and then average. My guess is time binning will be more efficient in practice. I mean, all of these are doable.
Yeah, and the code is available online, so this is easy to download and play with, it sounds like.
Please do that, and please bug us with questions. We are really looking to see that people are using it.
And maybe I'll just ask one last question about, so it seems like this work also assumes that the scattering medium is homogeneous. Is that right? Or what about extending it to inhomogeneous?
Yeah, so the version that I showed assumes that the scattering media is homogeneous, but we already have an inhomogeneous, heterogeneous version of it. So maybe the version is, the code that I linked is very limited, but there are various extensions that Chen has, and if you're interested, send us an email, and we have many extensions which are not online.
Okay, great. So it sounds like you're far ahead, and anyone who's interested in this or any of these different versions of the simulator can go ahead and contact you.
Yes, please bug us, and we have many variants of the simulator which are not online.
Okay, fantastic. Well, thanks so much for joining us and for your talk, and we'll be back in just a moment with the next talk. Thanks again. Welcome back, everyone. Our next speaker is Chi Gua, and I'm excited to introduce Chi. He's a PhD student at Harvard University, advised by Todd Ziegler, and his research involves combining optics and computer vision algorithms to create computational sensors. Chi received his bachelor's degree in automation from Tsinghua University. He's interned at Facebook, NVIDIA, and Baidu, and has also received a number of awards, including the Best Student Paper Award at ECCV in 2016, and the Best Demo Award at ICCP in 2018. We're excited to have Chi join us and look forward to his talk. Take it away, Chi.
Thank you so much, David, for the introduction. Hi, everyone. I'm Chi. Today, I'm trying to promote a rapidly maturing technology for optical manipulation, the metasurfaces. I know some of you have already started using this technology already in your research. I thank my wonderful collaborators. In particular, I'd like to acknowledge Dr. Zhujun Shi, who has contributed significantly to this talk. I will first give a brief intro to the metasurfaces, what their advantages and disadvantages are compared to traditional refractive and diffractive optics. Then I will show you some potential applications of metasurfaces with an example of my past research. We have been making lenses for quite a long time, from the Nimmer lens 3,000 years ago to the medieval glasses and to modern optics for microscopy and photography. These engineered optics have been more accurate and compact. Inspired by the semiconductor industry, where scientists and engineers build nanostructure that manipulate electrons, people use similar fabrication techniques to build nanostructure on a surface plane to manipulate photons. These surfaces with nanostructures are usually called metasurfaces. The shape of the nanostructures on a metasurface determines how photons are manipulated when they travel through. By designing an array of such nanostructures, the electromagnetic field that passes through the matter surface can be modulated to the desired wavefront. We can design the matter surface to be a focusing lens or meta lens by designing the nanostructure array so that the phase delay added to the wavefront is quadratic. There are several advantages of using matter surfaces in your setup. First, it can achieve similar or even better imaging performance with much smaller size than the traditional optics in the design wavelengths. For example, the matter surface in this image on the left has the same numerical aperture and similar diffraction limited spot as the commercial objective lens on the right at 532 nanometers. Second, matter surfaces can provide versatile wavefront control. By designing specific shapes of the nanostructures, we can achieve tailorable modulation on the phase, intensity, polarization, dispersion, and incident angles of the incoming wave. Third, matter surfaces provide incomparable multifunctionality. For example, we can design matter surfaces that do spatial multiplexing of different modulation function, or design different modulation functions for different polarization or wavelength or incident angles on the same piece of device. A similar device to the matter surface that people often use is the diffractive optical element. Here is a comparison of these two different types of devices. One apparent difference is that the structure of the matter surface is generally smaller than the DOEs. Fabricating custom designed DOEs are very convenient these days. People can build DOEs simply by 3D printing or laser writing if higher fabrication precision is required. Fabricating the matter surface requires similar procedures as fabricating the semiconductors, which involves clean room operations like electron beams lithography, ALD, and etching. There's already a startup called Lens that tries to commercialize the matter surface technology. In fact, they just launched their first product in June. Besides the fabrication, matter surface and the DOEs have some differences in the light modulation capability. As shown in this table, matter surfaces can modulate more than phase and amplitude of the light. So, if you plan to use matter surfaces in your prototype, several things that you need to consider are whether you and your collaborators are accessible to the clean room facilities, the cost of the clean room, the lead time, and whether your application will benefit from these advantages of matter surfaces. Now let's talk about applications of matter surfaces. I have mentioned this startup that commercializes matter surface fabrication. Their first product launched this year is a very small and simple dot pattern projector called Orion. It consists of a laser emitter and a piece of matter surface that modulates the illumination into dot patterns. This product can potentially be used on phones for Face ID kind of applications. What is more, I personally believe that matter surface can be widely used for visual sensing. An artificial platform usually consists of two parts. The first part includes some optics to transform light signal from the environment to the digital signal. And the second part has digital computation to recover desired scene information. A lot of computational photography people like myself are trying to migrate a large portion of computation to the optics acquisition, so that the optics act like an autoencoder. The photon transducer no longer receives an image anymore, but a feature map. The digital computation starts from this feature map to recover scene information. I call this process of perceiving scene information via the synergy of optics and computational visual sensing. These computational visual sensors have been widely used in modern applications ranging from gaming to autonomous vehicles to reduce their size and computational cost. and they have the possibility to be used on future applications which have strict constraints on space and power. And it is very difficult for current methods to be deployed on them, such as micro robots, wearable devices, medical imaging devices, and so on. As meta surfaces has the advantages to be compact, versatile in wavefront modulation, and multifunctional, I believe they are very suitable to be used as the optics part in computational visual sensors. Several groups in this community have already pioneered their research in incorporating meta surfaces. And today I will present a past work from our group, which is an example of using meta surface to build a compact single-shot depth sensor. The work is based on a depth sensing algorithm called depth front differential defocus developed by our group. By using this algorithm, we can estimate a per pixel depth and a confidence estimation of a given scene from two shared perspective, differently defocused images without active illumination and with very cheap computation. Here, the depth is masked according to the confidence, so that only pixels with confidence higher than a threshold are shown. In our previous setups, the two images are captured sequentially, so the object is assumed to be static during the capture. We'd like to design a new optic that captures the two images in a single shot. The idea is to design a meta surface that simultaneously form two off-axis focal spots with different focal lengths for a single point source. This can be done by separately designing two meta surfaces, each acting as an off-axis focusing lens, and interleaving the nanostructures of the two together. For each of the off-axis focusing meta surface, it will add a quadratic phase delay to the incoming wavefront. So to design an array of nanopillars on a meta surface that generates a specific wavefront, there are usually three steps. First, we invent a library of sub-wavelength nanocells. Each of the nanocell has certain shapes of nanopillars. For example, in this project, we use cuboid nanopillars. Our library consists of cuboid nanopillars with different width, W. And then we use the electromagnetic field solver, such as the FDTD, to simulate the EM field of each nanocell given different incoming waves. Third, based on the simulation, we can draw the mapping between the phase delay and the width of the nanopillars so that we can pick nanocells from the library and arrange them to generate the specific phase delay via the inverse mapping. In this design process, we assume there to be no interactions between wavefront at different nanocells. Here are the SEM images of the designed meta surface. Using this meta surface, differently defocused images can be simultaneously created on the photosensor. To avoid overlap between the two images, we add a field stop in front of the lens. In fact, this field stop can be avoided if we design a polarization selective meta surface so that the two images will be of different polarization, and we can use a polarization sensor to separate them. Interestingly, this design is inspired by the eyes of jumping spiders. They use layered retina to capture two differently defocused images, while we use a meta surface to do the same thing. This is the first single-shot meta surface depth sensor. The optics only include a 3mm diameter meta surface and the photosensor, which can be made very compact. Here is a quantitative analysis. The x-axis is the true depth, and the y-axis is a predicted depth. The width of the color band is the mean error. Different color represents different confidence threshold. With confidence higher than 0.5, which corresponds to 50% density in this case, the working range is from 30 to 40 centimeters with less than 5% relative error. Here are some results. The first image is the scene And the third are the defocused image pairs. The fourth is a sparse depth map masked by the confidence. All the depth maps are masked using the same confidence threshold. And this is a textured plane that is slanted. To mimic the jumping spider, we use the sensor to predict depths of fruit flies. And here's a video of real-time depth generation. It can run at 100 frames per second. These are dead fruit flies, and these are living ones. This is a depth map of a water stream ejected from the needle to the sensor. The sensor is viewing from the front. The water stream goes up and down, so the left part is farther and the right part is closer. And here is a video of it. The water stream is moving very fast. So the capability to estimate on a fast-moving scene like this is only possible for a snapshot depth sensor. Here is a depth map of the candle flame. The 3 candles are placed at different distances. Here is a video of it. Because the sensor is monocular, it can use any intensity change as depth cue. Imagine if you want to do time of flight or structural light on these non-solid objects, it just won't work. So to conclude, it is the world's first single-shot metasurface depth sensor. It consists of very compact optics that can be assembled in a very small form factor. It requires no control power for optics. The disadvantage is that the current prototype only works for a small working bandwidth of light. Looking forward, I believe there are numerous exciting research projects that involves metasurface and computational visual sensing. First, I have shown an example of using metasurfaces for depth estimation. There are so many other scene information that can potentially be recovered using metasurfaces, such as polarization, spectrum, phase, and so on. And following the recent trend of end-to-end optimization, metasurface can be also designed by joint optimization of optical parameters, M, and the computational parameters, phi. The joint optimization requires a parametric and potentially differentiable model of the metasurface. This requires a differentiable model F that solves the Maxwell's equation given the environment pi and the metasurface shape M to simulate the signal captured on the photon transducer I. So one research question here is, what would be a good model F? People have used numerical solvers of Maxwell's equations such as FDTD or RCWA. These physical methods are accurate, but are usually slow in computation. Recently, people have also developed computational representations of implicit functions. For example, the siren that can be used to solve wave equations. I'd love to know if it is possible to go a step further, that we can have a non-iterative feed-forward computational model F that is differentiable and cheap to compute. Please do let me know if there is already one. There are 2 reasons to develop a fast approximate model F. The first is due to the increasing complexities to represent the metasurface shape M. In the early years, people have tried simple shapes of nanopillars, for example, the cuboid nanopillars. In this case, the space of nanostructures can be characterized by a single parameter. With more complicated nanostructures, the number of shape parameters increase. Recently, people started to design these free-form nanostructures and even stacking multiple layers, and the shape space becomes much, much larger. When the shape space is large, it is more unlikely to find the nanostructure that generates the desired modulation to the wavefront, but it is more difficult to pre-compute the modulation of each possible nanopillars, as we did for the depth sensing project. Therefore, a fast differentiable model F is much needed so that the modulation can be estimated on the fly. The second reason is that people have been trying to solve the EM field of larger areas of the meta surfaces instead of dividing them into cells and assuming no interactions among cells. As I said previously, in the past, people divide meta surfaces into sub-wavelengths nanocells and only solving Maxwell's equations for each nanocells individually. Now, it's possible to make the nanocells as large as tens and hundreds of wavelengths. If we can further reduce the computational cost of solving Maxwell's equations, we might be able to directly solve the EM field of the whole piece of meta surface that is millimeter or centimeters large. Being able to model larger and larger meta surfaces can significantly increase the design space and potentially build meta surfaces that are more powerful and for sensing and imaging. There are many interesting and fundamental problems to be solved for using meta surfaces in visual sensing. I'd like to invite you to join this emerging research trend, and I will be happy to take any questions.
Thanks, Chief, for this great talk. I agree. I think these meta surfaces are really interesting and promising technology, especially for computational imaging. We have a couple questions from the chat, so maybe we can go there. The first question is from Regina Eckert, and who asks, what is the maximum size of the meta surface, and how does that relate to the field of view or resolution constraints?
That's a great question. So currently, when I collaborate with the meta surface fabrication group here, the maximum size we do is 3 millimeter in diameter. But I believe now, like it is, like people can definitely make larger and larger meta surfaces. But I'm not sure about the specific number regarding to it.
And does that, normally you think of how the aperture size relates to the diffraction limited spot size or the resolution. Is that the same with meta surfaces, or is there a trade-off there as well?
I think it's the same here.
Okay. The next question is from Barmak Heshmat. He says, great talk. Does this only work with coherent light? Are there crosstalks between different images? Referring probably to the two depth map, the two differential defocus images you capture.
Yeah.
And is there a translational shift between the two depths? So are they offset somehow?
Okay. So for the first part of the question, so we assumed it's like the scene is like incoherent light source. So we only assume coherent interference from the wave that comes from each single point, and we do not assume like there are coherent interference between different point sources in the scene, so that the two images formed here, like I don't think there are a lot of I wouldn't say like there is no crosstalk, but there is no significant crosstalk that will affect the results. And in fact, we put like an aperture here to limit the field of view so that each of the image will not like overlap with each other. And could you repeat the second part of the question again?
The other part is for these two images you capture, I guess they're each of them integrating light across the whole aperture. So they're not shifted at all or offset? Are they directly aligned as well? I think that's what Barmak is asking.
Okay, yeah, so the two images are using the exact same part of the aperture. So they are all using the whole part of the aperture, because how we do it is by spatially interleaving different nanocells together, so that the two camera modulation function is like interleaved together, so that you can think of the two images to be like exactly the same. We actually don't do any kind of further alignment between them when we process them to get that.
Got it. Okay, well, thanks again for the great talk, Chi. And we'll be back with the next speaker in just a moment. Okay, welcome back, everyone. We have our next speaker, Ayush Bandari, who will be the concluding speaker of this session. Ayush is an assistant professor at the Imperial College London in the Department of Electrical and Electronic Engineering. He received his PhD from MIT in 2018, and for his doctoral work, he was awarded the Best PhD Dissertation Award from the IEEE Signal Processing Society. He's won numerous other awards, including the President's Medal for Outstanding Early Career Research at Imperial, and Best Paper Awards at ICCP and ICAST. And we're really thrilled to have you join us today, and looking forward to your talk, Ayush. Take it away.
Thank you. Thank you to the organizers for this wonderful event. So my talk is going to be one man's noise is another man's signal. And the starting point of this talk is really this idea that we are taught at our undergraduate classes that that typically noise is considered to be an undesirable entity that deteriorates a signal of interest, and we are always designing algorithms to recover signals from noise. However, as we shall see in this talk, when the noise is structured or even signal dependent, then there are unique advantages that can be leveraged. And this takes us back to the sort of well-known idiom that one man's noise is another man's signal. And hopefully with two concrete examples, I would be able to demonstrate this, this fact to be quite true. So if you look at our conventional pipeline, we have a two-step procedure. From the hardware, we capture data, and from using the algorithms, we churn out the information of interest. Now, to be able to leverage information from noise, this approach is not going to work because typically what is happening is that any information loss at the hardware level would not let you leverage optimal information from the algorithms, because algorithms always assume that you are capturing data within certain limits of the algorithm's functionality. So, of course, to be able to go beyond this, we need to rethink how we are capturing information such as signals and images. And to this end, this is really the right time to think in this new light of philosophy of computational sensing and imaging. So the reason is that if you look at this photo, on the left-hand side, you see the space control mission of NASA, which was responsible for the Apollo 11 mission. And on the right-hand side, you see a modern smartphone. And what is interesting is that the computational resources in both cases are equivalent. And this is something fascinating. However, when we are designing algorithms, this kind of leverage is very hard to incorporate, or has for most part been ignored. And let me give you a concrete example: image super resolution. So most of my work has been in signal processing. Many of my colleagues have looked at the image super resolution algorithms for 2 decades now. But if you go to a manufacturer like Nikon, Canon, or Leica, they would just resort to hardware. So they would make a 50 megapixel sensor rather than relying on algorithms for image super resolution. So this concretely tells you that we are not leveraging the computational resources at hand. So now, as the hardware is being pushed to its limits, only recently, in the last 10 years or so, people have started to exploit this kind of a co-design. And the idea is that by leveraging a co-design, you can go beyond conventional sensors designs, and you can leverage how you capture information in an optimal way, and then you use advanced algorithms for recovery. So what this typically allows you to do is it allows you to go beyond sensing barriers. For example, you can have high data rates, or you can increase the dynamic range, or you can increase the resolution, or you can even perform low-cost imaging. So 2 examples that I would like to cite here is based on my collaboration at MIT with the colleagues in Professor Rusker's group. So one of them is time-resolved imaging, and I will revisit this example later in the talk today. And then there's also the example of low-cost bioimaging, where you can use cheap sensors but more sophisticated math to actually recover the same equivalent information. So when we think about leveraging the structure of noise, the 2 kind of concrete ideas that I will be presenting today are based on dynamic range that would lead to high dynamic range imaging. And then we have spatiotemporal barriers, which is how do we sample images in space and time. So the first part of the talk is truly about high dynamic range computational imaging from quantization noise. And this is the work with my lab members at Imperial College and also my collaborator and friend Felix Kramer, who's at Technical University of Munich. So high dynamic range imaging is a very classic consumer photography application. Now this has been built into our cell phones, and most of us know how this works. So if you point a camera towards a very high intensity object, you will either have fading or dark, a washed out image, or a completely dark image, because the sensors will, the pixels will saturate at some point. Now, this has started to become a very interesting problem in the context of autonomous vehicles. So when a car comes out of a tunnel, suddenly, because there's a surge of light, the sensors saturate. And yet again, there are very interesting solutions to this problem, but they're hardware-only solutions in the sense that manufacturers develop high dynamic range imaging sensors, which increases the cost of imaging. But then you have so on one hand, you have this hardware sort of approach, but then you also have a computational photography approach, where we have this very classic paper from Dubovik and Malik, where they show that multi-exposure photography. So what you have on the left-hand side is images at different exposures, and when they are interpolated in the exposure domain sort of, you can tone map and recover high dynamic range images, right? So this kind of problem also shows up in other applications such as computed tomography and so on, and these are very recent developments in the context of technologies. For most part, this has not been the case this way. So going back to the fundamentals, if we consider the digital sampling pipeline, then we can refer to this classic book in signal Nyquist-Shannon density or sampling formula for band-limited functions. The same applies for modulo samples, namely that for a pi band-limited signal, which is typically sampled at one sample per second, with this new oversampling factor, you can in fact reconstruct the whole signal. And what is amazing here is that the result is independent of the modulo threshold. So you can, in theory, capture as high dynamic range signal as you like, and you can reconstruct it. So, of course, this is not just a theoretical work. We have also tried to develop an ADC. So what you see here is a screenshot where as the yellow signal clips over here, you can see that the pink signal is continuously wrapping. So the high dynamic range information is intact at all possible times. Now, the computational sensing or imaging problem here would be how can we recover the high dynamic range signal from the pink data that is being folded and wrapped. So Of course, in the hardware literature, people have looked into this problem. One of the first architectures was proposed somewhere in 2003 by Ree and Ju. They proposed a hardware for wrapping images. Recently, Sasagawa and Yagamuchi, their team has developed a number of high dynamic range sampling approaches based on this folded ADC architecture you can see here. And the same from the group of Ramesh Raskar, for instance, the work of Heng Zhao and colleagues have also looked into this problem. What has been truly missing is mathematical recovery guarantees and a proper framework for recovery algorithms. So, to overcome these barriers, we started looking at this problem from scratch, and that led to the main idea that is going to be presented next. So I showed to you that there is a Nyquist-Shannon criteria for band-limited functions, but we know that images are not band-limited. They are much more densely captured or appropriately captured in wavelet or spline basis. So if you have wavelet and spline models for imaging, then the question is that if we start with an image, G, which can be written in some spline space, and then we observe point-wise quantization noise, or let's say the modulo samples, then the question is that can we have an analogous Nyquist principle that we can guarantee high dynamic range reconstruction? And this problem is a very interesting problem because this would, if answered, it would be truly one of a kind solution for single shot high dynamic range imaging. Because typically, as you have seen, that we are capturing multiple images to recover high dynamic range images. So the main intuition behind this kind of an idea is that whenever you have smoothness of any kind, then it turns out that oversampled finite differences tend to be correlated, highly correlated. And what that manifests in terms of a simple mathematical argument is that finite differences have this property that they're going to shrink the amplitude. And this is what you see over here. So in short, without going into the details of the result, it turns out that Andrei Kolmogorov, who has contributed to a number of different mathematical themes, including probability theory, has also a very wonderful result in approximation theory, where he has shown that intermediate derivatives can be in fact bounded for a smooth function. And the optimal constant Cn here, which is very relevant for our cause, is based on something which is known as the perfect Euler spline. So just handpicking the main result that we need is that this constant C over here is very well known, and we are going to just pick it up from the theory of Kolmogorov. So the main idea is that if an image, let's say G, lives in some kind of a spline space which has n times smooth, then it turns out that you can choose a sampling rate which is proportional to the maximum value of which is inversely proportional to the maximum dynamic range of the image. So BG is the maximum value that the image can take. And lambda is your wrapping, basically your wrapping threshold. So based on these two quantities alone, you can actually guarantee exact recovery. And just to show you how the recovery is done, it's based on a simple iterative algorithm, which is going to start with some wrapped samples or image measurements, and then at the output you get the reconstruction. So this is a more interesting demonstration. So what you see on the left hand side is basically a quantization image. You can see that a 255 or an 8-bit image has been wrapped in amplitudes between -1 and 1. So on the left hand side you have a black and white image, and on the right hand side you have a colored image. And in either case, the algorithm, despite the high dynamic range 255 maximum amplitude being compressed to -1 and 1, you are exactly able to reconstruct the image. And this is only because now we have certain amount of understanding of how to recover these images with some mathematical guarantees. So of course, high dynamic range imaging is not the only thing that one can do. The abstract idea can be applied to a number of solutions. So one of the things that we have been pursuing recently is computed tomography. So we have seen certain experiments show up in the literature where people have argued that high dynamic range tomography can be performed by leveraging multiple tomographic projections of different intensities. But instead of using the radon transform, if we define the modular radon transform, which is going to take the radon transform projections at a particular angle and wrap them back as a modulo radon transform, then you can get a low dynamic range measurement from which you can reconstruct the high dynamic range tomographic projection. And pursuing this line of work would allow us to then argue that we can reconstruct high dynamic range computed projections that arise in the context of tomography. So here's a proof of concept sort of idea, where you can see the conventional Shep low gun on the left, and you will see the radon transform in the middle. However, you can again wrap this radon transform using the modular radon transform, where you get low dynamic range measurements. And then using the algorithm that I have not yet described in this talk, we have shown that it is possible to reconstruct the original tomographic image exactly. So what we have done recently is that we have taken some experimental tomographic data, and then we have passed it through our analog to digital converter, which can perform these modulo samples. And based on that, we have sort of made a proof of concept work, which would be beyond the scope of this particular presentation. But the main idea is that you can also perform high dynamic range reconstruction in the context of tomography. So that was the first part, where the idea was that you can take quantization noise and then recover high dynamic range images. But now the second part of the talk is how we can use, again, noise from the measurement to actually perform very low complexity, time resolved or 3D imaging. So for the last many years, capturing the plane optic function and its parameters has been the holy grail in imaging. And many different ideas have been adopted, for instance, illumination diversity, view diversity, and so on. But the idea of capturing images at time resolution is a very recent sort of idea, maybe just 10 years old. And one particular application of this idea is time-resolved imaging, where you have an active sensor, it emits light, the backscattered light comes to the sensor, and you know the depth or the time of flight. And this is a very rapidly expanding field. You can see many familiar faces here who have contributed to this problem of time-resolved imaging in different contexts, most notably the first paper from Andreas Welton and Ramesh Raskar about looking around the corners, and then now we have all kinds of exciting solutions. But if you look at how these images are captured today, then we have predominantly three different modalities. The streak tube, where you get picosecond resolution, but you can only scan a line at a time. You have then the SPAD system, where you can get to sub-nanosecond and you get low resolution images, 2D images like 64 by 32. And then you have a more relaxed kind of sensor technology like lock-in sensors, which would give you 160 by 120, but then they're going to give you a temporal resolution in terms of nanoseconds. And despite all this progress, we would like to have a sensor which can reach megapixel resolution. And unfortunately, most of these technologies would not be able to answer this question. And the reason is because these sampling devices or the imaging sensors, they are going to perform a time-based sampling at each pixel, which slows down the overall acquisition. So you are practically computing a full 3D tensor each time you use a time-of-flight sensor. And therefore, as you increase the pixels, just the sheer size of data would increase. So despite all of this fascination around the applications that time-resolved imaging sensors can offer, we still would like to desire a sensor which offers you very low resolution imaging, but with very high megapixel count. And how can we go about that? So if you look at the context of technology integration, then first we had some kind of a quadrature phase sampler, which uses some kind of 4-bucket trick in the context of lock-in sensors, and then those were enhanced to give you more sophisticated fast samplers like Kinect and so on. But now what we are trying to argue is that we are going to use 1-bit samples. And by using 1-bit sampling, because you only need to know the sign of the measurement, then at each pixel, you are going to minimize the sheer amount of information that you are going to capture. And this could be the pathway to the next sort of megapixel sensor, because now, of course, you are going to capture the sign of the measurement, and you will get a lot of noise, because if you have a 16-bit measurement and you only look at its sign, then you have a lot of noise. But as I mentioned, exploiting noise is the main idea in our work, we will see that we can actually do this, and this gives you very interesting results. So just to lay out the idea in one shot, what you see on the left-hand side is a proper 3D stack computed with a consumer camera. But in the middle, what you see is 1-bit samples that we have actually computed based on the left-hand stack that you see. And here in the figure A, you can see one particular pixel of the full 16-bit sensor stack, while in figure B, you can see 1-bit samples taken from the approach that we are proposing here. What is remarkable is that you can use the data in figure A or figure B, and in either case, you get the exact depth map, which is represented by the 2 spikes in figure C. And that's the main idea, that we can compress the whole 16-bit information into 1-bit information, provided that oversampling is there. So what is the main idea behind this work? Well, our main bottleneck is due to what is known as the analog to digital conversion at each pixel. And instead of using the conventional point-wise sampler at each pixel, what we are proposing is a 1-bit sampler. Now, what we know from conventional 1-bit sampling is that if the incoming waveform is band limited, then with slight oversampling, you can use a Nyquist-Shannon formula for reconstruction, which means that you can still take this value Q, which is plus or minus 1, but with Nyquist-Shannon interpolation, you are able to reconstruct the whole band-limited function back. And this is a very interesting aspect. But keep in mind that information such as depth is not band-limited. So to overcome this barrier of sort of noise, what we resort to is what is known as noise shaping in literature. So if I start with a first-order finite difference filter, then I can create a finite difference filter of order L by just recursively convolving the sequence, and this defines a high-pass filter. And this is something very basic. So if I look at my, 1-bit samples, then this 1-bit sample is basically the original data F and an additive mixture of some noise, which is where the noise variable is U. And if I do the Fourier transform, then we know that from conventional Fourier theory, we have additive the 1-bit spectrum of Q, which is a difference of the noise and the original data. But however, because we know that this filter V is high pass, you can see that all the noise is now concentrated in the high pass part of the spectrum, and the low pass part of the Fourier spectrum concentrates the signal structure. So there is this beautiful result from Ingrid Dovishi and Ron DeVore, where they prove that, in fact, when you have a filter with L tabs, which is what we typically use in all electronic systems, then your error bound is directly controlled by oversampling. So what that means is that the more densely I sample, the more I am going to remove noise from my data. So now, coming back to the time of flight problem, we know that the time of flight information, which is the delays tau and the amplitudes, manifest as some kind of an overlapping pulses. So now what I can do is I can take the 1-bit samples and write them just work them out mathematically. And then what I can see in my Fourier domain equation is that the noise is concentrated in the high pass, and in the low pass, I have a sum of signs. And where do these sum of signs come from? They come from the depth information that I'm interested to capture. So then, by isolating the Fourier transform of the signal structure, despite the fact that there is noise, we can actually implement an algorithm which robustly computes these sinusoidal properties, because what you see in the shaded yellow part is just a bunch of sinusoids. And this is a very classic problem in signal processing and spectral estimation, and people have studied for a very long time. So here is an example where I have taken raw data from a time of flight sensor. So what you see here is a conventional depth map in the left, and this is a full 16-bit data. What you see in the middle is the reconstruction from the proposed approach, where you look at 1-bit sampling with 1 filter tap. And as I mentioned, that as you increase the filter tap from 1 to 2, you can see that the reconstruction property in the rightmost figure improves. And what is really interesting is that if you look at the rightmost figure, it's almost indistinguishable with respect to the first figure of which is 16 bits. And this is very interesting because now it shows that you can actually implement a 1-bit sampler and you would get a very close property as if you had a 16-bit sequence. And this is only because you were oversampling. We can also repurpose this kind of idea for time-resolved imaging, where you want to do some kind of diffuse imaging. You want to see through a diffuser, so you have the conventional measurements here. And then in the bottom, again, I'm comparing basically the the reconstruction from 1-bit measurements. So what you see is amplitude in the bottom left, and on the bottom right set, you see the reconstructed depths. And what is again very interesting is that it's indistinguishable compared to the full 16-bit measurement. And this is the workhorse of our low complexity acquisition, where you capture noise, and I say noise because it's 1-bit data, and from this 1-bit data, you are able to reconstruct because the original signal, because you have a fair amount of oversampling. So to conclude this talk, I started with the idea that one man's noise is another man's signal. And the main idea here is that instead of using noise as noise is defined, if we use structured noise, then the structure of noise can be shown to have a lot of relevance when the noise is still signal dependent. So concretely, I showed to you 2 examples. The first one was based on quantization noise, and the main idea here was that you can do high dynamic range reconstruction if you sample quantization noise. And in the second example, what I showed to you is that if you acquire 1-bit samples, then because 1-bit is a very low complexity acquisition system, then you can basically use more sophisticated mathematical or computational algorithms to recover the information loss that has happened because of 1-bit sampling. But now the advantage is that with 1-bit samples, you can perform very high spatial rate information capture, which would not be possible with conventional ADCs. So to summarize, I would say that wherever there's a bottleneck in terms of a hardware system, then by carefully thinking about the noise structure of the problem, in fact, we can go beyond these bottlenecks if we are willing to trade off a slightly imperfect acquisition system with more advanced mathematical algorithms. So thank you for listening, and if there are any questions, I'm happy to take them now.
Great, thanks for this really interesting talk, Ayush. Looks like we have a couple questions in the chat. The first question is wondering if you can interpret the presented modular reconstruction algorithm as a phase unwrapping method that could be applied to other existing problems like indirect time-of-flight phase unwrapping.
Right, so yes and no. So traditionally, when we think about phase unwrapping, we do not have any control on redundancy or signal structure. In fact, what is very interesting is that for phase unwrapping problem, you will never see any Nyquist-Shannon reconstruction criteria. So for Nyquist-Shannon, you know that you can sample a signal twice the bandwidth, right? For phase unwrapping, you can see the literature, you will not find it. And this is the main sort of new idea that redundancy meaning extra measurements than needed, is what makes compressed sensing, deep learning, and all these new breed of algorithms work. So I think what is interesting is that, yes, there is an analogy of folding of the information, but what we have understood is that, in fact, fundamentally, there are significant differences which makes this problem different and sometimes more complicated than phase unwrapping. So the answer would be not so easy, yeah.
So the one thing I'm trying to understand, it sounds like you almost get something for free just with this little bit of how you change the sampling. Yes. So like in practice, you're doing high dynamic range imaging. You have this equation that tells you how much you need to sample, and it's dependent on where the modulo is and yes, the dynamic range. So what does that look like? Can you just use a conventional resolution sensor and get higher dynamic range, or does it have to be much larger resolution?
Right. So the answer is that you would have to have a new hardware which is folding the information before it's being sampled.
Right.
Because before sampling, we are in the analog domain. So we need to have an analog signal. Now, one thing that some practitioners in audio engineering have exploited is that if you have a 16-bit data, okay, and you throw away the most significant 4 bits, you get a modulo implementation.
Right.
So one option is that you can take a consumer sensor and you can actually throw away its most significant bits, and then with what remains, you actually get modulo implementation. However, thanks to many circuit designers who have been doing this since 2000s, they have actually implemented these circuits. What they lacked is an algorithm for recovery. So they captured the modulo image as well as the number of times those wraps have happened. And this created a bottleneck in their implementation because they had the circuit to fold, but they also need to know how many wraps have happened. What we are saying now, that because purely of algorithms, you don't need to record how many times the wraps are happening. And hence, we believe that we can take some of that existing machinery and use it with much more simpler circuitry. And some of the Ramesh Raskar and some of his team members and some other groups have also tried to do that. But I think what's missing there is truly unleashing the algorithmic power based on mathematical background. That's what we are trying to do. But yeah, most of it is unanswered and very interesting question, by the way.
Yeah. Okay. Okay. And there's one more question in the chat. Barmak Heshmat says that he loves the title of the talk. What is the best way to have the sensor actually hold the signal once it passes the saturation? Can the modulo sampling be advantageous in the lower end of the dynamic range? But I think you kind of answered this, right? You're actually you're folding it before it's actually sampled, right?
Yes.
Is that correct?
Yes, absolutely. So, so one thing I would like to add that a lot of people sometimes miss is that if you have a fixed bit budget, let's say you have 8 bits, then it's much better to give 8 bits to a modulo sampler, because if you assign 8 bits to voltages between 0 and 1, you get a much higher resolution than you assign 8 bits to voltages between 0 and 10, because your intervals are much larger. And therefore, in many applications, you cannot recover a signal which is very low dynamic range because your quantization has pushed it into the noise floor. But with modulo, this would not be a problem. And in a parallel sort of work that is emerging in the signal processing community, now people are starting to address this problem from compressed sensing point of view, because they are interested to see that they can recover very low weak signals by folding them, because quantization still helps you capture that information which was previously not possible when signal was not folded.
Really interesting. And I think there are potentially many applications, as you've shown and discussed, for computational imaging as well. So I hope that this is something that gets picked up and we see even more interest in this area. So thanks again for your talk, Ayush. And at this point, well, this concludes the second session. We'll be back with the third session of the CCD workshop in about 45 minutes. We'll resume at 1:30 p.m. Central Daylight Time with the third session. Thanks again, Ayush, and we'll see you all soon.
Thanks for organizing. Thank you.
Hi everyone, welcome back after the post-lunch break. Very excited to introduce our fourth keynote speaker. Today we have Professor Kostas Delides from the University of Pennsylvania. Kostas is the Ruth Slalom Professor at CIS at UPenn. His research interests are broad, spanning both computer vision and robotic perception, addressing challenges like motion in space, geometric design of cameras, interplay of geometry and appearance, and many more. He has won many awards, too many to list, but a couple highlights that I would like to just share with the audience here. Kostas is a excellent teacher, in addition to his research, and has widely circulated Coursera courses on robotic perception and robotic navigation applied to computer vision. So I've met many engineers during my time in industry who watch his courses to learn the basics of closed form algorithms in computer vision. Secondly, Kostas has also... welcome back after the post-lunch break. Very excited to... Kostas has also graduated 24 PhD students during his time at UPenn, and I'd like to turn it over to him for the keynote. Thank you, Kostas.
Thank you very much, Achute, for the very nice also spin, and you mentioned also the online, our online courses on geometry together with Jumbo Shi. I would really like to thank the organizers for first continuing this workshop and for inviting me. This is really, the whole day has been so refreshing to hear things different than in many other workshops, and very, very inspiring actually talks. So I'm going to talk about algorithms for a quite recent new sensor called event-based camera. And this is work with Alex Zhu, Ken Cheney, Bernd Frommer, Ziyun Wang, and Kendall Quinn. Let's start from the very basics. So how a biological eye work. Let's start with one measurement that was done at Penn by measuring in 2006 by Vijay Balasubramanian. They measured the guinea pig bandwidth of the optical nerve, being about 1 megabits per second. And by extrapolating in the number of ganglion cells, like linearly extrapolating from the 100,000 ganglion cells in the guinea pig to the 1 million in the human ganglion cells, the estimate became something like 8.7 megabits per second. So this is a very impressive bandwidth compared to the raw bandwidth you get from an HD TV signal, not after compression. When it comes to your home, if you have seen like in Netflix or Amazon Prime, you have seen bandwidths between 1 and 5 megabits per second, but the original bandwidth of high definition is about almost 1 gigabits per second. So what really happens between the photoreceptors and the optical nerve that produces this very low bandwidth? And I was inspired by Noah by showing things. I will not show a poll, but I will ask you, and let me make this the top disappear. Yeah. So I will ask you to stare at this black cross. And I'm sure after 4 or 5 seconds, you're going to see all the color blobs disappearing. And the reason why this happens is first that any biological eye is perceiving only changes. If something remains static, then it is just produces zero activation in the sensor. This was discovered very early in 1804 by Troxler. And of course, you will ask the question, why do we perceive the cross and we stop perceiving the color tones? And there are two main factors in this phenomenon. One is that you are fixating on the cross with your fovea, which does still micro movements while you're trying to fixate. And because there is a the fovea is in very high resolution, because of the micro movements, the stimulus always changes. When these micro movements still affect the whole eye, but because the receptive fields of the cones, which are in the periphery and perceive the color, they are much bigger than the receptive fields of the fovea. And I must say, not the receptive fields, really the pixels, like the photoreceptors. And even if with small motions, the differences that appear when you do these micro movements, these photoreceptors are really not significant to trigger a change. And that's why they're disappearing. The same happens if you look at this blue ring. This is, try to stare at the red dot. And it takes a little longer than the previous one. But you will start, the blue ring, will start to see it much thinner. And at the end, it will almost fade away. So this is one of the very first proofs in the biological literatures in the human behavioral experiment that the biological eye is really responding only to changes. And this has been measured also not only behaviorally, as Troxler did 220 years ago, but also with measuring with electrodes what exactly information is, what signal is coming out from the ganglion cells of a salamander and of a rabbit. And you see them as S1 and R2 here. And what is coming out is what we call spikes, these spike trains that are only responding to changes in the stimulus, which is shown here, this intensity stimulus. And here you show the number of spikes, because this is just over a very short interval, like 50 milliseconds. And this shows the number of spikes in two different temporal revolutions if you plot it as a time histogram. So the output of a biological eye is really just these spikes. This is very different than what we have today in cameras, where we just receive frames. This is what we learned in computer vision in any course. You learn that the input is just a sequence of frames, arrays that you can process with a computer program as two-dimensional arrays of RGB. So frames came up also very early, and you will see this film recorded by Edward Muybridge at the University of Pennsylvania, where he was trying to prove that none of the legs of the feet of the horse are touching the ground while galloping. And then there were several other imitations. That there are several first trials to produce film by this cyclograph here. And the film came out with 10 frames per second, and later 20 frames per second. Now, frame-based cameras are beautiful for photography, but they were really not built for survival, to be put on robots. They were built mainly for visualization and for movies. So they suffer from the temporal aliasing, which you see on the upper left, on the upper right there. And their spatial and temporal relationship is really completely disentangled. So you're going to see, even with a very high temporal resolution camera, like the one here, which is from the 240 frames per second iPhone, you are going to see, you see that you get not only heavy temporal aliasing, but also motion blur if you try to get individually these frames. The reason being, even if a frame exposure is only, let's say, the full time between the two frames, like 1000 divided by 240, about 44 milliseconds, still you get blur if something is moving very fast. I have also a like a fidget spinner in front of me. You can see now, if you see my face and you see the fidget spinner, you see very clearly the temporal aliasing, the way it is, it goes through multiple samplings here through the Zoom or YouTube. So the intensity values and the RGB values are really perfect for recognition, perfect for solving the correspondence problem in computer vision, but they have a very limited dynamic range. They are blind between exposure times. They are, as you see on the right, they're susceptible to motion blur and temporal aliasing, and they really consume a lot of power. So in the early 80s, Carl Vermeet at Caltech and Misha Mahovald tried to build a camera that imitates the biological eye that they presented at the beginning. And if you read this abstract here, it really describes everything that all event-based cameras are about today. It says a resistive network is used to compute a spatially smooth version of the receptor outputs and amplify difference between the receptor signals and their smooth counterparts, form a second-order spatial filter, measure outputs, show many of the characteristics of the bipolar cells on the vertebrate retina. So these days, there is also not the sensor that has been first really was created and being functional by Toby Delbrick, who is really regarded the pioneer of the event-based vision, also from Caltech. The first sensor, which was 128 by 128, it's really imitating all three layers of the photoreceptors, the bipolar cells, and the ganglion cells by taking the logarithm of the incoming luminance, pretty much the number of photons that are coming in. Then you get the difference between these logarithms here. And then depending on whether this difference exceeds a threshold towards the positive or towards the negative, then you create these spikes, which are on for positive changes, off for negative. And then this has to be reset and then so that the difference is really computed from the beginning. And this is what really happens at 1 pixel. If you plot the logarithm of the intensity, as long as you remain inside this vertical threshold, then you create, as soon as you pass it, you create an on event. As soon as you pass it to the darker side, you create an off event. And the only formation that is remaining is on the bottom. This is a nice slide by Cedric Sherling from Australia National University. And the raw signal is what you really see on the right. This is the signal from a fidget spinner like this one. It is visualized in frames on the left, but this is not what you process. What you process is this XYT volume here, where every timestamp is to the accuracy of 1 megahertz, 1 microsecond. So what can you do? This is a very big challenge. What can we do with this XYT point cloud pretty much on the right? And just to give you an idea about the difference between frames, this is if you integrate it in 1 millisecond, 2 milliseconds, or 5 milliseconds, this is what you get as simulated frames. And this is here, you already see some blur when you increase the integration time. So there are many such cameras these days. They have a very high dynamic range because they capture only the difference. So even if they get at the very, very dark or at the very, very light, then they can still capture the difference in the logarithm. So all the state of the art has more than 120 decibel. This is, you have to compare with something between 50 and 60 in the regular cameras. their consumption is the under 100 milliwatt, even with the highest resolution, compared with always greater than 1 watt in all the cameras that you're using today. Then the bandwidth is relative because it really depends on how many pixels you have. For the highest number of pixels, it's really about 1 giga events per second. All these are from a very nice survey we have written together under the leadership of Guillermo Gallego, and disappeared in IEEE Transactions on PAMI last year. So the very first question we're asking is, let's say, what can we recover from this series of events? And something that you can immediately do, and Toby did it in 2014, I show it here, is really taking these events here on the bottom and just adding the threshold that you have used for positive and negative changes. And this is different for positive and negative. So as a formula, it really looks like this. If you're given the events, the reconstructed signal is this really quadrature integral you see here, where you really don't know where to start because there is no absolute intensity. So if you keep adding them, you're going to keep adding them forever. So we need some kind of forgetting of these events. So we are adding an exponential here. And this is, as you see, this is an operation which really asynchronous. It's really updated only after every event. It's not updated by waiting for events to make a frame. And this is an experimental setup to understand more the cameras with rotating turntable and the Siemens star here. And observe that we have a part without the signal here, the white part. And this is if you just add these thresholds or subtract them, this is what you get. You get in the white area where there was absolutely no signal, you get this ghost image because it remembers the system remembers what it has seen forever. If you see if you work with exponential moving image, then this really disappears and you get a pretty good reconstruction of the original image, although you didn't know the original intensity. In terms of space, if you want to do what we call an asynchronous convolution, which was introduced by Sherling and Rob Mahoney, you just have to remember a very basic signal processing 101, where you defined the impulse response as the output of the signal, which is just a Dirac. And every event here is nothing else than a Dirac. For example, a negative event here, which is a timestamp, the XY coordinates, and -1, is nothing else than this array here, which if you convolve, let's say, with a Sobel operator here, you are going to have nothing else than the replication of the Sobel operator. And this is how you create this is how the convolution with every incoming event happens. Now, you're not going to have only this -1. After some time, multiple pixels will be occupied, but you can have a result of a convolution at every timestamp. You don't need to wait for frames. And in order to, in terms of reconstruction, we found out, but as a matter of fact, if you do the same way, like asynchronously, if you don't do a convolution, but you do this nonlinear bilateral filtering, after convolving first with a Gaussian kernel K, and you apply a bilateral filtering, which is nonlinear, then you really get a very good reconstruction. And this is without the exponential filter, just to have the effect of the reconstruction of the signal. This is done without any learning, without neural networks. The other versions here also by the previous, the bilateral filtering was ours. Here you see the raw frame, which because of also the speed and the lack of enough photons to create any signal in the, this is what you get. This is if you use the frames in between, and that's why you get the darkness here. And here, if you use only the frames where you assume that you don't know where to start integrating, like the DC component of the signal pretty much, and that's why you get this gray thing here. This is from one of the most recent results by David Escaramuza's group, where 28 frames per second signal is together with events can output pretty much any temporal resolution. This uses an attention network to do that, but this is probably the state of the art. I did a CVPR paper this week. This is one of the probably the most immediate applications that will come up on cell phones equipped with event-based cameras, producing like slow-mo at any speed you want. Now, when we process events, we have two main challenges. One is that we don't have a photometric consistency for correspondence like the one you see here. And the second thing is that we don't have any training data if you want to do anything these days, where frame-based approaches have a lot of data to work with. And there is two solutions for this, that the corresponding thing to the photometric consistency is really the lack of any blur after we are warping the events. And the second is that we really try to do everything with a self-supervision signal, as you know from many prediction algorithms these days for video. So starting with features, I will give you a very brief history of event-based algorithms. It's not clear what is a feature in this picture here. And others like Riyad Ben-Osman and several others in event-based vision, they try to define local surfaces in this point cloud. What we defined as a feature, as you see in this, this magnification here from what you see on the left, is that it is events that are together, is a set of events that is moving coherently in motion. So we defined it as a data association problem, where obviously, as any data association problem, you have a chicken and egg based on the assumption of the constancy of the flow, and you don't know what is the flow. So we solve it with an expectation maximization problem, where you, in the expectation, we compute the probability that they belong to the same event, and in the maximization, we compute the optical flow. So how you group them in time, and how much you consider for this association, is we make it that it is 1 over the speed. So you see here is the speed, is the slope of this curve, and the higher is the speed, the smaller the window, the slower it becomes here, the bigger is the time window that we consider. And here we have been, this was our very first experiment, it was very revealing. What you're going to see, this is real measurement on seconds. This was a very fast sequence. The optical flow is in the order of 5,000 pixels per second. If you divide it by 30, the features really disappear. So there was no way to compare with a regular camera. So we went with an iPhone, still the iPhone 6, not one of the current ones, but still 240 frames per second. And this is just one snapshot. I will play also the video, but you see particularly on the wheels here, you see all the distortion in trajectories you get with a KLT on 240 frames per second. And you will see the smooth trajectories that you get on the right from the event-based system. So the truck was driving with about 60 miles per hour. And this is a complete, on the right, it is really a complete slowdown of the sequence. So we haven't reached still 1 second, right? It's 0.4 seconds, 0.5 seconds, and so on. So this is how fast the sequence is. So in order to study it, we produced a stereo data set by having a combination of Velodyne LiDAR and 2 high-resolution like regular RGB cameras and 2 high-resolution event-based cameras. And we captured a lot of data with a quadrotor, with a car, and with a motorcycle. We created a 3D map of the environment using the cartographer and LOAM, and with the LiDAR and the RGB. And this is like the sequence that we have on events on the left. This is the RGB, and this is the ground truth depth and trajectory. This was really the first data set that was so comprehensive in having ground truth. And recently, I think 2 months ago, a second stereo data set with LiDAR, the DSEC, was created by Davide's group, and Prophecy, the main producer of event-based cameras, have produced a very extensive annotated data set, not for motion, but for the existence of vehicle for automotive applications. So coming to the main result, I'm going to show you about optical flow using events. So how can we compute optical flow, like dense optical flow from incoming events? So we, first, what would be the input representation to whatever algorithm we use if we don't want to use frames? And although the ideal is really to have an asynchronous processing, and this is our goal, here we made a compromise and we binned these events in red and blue bins, depending whether they were on and off events. And we submitted to the algorithm, to the system, a spatiotemporal volume in XY and for 30 milliseconds like in time. So the architecture we use, it's really a learning architecture. It is a unit. The first version didn't have a computation of any 3D information, so this was missing. So the input were the separate channels for on and off events over a time window, and the output was 2 channels, the optical flow. And really the context of the scene is really kept by this like low resolution like bottleneck here. And losses are applying to multiple resolutions here so that multiple lengths of optical flow are captured. Then we extended it to similar to the SFM learner, the structural motion learning traditional paradigm, not traditional, like recent, like from 3 years ago, where you regress from with a linear regression to the rotation translation parameters, and instead of computing the flow, you predict the depth, and using the rotation translation, you can predict the flow. Now, what loss are you using there? The loss you are using is that after you predict, you don't use any photometric loss, which we first tried actually for cameras that we had this information. But what you really use is the following. You take every event and the predicted flow, and you unwarp it. And you expect over a volume that you get the minimum blur. And this is simulated here, that if you take a volume of events and you warp it with a correct flow, you expect everything to lie in columns, like stable, big stable, a long time. And you can use several such blurriness, like loss functions. One might be the variance, another might be the average timestamp over these figures. And but this is the main message from that. This is really that this is a very self-supervised. We don't need any ground truth flow, and that by training it on sequences of drones, motorcycles, and cars, we can still generalize to many more situations, like the one with the fidget spinner here, where you can see at some point we really turn off the lights, and you can still see this is a very good computation of the optical flow. That was for us amazing, given the that we expected that this is like something like it has the bias of like kitty sequences, which are more driving, and would not generalize to this, but it was really had really very good generalization capabilities, mainly because there was, I think there was much more weight given to the incoming signal and how much signal is there than rather to the inductive bias of the bottleneck, pretty much of the context in our network. But this is a very, very impressive sequence where you can hardly see even with a human eye when you look at the fidget spinner in which direction the fidget spinner is really turning. And we had very good results compared with a standard flow method that uses RGB images. So these are, for example, situations of very fast throwing of a ball, where our algorithm works pretty well. And you can see it also in the slow motion here, the throwing of a ball. And it generalizes to many other situations like water. And I will explain with an example of why it does it so well within optically challenging situations, or a small cataract here, waterfall. Here is driving in the night with a motorcycle driving 140 kilometers per hour. Oops, I don't know why this video is not playing. That's very strange. Yes, we have very courageous students who drive with 140 kilometers per hour in the city. You see that there is still, due to the low resolution of the event-based system, we don't get enough signal on the road itself, on the asphalt. We don't, we get only on the lanes. And we're gonna show some more of the driving. This is when you face a light and you try to see like we are more interested in the motion of the tree here. This is very difficult sequence, completely saturated. The glimpses, the flashes that you see are really also effects from the pixel noise that you have many times, where the optical flow is really just having some priors in that case. And yeah, this is the right sequence from the motorcycle. You can see very well the radial, like direction of the optical field. We really wish, and we have seen it now with new cameras. This is only with 340 by 246 pixels. We really want, with the new cameras, which go up to 1 megapixel, we are getting much more optical flow on the strip itself. So this is also not only computing the optical flow, but predicting the depth. This is the event image. This is the event image after being worked with a predicted flow. You see that this is the loss that is really minimized. This is the ground truth focus of expansion and depth, and this is the predicted one. And once more, so this is something that you will like here about. This is like capturing water poured inside the container. It was amazing to see first the events themselves, which really look like the water particles. You see that the turbulence is captured really very well as you see everything running out. And this is the corresponding optical flow. You see a lot of noise, of course, outside, but you see very well the whole turbulence that is captured here on the bottom. And you are going to see that we try to capture this also with fast now with an iPhone 12 slow-mo, which is this one here. And to apply a state-of-the-art optical flow algorithm on the slow-mo sequence. And we see that the direction here is quite good of the flowing, but the direction, the flow field on the bottom is really very, very sparse and quite wrong. And the case is because of the really photo consistency assumption of the optical flow, which is not really valid when you have this, like all the refractions and reflections that are happening inside the container, while the event still, the event camera, which is 640 by 480 here, it is a higher resolution than the ones we used in the MVSEC dataset. It really captures all the small motions of the bubbles, and it captures them without any like saturation of the signal. We still don't have the math to explain that, and I wish that in the future we're going to have a much more controlled experiment where we will show why, in the case of liquids, we're doing so well. So this one frame of the 240 frames per second and classical optical flow versus self-supervised flow computation on the events. So back to the, I'm gonna have to finish, I think, back to asynchronous processing. What we did is everything, we are not happy with the volume. So we're trying to see, have a hybrid solution where we learned synchronously, but we applied asynchronously convolution. So we take the whole filter bank from the first layer of the neural network, frozen, and we applied with asynchronous convolution in order to detect the really salient parts of the scene. This is the raw event sequence here, for example, in this sequence where we try to detect a drone. And you see that we're filtering almost 100% of all events, except when they have, we have a drone flying by, like in this case here, you might see, where we filter about 90 to 95%. So there are several recent developments. This was the technical part of my lecture. Prophecy and Sony have joined forces. Sony is producing more than half of all the imaging sensors on the mobile devices these days. Samsung is producing a SmartThings device that you can order in Europe for 150 euros, which preserves privacy and detects like falls in a home environment, detects also pets. Events has been used together with an associated projector in a system that simulates the retina. And at the same time, the doctors are applying optogenetic therapy for healing retinitis pigmentosa. And the reason why they don't use a regular camera is because they really need a very fast capture of the incoming stimulus. This was an article in Nature Medicine. This is our survey of the field. It's already 1 year old. For most recent stuff, you should visit our workshop here. And I think as a take-home message, I have shown at least the three parts, the high speed, the no blur, and the like moving in the dark or very high saturated areas. I think the main challenge for using the event-based cameras is really to have an extremely fast computation for either using FPGAs or what is really the future in neuromorphic AI, which is the spiking neural networks. I think I'm exactly at the 40 or 38 minutes, and I'm going to stop here. Thank you very much. Thank you again for organizing this really great workshop.
Thank you, Kostas, for this outstanding talk. Just to keep the workshop on time, I think we only have time for one question. So I'm a very selfish host and moderator, so I'm going to ask the question actually. You did a beautiful result on the liquid with the event camera. And I think it opens up the question if maybe more exotic computational camera systems can be built upon the event camera. And I'll give you one example just to seed conversation. So the flow and kind of the variation in the liquid is also due to the caustics and the specularity, which are view-dependent effects. So there's a kind of a synergy between kind of the photometry changes as well as the viewpoint changes. So I'm wondering if some sort of light field event-based camera would be exciting to look at in terms of going deeper into the liquid analysis problem.
Yes, actually, I should have put it on the green text here. The combination of optical and electronics, right? Because right now, we have put it once in front of a mirror for an omnidirectional view of events. There is a lot of work on tracking particles behind the microscope, tracking particles with event, even like tracking like T cells. And I definitely thank you very much for bringing this up. And in my next talk, I will add it as a first point before the processing. The combination of optical and electronic, whether it is with micro lenses for a light field, or for any other, like of all the optical advances that we have seen either in the workshop over the last years or even in CVPR. I think that's a really great idea. Thank you for bringing this up. Whether it can be, right now, the hottest thing is under the microscope applications. There is omnidirectional, there is some with putting inside the telescope. There is a very cool group in Australia, Greg Cohen. They have sent a lot of event-based cameras for capturing light changes in the universe. And definitely any other actually creative optical replacement of the regular lens, I think it would be at least revolutionary in science, and might be even in terms of light field, or might be on reconstructing very fast scenes. The other application is like Oliver Crosser's projection of a very fast projection of any signal, whether it is like a Gabor or like laser stripes.
It's very exciting. So there's actually a question that just came through the chat. I just refreshed my feed. I'm going to give the question explicitly, but definitely it's probably a larger question for a post drink at the conference. But
oh yes, that's a great. Yeah, please. I was reading. Yeah, please read it out so that people hear it.
Yeah. So most event cameras still provide rather noisy data, while human vision is rather smooth, at least experientially. So what is missing in event cameras to reach human vision performance? And this question is asked by Mark Scheinen, a postdoc at CMU in Srinivas's group.
Yes. That's a great question. It is. We are still spending a lot of time. My postdoc Bernd, who is here in the picture, he is spending a lot of time on just counting the events. So in the rotating wheel, if you does a full resolution, it has the same number of changes into black to white and black. So one would expect that we get the same on events as the off events, but this is not the case. There is a lot of electronic leakage. And I think Toby and Delbrick and the other hardware electronics people, they still work a lot on that. Now, if you look at the signals in the optical nerve, they are also very noisy. If you look at the spike outputs of neurons, they are also very noisy. And since the neural measurements are also noisy, probably there is something in the algorithm, the architecture, closer to the cortex, closer to higher levels, which makes us see it much clearer. That's my conjecture. And that we don't see any speckle or anything that we see with the events. It is any direct integration like averaging with an exponential. If it is done in a learned way, like the recent like algorithms for integrating them and producing an original signal, they also eliminate noise. Now, we can eliminate almost 99% of the noise with just using very simple like spatial correlation filters and the first layer of the optical flow. So we can do that for sure now without going into like higher levels of perception.
Excellent. So that, you know.
Oh, sorry, I'm distracted because I'm reading the questions at the same time. You should read them out as a moderator. Yeah.
Yeah, no, unfortunately, we should move to the next talk. What I'm going to do is, Kostas, you have access to the question in the chat. Please.
Yes, I will answer them in the chat. Thank you very much for the questions. Yeah.
Thank you very much, Kostas, for this talk. I'm going to copy the survey paper here also in the chat, so feel free to read that if you're in the audience. That's a good overview for event cameras. Thank you very much, Kostas. Excellent. Hello, everyone. Welcome to the next talk. It's a pleasure to introduce Regine Eckert. She's a PhD student in the Computational Imaging Lab with Professor Laura Waller at California, Berkeley. Her interests are broad, but include computational imaging systems for high resolution and high dimensional microscopy. She has a plethora of applications and interests outside of her research as well. I happened to go to her website, encourage others to also visit her website, and it seems that she's an excellent photographer as well, in addition to being a microscopist and computational imaging scientist. So Regina, please take it away.
All right, thank you so much. Yes, hello, my name is Regina Eckert, and I'm going to be talking to you today about measurement diversity for 3D refractive index microscopy. Before I kind of dive into 3D refractive index, I just want to talk more generally about imaging. So in imaging, our goal is to understand something in the world that we're measuring, right? So in microscopy, this is usually something scientific. So for example, we might want to know what type of cell is this? What's its structure? But when we're imaging anything, we're really seeing that there's some light moving through some scene that we can measure on some kind of camera system. And then we're having some computational system that's asking, what exactly am I seeing? How can I actually understand this and use this in the world? So for 3D refractive index, we're reconstructing some type of 3D RI volume here. But I think something that we're all really interested in asking is, how can I actually make this problem work better? And I think what we've all really seen is that in order to do this, we do have to consider both sides of the equation here. We have to understand how can we optimize both our optics and our computation together to make a better computational imaging system. But this is like a really hard problem, right? There's a lot of different design considerations, both on the optics side, where we're asking things like, are the optics actually physically possible? Are they cost effective? Are they robust and usable? And then on the computation side, we're asking things like, is it fast? Is it accurate? Is it actually easy to use? So this is actually really difficult. We can't just like throw these systems into some big machine learning algorithm and tell it to spit out like, how do I actually measure these things best? So in this talk, I'm going to be talking a little bit more specifically about a question that I've been asking for 3D refractive index, which is how can I increase my system's measurement diversity? So I'll kind of get to exactly what I mean by that in a little bit, but for now, we're going to dive into 3D refractive index imaging. In this kind of imaging domain, we're using the native contrast of some really small organism to reconstruct its structure. So refractive index, just as a reminder, describes how a material changes the speed of light, and it also controls the bending of that light in transparent objects. So here I have this volume where I have this 3D cell cluster, and there's different properties that have different refractive indices. So the cell background versus the nucleus versus different organelles all are going to have different refractive index values. But it's really hard to image this because these things are really small, they're transparent. We can't actually directly measure this refractive index value, and we're trying to get 3D measurements from 2D images. So it's a really difficult imaging problem. All right, so that's the problem. Why do we even want to do this? You might be asking, like, what's the point? So there's actually a range of medical imaging applications for 3D refractive index, one of which is organoid development, so taking stem cells and understanding how they structure themselves into organs. But humans are just a part of a much bigger picture. Another application here is actually calculating improved scattering models for how light scatters in things like phytoplankton or snow algae to help understand and better model climate systems. All right, that's the application space here. So let's talk about how we actually approach this problem. All right, so I have my object, it's this 3D refractive index volume that I'm gonna call X. And I better put some light through this system, right? I need to be able to measure something. And I should probably use coherent light because phase is related to how refractive index delays light. Then I can model the scattering of this light through my object by this operator S. And since I said these things are small, we better use some type of thing to blow up the image so we can actually measure it. So we're going to use a microscope objective, which is going to have some point spread function that we can multiply. And then, of course, we can measure at our camera, but unfortunately, we can only measure an amplitude. We can't measure the actual phase of this. All right. So then we can use this equation that we've built up and formulate it as an optimization problem to solve it. So here we're having this kind of modeled thing of our how the light moves through our objects. And we're comparing it to what we've actually measured at the camera sensor in order to reconstruct some estimate of our volume X. So cool, we solved it, great. Ooh, we can go home now. Not really, right? This is a really complex reconstruction that I talked about. We can't actually just use one image to solve it. You can kind of think about it's a really dense volume, it's a 3D volume, and we're just measuring 2D information. So you can think about, you just really need a lot more information through the system in order to reconstruct all of that information that we're trying to get out. All right, so how have people attacked this? So previous methods have used a changing illumination angle to get 3D and phase information out of this object. So you can kind of think about this as holding your illumination constant and having different views of the same object. People have also used a change in focus. So again, you can think about having 3D information because you're defocusing the information in your scene. Finally, people have used rotation of the object. So this is really similar to CT scanning, where you're just rotating the object and therefore getting 3D information about it. So the question that I've been asking is, how can I best measure this data to reconstruct refractive index? And here I'm taking best to mean most accurately, most robustly, and then the easiest, fastest, and kind of least data intensive way. So the kind of conclusion to this, just as a preview, is the system that I've kind of come up with combines two of these previous methods, where I'm going to both change the illumination angle and introduce pupil coating at a Fourier plane in order to do this imaging process. So I'll be talking about that. And then at the end, I will also talk very, very briefly about how we can learn better pupil coating designs using machine learning. All right. So to dive into this system, This is kind of the proposed optical system that we're going to use. So we have an angle scanning mirror that's going to scan a coherent beam through our sample, which we're going to image with an objective, which is then going to relay the pupil plane of the objective to a phase spatial light modulator. So we're going to be modulating the conjugate Fourier transform plane of this system. And then we detected a camera. All right, so what we're going to do here is at each different angle of illumination, we're going to apply a random phase mask. And we can think about doing this for actually a lot of different modulation bases, because we have some pixelated SLM that we can randomly code to do whatever we want to do, right? So one easy way of thinking about this is doing some defocus kernel. So that would be really similar to just directly combining previous methods where we're doing the angle scanning and the defocus scanning. However, we could also just do random pixels and see if that works, or we could do something like a random coefficient on a Zernike basis. Now, actually, I've seen through this work that all of these different bases work fairly well and fairly similarly to each other. So I'm just going to be talking about the Zernike basis here to make some of the next slides a little bit easier to look at. All right. So what I've seen in this work is that including this pupil coding in the system increases our measurement diversity. And so here I'm defining measurement diversity to be having more diverse information content collected across my measurements. So we can see this by looking at some simulated measurements. So here I have this cell cluster phantom that we were looking at before. And I'm looking at the no pupil coding case here, so the kind of original diffraction tomography case where we're just changing the angle of illumination. And down the column, we're going to have a different angle of illumination for each measurement. So you can see that there's some information here. Some of the cells that are out of focus are kind of moving around as the angle scans, but generally these don't look that different by eye. However, when we introduce this pupil coding element, we can see that we get really a lot more contrast across these images. And so we can just think about having just different information in these images, which is kind of apparent to us visually by having this higher contrast. All right. So we reconstruct with that same optimization algorithm I showed before. I'll unpack some of these different terms here. So we have our data consistency penalty, where we're having our system model that includes the information about our angled illumination, our multiple slice forward model, which is the scattering through the object, the objective pupil, and now this random pupil coding that we're applying. And that's going to compare to the actual measurements that we get out of our system. We can also apply a prior penalty that can say things like, I think that my system, my object's going to be purely real or smooth in some way, things like that to make this work a lot better. And then we're going to reconstruct some estimated volume X that explains the measurements that we have. All right. So what we've seen in this system is that actually given all time and all data to compute, both of these methods converge fairly well. So here we're having all of our illumination angles up to the NA of our objective that we're using to measure. And so when we compare these reconstructions to the ground truth, we can see that both of them have fairly good reconstruction of the cell backgrounds. So this low spatial frequency, which corresponds to the RI values, is recovered fairly well. However, what we've seen in previous work is that this pupil coding makes the system more robust to limited illumination angles, limited computation time, and also increased background noise. But I'm going to focus on limited illumination angles here because that actually makes our system that we're using a lot easier to use if we can have limited illumination angles. So here we're looking at this original illumination angles that go up to the NA of the objective. And now we're going to cut down to a much lower NA of our maximum NA of our illumination angle, which corresponds to a 43% in our data also. And here we can see these reconstructions again. So what you're seeing here is that the Zernike coding reconstruction looks fairly the same as our previous result. However, in the no pupil coding case, which is kind of what our old system looks like, this cell background value is not reconstructed very well. So that's really cool because we're actually like getting more information encoded into these fewer measurements when we include this pupil coding. And we see that in experiment, this is also what happens. So we have this 3D refractive index phantom. And we can see that with less illumination angles, with the coating, we are getting those background values much better, just visually looking at them. And that this is true also for even lower numbers of images. All right. So you might be wondering why exactly does that work? I've talked about measurement diversity, but what's the mechanism here? And I'm not going to talk about the math here exactly, but what we've done is taken some transfer function analysis, and we've seen that this pupil coating has actually a better low spatial frequency weighting in our measurement system. So we can see here on the left, the original illumination case, and all of these kind of systems are getting more information in that low spatial frequency, so near zero. But when we limit the illumination down, the no coating doesn't have very much weight in those low spatial frequencies and therefore can't reconstruct it very easily. And digging into this a little bit more, we've seen that this is caused by having diverse pupil coating, which couples varied phase information, not the same in phase information, into our intensity measurements to make this reconstruction easier. All right. So just kind of taking a little bit of a broader picture away from this, I just talked a lot about some specifics for my system, but I just want to say that measurement diversity, which I've seen is useful in my system, is also important across computational imaging systems. So you might have already been kind of thinking this, right? There's some stuff from the 80s where phase diversity is used for doing wavefront sensing. There's also compressed sensing, obviously, where you have some incoherent sensing matrix that can reduce the measurements that you need for sparse signals. You can also think about having diverse data for machine learning, right? Where we need a wide range of examples in our data sets to have good results. So this isn't something that's just applicable for sparse systems or just applicable for non-convex systems. It's something that actually spans across all of these imaging systems and therefore is very useful to think about. All right. So I've talked about this kind of new proposed system for doing 3D refractive index imaging. I'm going to talk briefly, as time permits, about how we can learn better pupil coating designs for the system. So as I'm sure you've all seen, we can take this optimization algorithm that I've talked about previously, and we can represent it as a network by just unrolling every gradient step in our algorithm and treating it as a layer in a neural network. And the benefit to this is that we can then compute some loss compared to ground truth, and then back propagate that loss to update some parameter about our network, which can represent something in our system. So here, we're learning pupil coating from this unrolled network kind of system. So we have our learnable pupil coating over here on the left, which is input to our network, and is used to create all of the images that go into each of these iterations. Then we use this to kind of reconstruct a volume, which is then compared to a ground truth volume. And that loss is backpropagated through the network to update our learnable pupil coating and then update our images. And then we've constrained our system here to only have this limited illumination angle case to do this reconstruction. So that's kind of how we've thought about this. I won't go into the details too much because I don't think I have time, but if you're curious and want to ask later or email me, let me know. All right, so with that, I've introduced this new combination of illumination and pupil coating for 3D refractive index tomography. I've talked about how we might learn better pupil coating designs using machine learning. And all of this has been in service of doing better imaging for a wide range of different applications. Before I conclude, finally, I just want to kind of bring it back to what everyone else is working on, not just microscopy, but across all imaging systems, and just kind of urge you to think, when you're next thinking about how you can jointly design your optical system, can you ask, how can I increase my system's measurement diversity to kind of make this system work better? And with that, I'd like to thank my group and ask for any questions. Thank you so much.
Thank you so much for this great talk, Regina. I'm going to start with the first question from Yan Wei, which is, what if the data reduction came from randomly sampling illumination angles instead of limiting the angle? How would that affect the reconstruction?
Yeah, it's a good question. You could do that, and definitely, actually, if you just limit your illumination angles to be the larger illumination angles, then you actually wouldn't get as much improvement with the pupil coating as what I've shown, where you limit down to the lower NA. But the kind of benefit of doing this lower NA illumination is that you can actually reduce the complexity of the system design for doing the angled illumination. Because that can actually be like a really complicated part of doing this when you're going to high resolution systems that need like really high angles. So doing it where you're actually like limiting down to the least extreme angles makes the system design a lot easier.
Terrific. So there are a couple more questions. I'm going to pick one that seems a little quicker to answer. So Yunhao has asked, by using coherent illumination, will there be speckles? And if yes, how would one potentially get rid of this?
Yes, yes, and that can be a big problem. So what we actually do is I align with a laser, but then we put in a collimated LED that is fairly coherent, but not so coherent that you get speckle from every single optical surface. So yes, very good question.
Excellent. So thank you so much, Regina, for that talk. And there's one more question in the chat from a postdoc at Princeton, that Sang-Hwan Bak, that you can potentially address there. Thank you again for giving the time today. Now we're getting into our second invited talk of the session. And I'm delighted to present Vivek Bhuminathan, a postdoctoral researcher from Rice University, where he also did his PhD with Ashok Veeraraghavan. Vivek has made numerous contributions to lensless imaging over the past almost 5 years or more. And today I'm tell us what the recent advances are in the area. Vivek, take it away.
Thank you, Achita. Thank you for the introduction. Welcome, everyone. Thank you for being here for the talk. I'm Vivek Bhuminathan, a postdoctoral researcher at Rice University. And today I'm going to talk about recent advances in lensless imaging. Let's start with the conventional optics that's used in your cameras and every camera in general. That is lenses. The one element we are going to try to replace in this talk. So conventional optics, which is lenses, try to focus one point in the scene to a point in the sensor. In essence, the goal of lens design is to directly capture a perfect image of the focus plane and without any need of additional processing. However, there are limits and trade-offs when it comes to lenses. A simple one we can imagine is it directly maps a 3D scene onto a 2D image, losing three-dimensional information. And there are other trade-offs like trade-off between resolution and field of view, trade-off between light throughput and depth of field. Lenses can get heavy. And also there is a constraint on the thickness of the camera due to lenses, which we will touch upon later. Now, we have tried to solve many problems of the lenses using computational approach. Here is one example of modifying the lensing optics and adding computation so that we can reconstruct the depth image directly from a single capture. However, all of these approaches don't really get rid of the lens, but use the lens and capture an image that is still perceivable by humans. That means I can look at this image and say there's a leaf. And then with some processing, we are able to extract information. But none of these optics have gone beyond thinking beyond how lenses can work. In the sense, do we have to maintain this focus to capture an image directly to do many use cases. And that's where we are going to talk about how the lensless is going to help. Now, one particular advantage I'm going to pivot on, at least to begin with, to motivate lensless, is basically talking about the thickness and size of the camera. Now, for conventional cameras with the lens needs to be at a focusing distance away from the sensor. If it is not at that distance, it's going to produce blurry image. Now, this we can say is kind of a constraint placed by the lens. And what we want to do is we want to explore ways so that we can make this camera way thinner and be beyond the constraint placed by lenses. Now, just briefly, why do we want thinner and miniaturized cameras? There's actually a ton of reasons for that. There are reasons where you want to put it on micro drones for surveillance and rescue. There are many places where you want to put it on wearables so that you can have continuous bioinformation about your body. And also there are other places where you can put such miniaturized cameras such as endoscope, observing the neural activity of brain as an implantable and even as an ingestible camera. So with all these applications, one of the driving forces is we need to miniaturize these cameras so that we can make it usable for all these applications. Now, lenses, the design of lensless have acknowledged this necessity, which is miniaturization. And over the years, with different technologies, we are able to reduce the size of the camera using, in the beginning, digital sensors, compound optics, and now plastic optics. But still, with few millimeters, 5 to 7 millimeters of your smartphone camera, making it thinner is going to affect how the imaging capability is going to be. So in that case, what we are going to introduce is to go beyond such lensing optics, which tries to focus light. What we want to do is we want to replace the lens with a thin optical mask that's not going to do focusing, but rather it's going to map a point in the scene to a 2D pattern, a larger pattern. Instead of a point to a point, it's going to be a point to a larger pattern. What we call this pattern is like a point spread function because it's a response to a point. And in this way, we don't need to continue having this focusing distance as our thickness constraint. We can go smaller than the focusing distance and achieve smaller thickness of cameras. But doing so means we need additional requirements. Case in point, when we see the sensor measurement, it's not like an image that we can process. We cannot look at this measurements and say, oh, I see a Santa Claus there. Instead, we need an additional computational algorithm to go back to the image. So in essence, a lensless camera is a fully computational camera. That is, it reduces the thickness by replacing the lens, and it relies on computation to do the focusing, or basically to recover back the image. Now, with such a camera, it doesn't mean that we lose information. We actually retain information, and we are able to reconstruct video, able to do face detection over the reconstructed image. Basically, we are still able to capture all the information that is important in an image, but achieve it using thinner cameras. So just to combine it with the advances over the years, computational cameras are allowing us to go way thinner in camera and use computation to reconstruct images. Now, I just want to take a slight detour so that I acknowledge the work done before the type of cameras I'm going to talk about. So between 2007 and 2015, there was a different kind of lensless imaging that was trending. That is an illumination encoded lensless, in which case the illumination is behind the scene. And the way the encoding is done is how the objects interact with the illumination. In the talk I'm going to give today, I'm going to show the recent advances in lensless imaging, which is mask encoded lensless imaging, where it doesn't place any constraint on where the illumination is. We expect ambient illumination, and then the scene reflects the ambient illumination, just like in a normal camera sense. And that's what we capture and reconstruct. Now, in this lensless imaging setup of a mask encoded lensless imaging, we can break down the anatomy into two parts. One is the camera itself, the optics, the sensor, the design of the distances. So that is one part of the lensless imaging. And the other part of the lensless imaging is the computational algorithm that we are going to use to recover back the reconstruction. Now, when we come to the camera, so there is a couple of anatomy within it, which is there is the mask that's going to encode the incoming light. There's a sensor that's going to capture the intensity image. And then the design parameters are the thickness, which is the distance between the mask and the sensor. And the other thing is what is the response of the mask, what we call the point spread function. So over the next few slides, we are going to go over the lensless anatomy. But briefly, I'm going to mention the computational algorithms used. There are different versions of algorithms that have been used. There can be a single step solution, usually very fast, but can have lesser quality. Then there is iterative convex optimization, which produces really good images, but takes a long time to run. And finally, there is, of course, the machine learning data-driven approach of feed-forward neural network, which is both fast and is able to produce really high quality reconstruction. So over the next few minutes, I'm going to focus on the anatomy of the lensless camera, which is the mask and the sensor. Now, many masks have been explored over the years, over various works. There is amplitude mask, which is basically there's incoming light and it's going to modulate by allowing and blocking light at different points. Then there is the, and in case of amplitude mask, allowing and blocking light that can cause either shadows or using, it can also be modeled using diffraction to produce specific patterns. Here is an example from a paper that used Fresnel zone apertures. Another type of mask is phase grating. Definitely going from amplitude mask onwards, amplitude mask is going to block light, which means there's going to be less light throughput. The next three types of masks are going to allow all the light to go through, and so having better light efficiency. In case of phase gratings, the phase delay or the retardation of light is only either 0 or pi. So phase modulation is either 0 or pi. Then there is diffuser, which has a statistical distribution of phase retardation and can produce phase delays from 0 to 2 pi with a rapid. And finally, there is a phase mask, direct designing phase mask, which produces phase modulation at discrete phase steps. So you can choose what is the step size you want based on fabrication, and then you can do phase modulation of light at those steps from 0 to 2 pi discretized. And below, I'm basically showing an example of amplitude mask, an example of phase gratings, an example height profile of diffuser cam, and an example phase mask being used. So just to compare, amplitude mask being easy to fabricate actually blocks light, but it does have its advantages over beyond visible, which we'll touch upon briefly. And the other three types of mask are completely light efficient. It allows all the light to go through and is able to produce images. Now, as a case study, let's look at a specific example of lensless camera, which was developed by us and published in 2020. We call FlatCam, which is a face mask designed lensless camera. In this case, the mask is a face mask. It modulates the phase of the incoming light. The sensor is a normal CMOS sensor. The thickness is less than 2 millimeter, coming at the thickness constraint, able to do much less than 7 or 5 to 7 millimeter thicknesses, which are in your smartphone. And in this case, we can look at how the fabricated face mask looks like. It's basically, we can think of at different heights on glass, allowing for different phase retardation of light. Here's the face mask profile, and here is the point spread function that we capture using the face mask. And this is designed such that it produces as higher quality a reconstruction. Now, in the next few slides, we are going to use convex optimization based computational algorithm. In this case, it's a single step reconstruction. We can see that the captures don't are muddled or multiplexed, which we can't interpret. By reconstruction, we are able to reconstruct. This particular lensless camera also has a three-dimensional response to the scene, which is if it's close enough, the point spread function of the camera actually changes in size or magnification. And we can plot the correlation of all these point spread function over depths. And we can see a particular trend which we can exploit. In this case, when we look at the correlation between point spread functions at medium level depth, we can see that the correlation basically have a broader width, which means we can't directly detect depth probably, but we can actually do refocusing. So here is an example of refocusing at 3 different depths. We capture a single image, but then computationally refocus at the front, the middle, and the back. So this is refocusing. If we get even closer, we can see that the point spread function over depth, its correlation decays really fast, which means now we can exploit that to reconstruct 3-dimensional information. So in this case, we take a single capture of the scene. The scene is a text light at a slanted, written on a slanted plane. And then using an iterative convex optimization, we are able to reconstruct the image, the 3D information. So let's quickly talk about the theoretical resolution characterization of any lensless camera. It can actually be intuitively said that a resolvable feature is having a width such that its translation of point spread function on the sensor is 1 pixel pitch. Now, this is a theoretical resolution, and we always try to reach the theoretical resolution. So in that sense, a resolvable feature can be calculated in a theoretical sense as sensor to mask distance divided by the scene distance times pixel pitch. And using FlatCam, we are able to match this theoretical resolution, and we have done a USAF target characterization. The other thing about lensless camera is like the field of view. The field of view of a lensless camera is actually very large, and it's limited by the angular response of the pixels. That is, what is the pixels response over different angles, and this theoretically should be the field of view of the sensor. However, in practice, our best reconstructions is in the center, and as we go towards the edge of the field of view due to degradation in the point spread function, as shown by this plot from DiffusiCam, that the quality of reconstruction starts to degrade in the slightly outside field of view. But one thing to take away from this is every pixel actually encodes every point in the scene. That is, every sensor pixel is seeing almost the entire scene. And this was actually exploited for doing a single image to video reconstruction. This work from Berkeley, they basically capture a single capture from rolling shutter and are able to reconstruct the entire video based on a single capture. The same idea was exploited also for spectral imaging. Again, the spectral sensor, since each pixel sees the entire scene, we can use computational methods to reconstruct multispectral images or hyperspectral images from a single measurement. Keeping on the same note as spectral, lensless allows you to go beyond visible light imaging without having expensive optics. In this work, they showed long wave infrared imaging or thermal imaging using an amplitude type mask. So showing this gives the advantage of lensless to also be used beyond visible light without a huge increase in cost of the optics. Okay, so we talked about the lensless camera side. Now let's talk about computational algorithm side, specifically the feed-forward neural network algorithms. So these algorithms are neural network or convolutional neural network based systems, which is able to take a measurement and produce really high quality reconstructions. And most of the works related to this can be broken down into 2 parts. One part which uses the camera model and maps this highly multiplexed blurry image to an intermediate result. And the second part takes this intermediate result and enhances it to produce higher quality perceptual images. And the training data can be experimentally captured by using monitor display with the camera. So you get measurement and the ground truth. Here are two works which have different ways to implement the camera model into the network. In FlatNet, in the top case, we incorporate the camera model, either it's separable model or non-separable or convolutional model directly, but we learn the parameters of that model. The other alternate approach that was explored was not learning the camera parameters, but using unrolled layers of iterative algorithms and optimizing the parameters of the unrolled layers. And these are two ways to incorporate the camera model, which produces the intermediate and is able to then use a perceptual enhancement network to reconstruct a higher quality images. Here is an example of showing reconstruction quality. If we simply do simple least squares reconstruction, we get the middle, but then using the feed-forward network, we are able to get highly perceptual quality images. Here is another comparison. As you can see, the measurements are pretty blurry. With single-step Tikhonov solutions are pretty noisy and can lose the details. But using the two data-driven approaches, we are able to have high-fidelity reconstruction images. So that's with the data-driven approach. Let's quickly go through emerging applications and future applications of lensless imaging. One of the things lensless imaging is going to have big benefits is in microscopy. In this particular case, in flat scope, we showed almost 4 times the bigger field of view while maintaining the same resolution. Another case is we have shown in vivo imaging of brain neuron imaging. Here is the brain video with different neurons and the blood vessels seen. And here's work by Berkeley where they imaged the larval zebrafish expressing GCAM. So there is a lot of emerging applications in microscopy, and that's continuing. Future applications, there is upcoming devices that can do modulation at high speed. Now, can we incorporate that for lensless imaging? So on the left case, this algorithm was designed as a depth-aware system so that we can directly do refocusing. In the other case, they explored reconfigurable nanoparticles that change patterns based on electric field to do programmable reconstruction. And one other future application, which is a hard problem today, is designing it for privacy. We know that the measurements are blurry, but then can be exploited for privacy. But there are challenges in which we need to add loss of information or bottlenecks so that we can achieve privacy. And this is an ongoing future direction. To conclude, a ton of impact. Yeah.
Little over time, so.
Yeah, I'm almost done. This is the last slide. So there's a ton of impact, and I hope I motivated you regarding the lensless imaging, and thank you for listening.
Okay, thank you very much, Vivek. I think we extended a little bit of the allotted time, so we won't really have time for QA, but maybe I'll just ask one lightning quick question here. A really exciting culmination of your work, Vivek. Great to see. I can even see from the images you captured that your own hairstyle has changed over the years. You know, where do you think, what do you think is the next big milestone in lensless? Is it going to be commercialization to industry, or do you think the next milestone will come from continuing the academic research? Obviously, it's a balance of both, but what are you most personally excited about if you had to pick one?
So I think there is good amount of work that shows promise for commercialization. There are challenges, of course, but I think those challenges are getting solved as we go. So I think one of the next exciting things is to introduce this into commercial applications where you can have in-display cameras and many other places where this can directly get integrated to commercial products.
Thank you very much. And I highly encourage you to visit Vivek's website and get to know him better. Thank you, Vivek.
Thank you.
Great. Welcome to the last invited talk, and definitely please watch the invited talk and then attend the poster session right after on Galilee. But this invited talk is from Sheila Seidel. She's from Boston University, and she'll be presenting on non-line of sight imaging. Sheila, please take it away.
Okay, hi, I'm Sheila Seidel, and I'm going to talk about the vertical edge occluder as a powerful tool for forming non-line of sight images. So I just want to open with asking everyone a question. If you think we should be able to form a reconstruction of what's going on around this corner using a photograph of what's in this green box. And this is exactly the kind of imaging that's enabled by the vertical edge occluder. So the ability to form non-line of sight images could be really useful in a lot of different applications. This includes autonomous vehicle navigation or robotic navigation, search and rescue applications. And in the common scenario where the occlusion is a wall, light from the hidden side is cast onto the floor on the visible side, forming what we call a penumbra. And in this work, we're interested with taking photographs of this region and forming reconstructions of the hidden side. So what gives rise to the penumbra? So basically, I'm showing a bird's eye view of our scenario. If you put a point source in the hidden region and draw a dotted line between that target and the edge, you can see that everything to the right of the dotted line is illuminated by the point target, but everything to the left is actually occluded by the wall. And we can put another point target in there and see that this edge gives rise to these fan-like penumbra patterns. The first work to really exploit these penumbrae was by Baumann et al. And here they're forming 1D reconstructions where that one dimension is azimuthal angle around the corner of hidden scenery in motion from a video sequence. And it's moving parts of the hidden scene because they are performing background subtraction. In our own subsequent work, we form 1D reconstructions of moving and non-moving hidden scenery because we're not performing background subtraction. And we do that using a single snapshot without assuming a uniform floor albedo. In this talk, I'm going to focus on 2D scene reconstruction from a single photograph. So our new reconstruction dimension is range into the hidden scene. First, I'm going to talk about our prior work in relevant background. Then I'm going to discuss our 2D non-line of sight estimation from a single photograph. And then I'm going to discuss edge-resolved active imaging systems that are now happening. So many of you may be familiar with the original corner camera work of Katie Baumann. And what was achieved here was 1D reconstruction of hidden scenery in motion, and they're using background subtraction. So you can see the setup here. They have this tripod looking at a region on the floor of the visible side. And then on the hidden side, there's people walking around wearing different colored clothing. And in these reconstructions, you can see each column of the image is a single 1D reconstruction of hidden scenery in motion. And so here's the one person scenario with the person in the blue shirt. And then there's a blue and red shirt scenario in the bottom right. In our own subsequent work, we demonstrate 1D reconstruction of the entire hidden scene from a single photograph without assuming a uniform albedo. And we show in our paper that even with background subtraction, Baumann's algorithm suffers performance degradation when the floor albedo is not uniform. And in our own static scenario where we're not performing background subtraction, it's even more important to consider non-uniform albedo in our forward model. So in our forward model, you can see we're writing our measurements in terms of F, a vector of unknown floor albedo, which we're going to estimate, and V, our 1D hidden scene as a function of azimuthal angle. And then we write our optimization problem in this way, where we have a data fidelity term. And then in this work, we rely heavily on regularizers for the scene and the floor albedo. So just to give you a sense for what this looks like, here's a line of sight view of the hidden scene. And we take a measurement that looks like this on a very patterned, non-uniform floor and are able to form a reconstruction that looks like this. You can see in the plot, we're showing our 3 different color channels and then the composite RGB image on top, and there's very close match there. Another very relevant work is by Saunders, Murray, Bruce, and Boyal. And here they have an occluder of known size and shape. And it's 2D, and they're using that to form 2D reconstructions of the hidden scene. So here is their camera, and they're looking at this visible wall and trying to recover this hidden scene. And with a measurement that looks like this, they're able to form reconstructions that look like this. So there's very close match there as well. And in this work, they also introduced the concept of computational field of view. And so they basically show that the regions of the hidden scene that are best conditioned for recovery are those from which projections of multiple occluder edges fall. So in our work, we're using this 1D vertical edge occluder. And our question is, with this 1D occluder, are we fundamentally limited to 1D reconstruction? And so what I'm going to show in this talk is that we are not fundamentally limited, although range is certainly challenging to estimate. Okay, so in this work, we start with a point target analysis to better understand the merit of this edge occluder and the challenge for 2D reconstruction. So we parameterize the hidden side of our scene in cylindrical coordinates. We have a range from the corner and azimuthal angle alpha. Z is the height measured out of the slide. And then our approach is to derive the Kramer-Rao bound for localizing a point target at location rho s azimuthal angle phi s and at 0 height. And so I'm going to show you some sample results from some simple scenarios. And in all results that I'm going to show, I'm also going to compare to the case where we have no edge occluder, just so we can understand the benefit brought by that edge. So here's a bird's eye view of a scene, and you can see a point target at range rho and azimuthal angle alpha. And with no edge in place, you can take a photograph here on the floor, and it might look something like this, where you can see very subtle gradations in the measurement due to the radial fall off of that target. And then we can use our Kramer-Rao bound tools to derive uncertainty regions around this point target location and other point target locations on a polar grid. And so here's what that looks like. And you can just see that it's equally difficult to estimate range and angle here. And also, as you would expect, it's more challenging to localize a target as you get further away from the measurement. So if we put our edge in place, now our measurement looks something like this due to that yellow point target. And you can see we have that penumbra in our measurement, and the corresponding uncertainty regions actually look like this. So you can see now, even though I promised these are bubbles, they actually look like lines because the angular uncertainty is so low due to the resolving power of that vertical edge. And I also just want to point out that as you move deeper into the scene in angle, so like over here, the range uncertainty is actually greater with the edge in place. And that's because if you look at that measurement in the bottom left, you can see there's fewer pixels actually affected by that point target. And so it's more difficult to use the radial fall off patterns to discern the target range. The story actually changes a little bit when we have a more complicated scene with multiple targets. And here, the edge occluder separates light from different targets, making range easier to estimate when we have our edge in place. So here, we're going to fix one target at a range of 1.5 meters and at an azimuth of pi over 4. And then our second target we'll fix at 1 meter, and this one will sweep an azimuthal angle phi 2. And on the right, I'm showing the Kramer-Rao bound for these two targets, unknown ranges. And the top two curves are when we have no edge in place. And you can see, as predicted by the last slide, that it's more difficult to localize the further target. And also that both of these curves are much higher. The uncertainty is higher when there's no edge than when there is an edge now. And that's true at all angles except for when these targets are at the same azimuthal angle. And the reason for this is if you look at the bottom left, there's actually now a swath of pixels affected exclusively by target 2. And so it makes it easier to tease out the radial fall-off patterns from these different targets and estimate their range. So you might have looked at the last few slides and thought, you know what, angle is very easy to estimate from this edge, but range is much more challenging. Why are we trying to incorporate range into our forward model? So I'm going to use a toy scenario to try to answer this question. If you look at this simple scenario, we have our occluding wall, a hidden side that's composed of one simple white cylinder, and this is where we're going to collect our measurement. And in a really high SNR scenario, it might look something like this. If we assume that everything is in the far field, here's what our 1D reconstruction looks like. And you can see there is a peak at the angular location of the target, but there's also artifacts at angles where there clearly is no scene content. And then if you look at the residual, there's a lot of undescribed radial fall-off patterns in our measurement. So if we choose to estimate range and incorporated it into our forward model, now we ultimately arrive at an estimate like this with way fewer artifacts, and our residual is much smaller. So we're adding a new reconstruction dimension and improving our 1D reconstruction as well. So for a forward model, we parameterize the hidden side in cylindrical coordinates, like I mentioned before, and for the visible side, we're parameterizing in polar coordinates. And we'll describe the light outgoing LO from floor point P as the sum of incident light on the floor from the visible side and incident light originating from the hidden side. And then we'll multiply it by the albedo at point P, which in this work we do assume is uniform across the observation region. LH is the sum of all light coming from the hidden scene, attenuated by radial falloff. And you can see the d squared in the denominator, where d is the distance along the floor between point P and seen element at range rho and azimuthal angle alpha. And here, SH bar is that 2D plan view that we seek to recover with our algorithm. And you can see we're integrating out across height z. So to further model occlusion in the hidden scene and make this problem more tractable for us, we assume that SH bar is separable in range and azimuthal angle alpha. And so we can write it in this way, where SH alpha is the scene radiosity as a function of angle. And so for a simple scene like this with one target, here's what that might look like. You can see a peak in intensity at the angular location of the target. And then rho H alpha is the scene range as a function of angle. And so now at most we're estimating a single range and intensity per angle. So now we have our continuous forward model, which we've written in terms of this 2D plan view that we seek to recover SH bar. And we can write our discrete forward model. And now, in addition to assuming that SH bar is separable in range and alpha, we're also going to further make this problem easier for ourselves by assuming that the hidden scene is comprised of Q unknown hidden targets. And so under this assumption, SH bar can be described in terms of Q unknown ranges and Q angular extents, and then a 1D radiosity as a function of angle. So for this hidden scene, we've got 2 targets, Q equals 2, and now we're just estimating 2 ranges and 2 angular extents, and we'll have a higher angular resolution reconstruction in V. So our objective function has a data fidelity term. We're also promoting sparsity of the scene in a wavelet basis, and then also positivity of our range and scene estimates. And we minimize this by an alternating method. So here's one measurement scenario and a corresponding result. So you can see we have 2 targets in our hidden scene, the measurement in the bottom left. And in our reconstruction, we have really high angular resolution, sharp boundaries between the different colored regions on the objects, as would be predicted by our CRB. And then we also place the 2 targets correctly with respect to each other in in range. And so if you look at the measurement, maybe you can see where they are in angle, but it's very difficult, if not impossible, to look at that measurement and tease out range with the naked eye. We also recognize that these results have only been tested in a constrained environment. So in this paper, we explore how weak the signal can actually be and how this still works. So here's a high SNR scenario with the hidden scene on the left. And if we add more ambient light, you can see that our range estimate does degrade, but the angle is still very spot on as predicted by our Kramer-Rao bound. So range is fundamentally harder to estimate. So I'm going to change gears now and talk about active edge-resolved imaging systems. And the earliest one of these is the Edge-Resolved Transient Imaging System, or ERTI. And here they're deriving longitudinal resolution from the temporal response of a pulse laser and angular resolution from that vertical edge. So you can see here, they're pulsing a laser at the floor and scanning it in a small arc around the corner. And then a single pixel SPAD is pointed at the pink region on the floor, and that accumulates histograms of photon arrival times. And then if you look here at subsequent scan spots, you're illuminating slightly more of the hidden scene. And so by differencing subsequent histograms, you can start to isolate scene content in a given angular wedge. And so they use reversible jump Markov chain Monte Carlo algorithms on the measured data to reconstruct reconstructions like this. So I'm also currently working on a new edge-resolved active system, which we're calling motion-enhanced edge-resolved transient imaging. And so actually, due to the longer scan time of ERTI, that system's liable to miss motion in the hidden scene. And this new proposed system will hopefully produce robust reconstructions of changes in the hidden scene in real time, and it's designed to work with very high levels of ambient light at low signal counts, which I'll demonstrate for you on the next few slides. So in this configuration, we're now pointing a SPAD array at the floor at the base of this occluding edge. And we're going to pulse a laser on the floor adjacent to that edge. And our goal is to reconstruct hidden scene using changes between measurement frames. So here's a side view of the hidden scene. And in our measurement, we're going to have rates due to just the stationary background and scenery that's shown in yellow here. But if before our measurement frame, somebody enters the scene or an object moves in to the hidden region, we're now going to have rates due to the introduction of the foreground objects. And actually, in addition to that, because of occlusion within the hidden scene, now we're going to have a rate reduction due to the region in the background that's occluded by that new green facet. So our reconstruction algorithm is seeking to reconstruct and track objects in motion, and also reconstruct this blue region and paint in the background behind where motion is occurring in the hidden scene. So here's what that'll look like as someone enters. We'll find their location and also describe the background behind them and slowly paint a picture of the hidden scene. So I'm going to show a very early proof of concept here. Here's our synthetic scenario for one frame. We've got the walls in the background, and this foreground object has just entered, blocking this region in the background. And we're going to try to reconstruct both the foreground and background regions. And to give you a sense for the measurement rates that we can handle here, I'm showing the rates at a few different camera pixels here due to that foreground object. And you can see we peak out at 6 photons per pixel. And then the background rates in that region on the background are even weaker at less than a photon per pixel. And here's what our measurement histograms look like, very noisy. We've got counts due to the background walls, the small signal, and we're also simulating a very high ambient light level here of 10 photons. Okay, so using this very noisy and challenging synthetic data, we can test our proposed reconstruction algorithm. So our first step is to apply passive 1D techniques to determine the angular location of motion in the hidden scene using the techniques I talked about earlier in this talk. Our second step is to use Markov chain Monte Carlo methods to estimate the parameters that describe the foreground and background regions that have changed. And the first step here is first we estimate our foreground object. And you can see our algorithm arrives at a very close match there. And then we also estimate the background. And the same thing happens here. Oops, I just ran it again. And that's despite the very low signal and very high ambient light. Okay, so in conclusion, I've discussed our single snapshot passive edge resolved imaging work. And we had our 1D recovery of stationary and moving hidden scenery without assuming that the floor is uniform. And then I discussed our 2D reconstruction work. This included our point target analysis to understand the challenge and feasibility of this kind of reconstruction with the edge. And then also I introduced our new forward model, showed you our optimization framework and some recovery results. And then I also just proposed a novel motion-enhanced active edge resolve acquisition strategy. And I showed you a very early proof of concept there with very high ambient light levels. And I want to just finish by pointing out that edges and walls are ubiquitous. And this opens the door for some really exciting non-line of sight imaging systems. And so for those who are interested, you can check out our papers.
Thank you very much for this great talk, Sheila. Really enjoyed it. It's a very nice culmination because looking at your results, it seems like there's a lot of real world translations and kind of demos that can be done in kind of low resource settings, which is kind of unique for some of the talks here. So I read on your website that you're looking at educational programs as part of this research as well. So can you expand a little bit more about how you're going to connect non-line of sight imaging to kind of a younger audience?
Yeah, that's such a good question. And it's something we're really excited about because Katie Bauman's original corner camera, you look at that and it seemed magical. So we're going to try to use some of these results that seem so cool to try to get people excited about STEM. And what we have in mind is twofold. First, there's this box that we're making for kids to kind of build their own edge occluder in the classroom, and they'll be able to take a photograph with their mobile phone and reconstruct a scene that they set up on the hidden side of their box. And then we're also working with some undergrads at BU to work on an app like that will hopefully let people try this out in their own hands on their iPhone.
Wonderful, wonderful. And that's on the educational component. Maybe I think you have a very good visibility on this, given that you've been working on this topic for a number of years. 10 years from now, what is non-line of sight imaging going to look like? Is it going to propagate to mainstream CVPR? Is it Is it going to go into products? What do you think?
I think some of it could definitely go into products. Like Katie Bauman's corner camera is very robust. Some of my single snapshot stuff is a little less robust, but the last active system that I talked about, we're very excited about because we think it could be deployed to very real world scenarios. And there's certainly like a very active need for this with self-driving cars. So I am hoping that some of these systems will find their way into products.
Great. Thank you so much for this talk, Sheila. But before we quickly sign off, let me just mention that the poster link is in the chat. There's a Gavely link that David is going to put in. And there's also going to be one more keynote after the poster session, so do try to stay for that. It'll be a keynote by Paul Debovic. Thank you so much to all the speakers in this session.
Hi, welcome back from the poster session. I am thrilled to announce for our final keynote, we have Paul Debevec. He's a senior staff scientist at Google Research, and he's also an adjunct research professor at the University of Southern California's Institute for Creative Technologies. And creative technologies really gives you a good idea of what his work is all about. He does amazing things at the intersection of cutting edge technology and the arts. So Paul is a computer scientist with multiple Academy Awards because his research on topics like HDR imaging, image-based lighting, and photoreal digital actors has been used to create memorable effects in movies that you have probably seen, like The Matrix, Avatar, Gravity, the new Blade Runner, Benjamin Button, Gemini Man, Spider-Man 2, and Furious 7. You may also know him from his 3D portrait of Barack Obama. So you've probably encountered Paul's work in some form or another, and we're really delighted to have him here today, closing out our workshop by sharing his experience and perspective on the key technologies that make the magic happen. So thank you so much, Paul, for being here. Take it away.
Thank you so much, Emma. It's great to be here at Computational Cameras and Displays. Thanks for making it back for the super cool poster session there. Great work going on. This is a special day. It's not just Father's Day on June 20th. It actually happens to be the 5-year anniversary of when I joined Google, and have previously been full-time for 16 years at the USC Institute for Creative Technologies, where I'm now an adjunct faculty member, and enjoy getting to continue to work with their light stage and their researchers. And this journey to Google actually came about through virtual reality, and in fact through computational imaging. This particular slide that I had as part of a talk at a Stanford workshop on light field imaging ended up being kind of prophetic. The organizers of the Cyan workshop, Joyce Farrell in particular, decided to do a light field imaging session, and it was happening in early 2015, kind of at the very beginning of the crazed hype about virtual reality. And so I gave a talk about, you know, a number of light field related stuff that I'd done over the years, but it just didn't feel like I could make a complete talk without somehow saying, like, well, how do light fields have something to do with virtual reality? Because everyone's talking about virtual reality right now. And so I worked with Jay Bush in my group, our technical artist, to put together this diagram of what I thought would be a good, you know, virtual reality camera if you wanted to shoot light field video that you would watch in a VR headset. And the idea of shooting light field video instead of just regular 360 video or 360 stereo video is that, you know, you should be able to move your head around a little bit and see the perspective on the scene change as you move your head forward and back and left and right and up and down. Not just so that it's like a little bit more immersive, but so that, you know, the natural amount that we're just always moving our head around anyway, and we can't really avoid, even if you just like turn your head to the side, your eyeballs translate over there too. And if you don't see the 3D parallax effects that you should, it's a strange cue. It makes a lot of people, including me, feel sick to their stomach. So if we wanted VR to, like, you know, really take off, then how can we do that? Well, I thought, well, you know what we should do? We should just build an array of cameras, capture all the rays of light coming into this, you know, I don't know, almost 1 meter sphere that you might want to look at with your light field, come up with new view interpolation algorithms and new ways of rendering this in real time. And as you move around, you could watch light field video and it would be fantastic. And I kind of hinted at the fact that this was probably going to be about 5 years of work to really figure it all out. Based on this, I kind of got contacted by, you know, Google's VR group and said they'd be kind of interested in doing this kind of stuff. And in June of 2016, I found myself working at Google with, in fact, Jay Bush and 2 other members of my team from USC, and finding that we had marching orders to do light field stuff. And we wanted to get started quickly. This looked like a little bit of a system to engineer. So I thought I'd show some of the very early experiments that we did. And one of them was based on this thing I'd seen in the Boston airport, in Logan Airport, going through, where it's just kind of an array of mirrors that happen to converge in a way that if you stand in just the right spot and take a selfie, you get a legitimate light field of yourself with a single camera. It's not a very wide field of view because it's just like, you know, almost an orthographic view you get standing so far away from here. But I thought that this was nice because if you just shot video of this, you'd get light field video and you wouldn't have to worry about hooking up a bunch of cameras and synchronizing them, which is a big ordeal. So I found that you can actually get these mirrors that are slightly concave. And if you look at them from a distance, you see about a 45-degree field of view. You get them for about $2 each. So we actually 3D printed out these brackets that could angle the mirrors in just a little bit so that they'd reconverge on a subject. And we thought we'd shoot our first light field video this way. And since the Los Angeles YouTube space was just across the street from us, working at Google down here in Los Angeles, they had done something kind of fun for the 2016 election, which is they had taken one of their sound stages and they just hired some set designers to build a replica of the Oval Office so that any YouTube stars who wanted to broadcast live from the Oval Office could do that for their YouTube videos. And so we got to take over the Oval Office for a bit. This is Graham Fife, who also came over with us from USC. And we thought it would be fun to shoot some like a light field presidential address there. So you can see the mirror array over here at the side. And this is actually a red digital cinema camera that I think it was at least 6K, maybe it was 8K resolution, but the idea was that even though these images are small, you'd still get pretty good resolution with the red camera. So there's a little video of actually kind of setting that up and using it. I'm pressing record, and then Graham's getting ready to address light field there. Graham's actually
we're recording, we're stabilized, and go ahead and shoot.
A great change is at hand, and our task, our obligation, is to make that revolution, that change, peaceful and constructive.
So in an earlier clip, he called himself the Prime Minister. I had to kind of work with him on that a little bit, but we got some light field video, and it was kind of fun. We worked on kind of processing it. We just had very basic view interpolation algorithms back then. It didn't quite get to the point where the resolution really impressed the what we were hoping for in terms of what we could do with light field video. So we kind of kept that on the shelf for a bit. And we realized if we wanted to get somewhat higher resolution, maybe we could focus on still scenes and just move a single camera around. So this was another little test that we did in the Oval Office with just kind of a single fisheye view. This is a Kodak Pix Pro camera. And we just rotated it around. Every time it rotated around, that tripod has a little crank on it. I'd sit under the tripod and lower it by about 5 centimeters, and we would get these cylindrical light fields. So that gave us some light field data to start playing with as early as 2016. And based on some of those experiments, we kind of upped our game a little bit and finally built a camera that we actually really did use in production that we called the GoPro Oddity rig. This was based on a Jump Odyssey 360 stereo camera that folks in the Seattle team had built. And they had actually worked with GoPro to put a very tight synchronization mechanism between all of the cameras for shooting 360 video. And what we did is we unwrapped these GoPros into an arc and put a motor on him. The fourth person who had joined Shuming Yu over from USC built the drivetrain for the mechanics here. Jay Bush did a lot of the laser cutting and 3D printing. In about 30 seconds, this thing would rotate around. Here's a long exposure photo, and you would get your spherical light field pretty quickly that way. And that was just fast enough that we could actually record light fields, all throughout a space. We did Space Shuttle Discovery at the Smithsonian Museum. We could even do some light field portraits of people. These are some local artists who have decorated their house with a lot of tile mosaic. And we actually got a nice portrait of them. And using some work that we published at SIGGRAPH Asia 2018, we are able to do light field rendering. We compute like a depth map for each one of these approximately 1,000 views that we have on the sphere. And then there's kind of like a big advanced bilinear view-dependent texture mapping of the image data onto this local geometry that you have per view. And it produces quite high quality light field reconstructions. It also gets things like, reflections, for example. So if you see the window back here, there's pretty convincing kind of rough specular reflections that you would expect to see as you move back and forth in this light field reconstruction. And if you have access to a VR headset that connects to a computer, I highly recommend checking this out for yourself on your Vive or your Oculus Rift or your Windows Mixed Reality. For free, you can download this app called Welcome to Light Fields on Steam VR, and it will take you through about 36 light field static scenes, including that space shuttle tour, some architectural tours, and you'll get to meet Sherry and Gonzalo and feel like you're sitting right across from them. And that taught us a lot about what it takes to produce compelling light field content in terms of like how close objects should be able to come to you, what field of view you need, what kind of image resolution you need. And we took all of that into consideration as we continued to move our work further forward to get to light field video, which was really the big prize we were after. And one of the things that we realized is that encoding all of the individual image streams and their computed depth maps, it was going to be too much data to encode. And we had to figure out a way to create something that was more of a consistent distillation of one scene representation that brought in the data from all the cameras and didn't try to stream and represent all of that in a compressed form as it goes to rendering. And that became the basis of what we called our deep view video pipeline. This is based on a scene representation called multiplane images, which is some work led by John Flynn in our group, that represents the scene around you as a set of RGB alpha planes. And it uses deep learning to figure out what set of RGB alpha planes and what pixel colors to put on them will represent all of the original input views and also be very likely to produce correct view interpolations for what you would have seen in between the cameras to generate those rays of the light field. So there's a website that you can see there. There'll be a QR code for that in a little bit, where you can see some of the video that we've produced. And to apply it to virtual reality, where we wanted at least 180 degrees field of view, we adapt this through some work that some other folks, including Michael Broxton, who came on, our first author, to be able to put it onto spherical shells so that these planes can now curve and surround you with the video. If you go to that site, you can also just see this stuff live in your web browser because it's compact enough to do that. And if we look at this video, then we should be able to see an example here of, this is our friend Libor, who has a neat workshop, and we're just virtually moving the viewpoint around. This is our artist in residence, Alexa Mead, that we worked with, painting a person. This is a nice volumetric effect that Libor set off for him in his garage, which was kind of a target-rich environment for cool things to look at. And you can see we can move the camera viewpoint around pretty convincingly for this about 1 meter viewing volume. Here's Alexa doing some painting in the Playa Vista Google office. She liked the depth maps that we were computing, so she made a whole art installation that you can immerse yourself in that's based on her interpretation of our depth maps and also their stereo reconstruction artifacts, which she was a particular fan of. This is our program manager, Peter Denny, making friends with a horse. This is one of our technical videographer collaborators, Matthew Duvall, playing with his dog. And there's quite a bit of this stuff here that you can see in the VR demos. Let's go a little bit forward. We'll take a look at the camera array. So we were very lucky that one of the competitors to GoPro called Y-I, they came up with one version of their 4K camera that could take a sync signal in. So you could start them all by pressing one record button. And we made this like thin acrylic hemisphere that's about 80, 90 centimeters in diameter. We cut holes in it and we attached a whole bunch of these Yi 4K cameras all wired up with their micro USB cable. Unfortunately, they take a hard to find version of the micro USB that has a 6th pin for sync. They didn't keep completely compatible with that. But we were able to put that together. And when we record, we get these 46 synchronized videos. And the goal of our CNN is to turn it into this multi-plane image, or actually multi-sphere image, so that if you stack these front to back, it reconstructs the scene, including things flying through with sparks, good alpha edges and occlusions, and a bit of reconstruction of specular reflections. Even though the representation doesn't explicitly represent specular reflections, it can kind of fake those by putting little bright spots in the scene behind the surfaces that they're supposed to be reflecting off of, and making those surfaces a little bit transparent. So you might notice some specularities in some of these scenes. And then this last bit of the video that we've just seen here, I'll run this again, actually takes it down. You can see that was like about 120 layers to get this kind of quality. That was too much for us to compress and stream into a reasonable file format. So instead, we run another post-processing algorithm that tries to group surfaces in the scenes into a total of 16 depth-mapped, texture-mapped layers. And we found that 16 layers will kind of compress into a texture atlas movie that we can do okay as like a 4K by 4K map. And it still represents the scene pretty effectively. So we're going to see a comparison here between using this layered mesh representation and the original multi-sphere image. That's like 16 layers with depth versus 128 layers with just fixed depth. And this is a nice visualization that Matthew did for showing how it turns into a texture atlas. So basically our light field video is like this texture atlas movie. There's also an alpha channel that goes along with this too that looks similar to black and white. And then some rough 3D geometry that's compressed with polygons and vertices. And that produced a pretty good light field video experience. And if you go to our Deep View video site, which I'll show the link for one more time, there is a downloadable version of these videos that you can watch in a VR headset on your PC if it's hooked up. So we've continued to try to improve what we're doing in this area. And, you know, based on the success of our, we call that the Sentinel rig because, you know, it kind of like had lots of eyes and wires coming off the back. We thought we should go a little bit higher quality with things that we might have a bit more success with. And the poster that I just presented in the poster session talks about our latest light field camera called Brutus. And the design goals for Brutus were to shoot hemispherical light field video with somewhat higher resolution, somewhat higher reliability, and certainly better image quality so that, for example, we could set all the cameras to the same amount of exposure and not just have them all be on auto exposure, which is kind of problematic for a lot of immersive scenes. We still wanted to be able to capture subjects from 1 meter to infinity, to have people move their head around a meter in the scene. And we're willing to spend like maybe $50,000 on components for this one here. So up by a factor of 10, but not by a factor of 100 from our previous one. And the cameras that we found were Zcam E2s. It's kind of like a compact digital cinema camera. They're almost 4K by 3K resolution. They'll record at 60 frames per second. They have some nice video codecs that have logarithmic compression or 10-bit or 12-bit, so you can get better dynamic range. We put a whole bunch of lenses on them that were 190 degrees field of view each, so you basically see everything that's in front of the hemisphere. We went with another acrylic hemisphere. We had a thicker one because we had heavier cameras, and we arranged them basically like in a little ring of 3 in the middle, surrounded by a ring of 9, surrounded by a ring of 12. And you know, even the cameras on that 12 ring there still look straightforward because they have a 190 degree field of view on the lenses. And then Jay came up with these very nice custom 3D prints to hold the cameras onto the structure. And they were all attached to the dome using a custom jig that she built to drill into the dome and get them in the right places. And the dome itself was reinforced with some aluminum struts so that it was solid enough. But the half-inch thick acrylic was pretty solid. And what we've been doing during the pandemic is actually recording some light field video content, some immersive light field video, mostly friends of mine in my backyard. And this includes my friend Andrew, who plays bagpipes. He actually serenaded people in Santa Monica every evening during the pandemic and got written up in newspapers about that. He did a special concert for us. We interviewed our artist in residence, Alexa Mead, actually at her apartment, which is beautifully decorated with lots of colorful materials and different reflectance properties and rainbows streaming through prisms in the afternoon. So we captured that and interviewed her about her work. My friend Xishuan Yang played the Chinese erhu violin for us. And two actor friends of mine, Derek and Amanda, actually custom wrote a little comedy sketch specifically for light field enjoyment. And we're currently working on processing this data, and we also hope, like some of our other data that's available on our Deep View video site there's the link, there's a QR code for that. You can currently download some data with our Sentinel rig. Watch this space. We have hopes to be able to release some of these experiences and some of the high quality light field data to go along with that. So that's been one of the big threads of work that I've been involved in Google for the last 5 years, but there have been others. They also involve lighting, but not specifically virtual reality. And another big interest at Google has been augmented reality, including things that you can see in the AR Core API that you have with the Pixel phones and Android phones. And when we think of augmented reality, a lot of people were kind of introduced to its possibilities through Pokemon Go, which is sort of fun. It kind of rendered these little Pokemons onto your video feed, but I don't think it was really fooling anyone that the Pokemons were really there. Certainly the camera tracking was one issue, but another thing was lighting the Pokemons. Like, if you're going to put a Pokemon into this park, it should look lit like it's lit by the light of the park. And, you know, the bar has been raised considerably higher than that from kind of visual effects that we see in movies with image-based lighting technology. Here's a rendering from the recent Pokemon movie, and you can see they're much better integrated into this street scene than what we're used to, and through augmented reality. And the reason for that is that, you know, visual effects artists actually captured a high dynamic range image of the scene that they're being rendered into, and they lit the characters with the lighting that was actually there in the scene. This is something that we started having fun with in our research group even back in the 1990s, when I was going around UC Berkeley and capturing the light of the eucalyptus grove, or on my trip to go visit Stanford's digital Michelangelo project, I took a couple of photos in St. Peter's Basilica in high dynamic range to capture its lighting and to try to use that for a film that we made. And you can get some very convincing results of showing what those objects look like in those scenes. Doing that on a cell phone is, of course, going to be a little bit more challenging because you have a lot less information to work with. You don't have your personal visual effects crew going out there with mirrored spheres or fisheye lenses or HDR cameras to capture the lighting. You just have the video feed, which is low dynamic range, and it only covers about 7% of the field of view of the lighting directions around, and not even arguably the most important lighting directions that you need to capture. So this limited field of view of the background is hard to figure out what the lighting in the scene is. And if you don't have the full dynamic range of the light, you'll get a very incorrect result as to what an object would look like. This is this rocket ship lit by a low dynamic range image, a clipped version of this lighting environment. Here it is lit with the full dynamic range of the lighting, and it's a dramatically different effect. So we thought that since we don't really have all the data we need, we're going to have to kind of fill it in and make it up and make some educated guesses. And that suggested that we should look into a machine learning algorithm. And to give a machine learning algorithm a good chance to do what we needed to do, we thought we needed to record some good training data. And so we built a special custom training data acquisition rig that has a cell phone that's shooting video, but it's holding some little spheres into the bottom of the frame that tell you what the lighting is that goes along with that background. And so you get a lot of footage of images that look like a background plate, and then this little strip at the bottom tells you through the mirror sphere and the diffuse sphere and the matte silver sort of glossy sphere. From that, you can figure out everything you need to know about the full dynamic range of the light, and you still see most of the rear camera image. So this gives you a lot of training that says, if this is the background, then that's the lighting. And you can just send people out. We put 4 of these rigs. We sent them to different offices, inside and outside. We got millions of training frames of lighting all over the place. Here's some of the data that we pulled in. And from that, it is straightforward to those trained in the art to set up as a training for the network here. This is published at CVPR 2019 by Chloe Legendre et al. Called Deep Light. And if you give it a background, it can then infer and imagine what the high dynamic range light probe would have looked like that you should light a scene with. And these are some results with that rocket ship where we didn't actually measure the light. We just took the background plate from the pixel phone and then asked Deep Light to figure out what the lighting is and then render this object into the scene. And it generally looks consistent with the lighting that you would get in the scene. There's another couple of examples you can see. And we're overall pretty happy with that. And that actually shipped as a feature in the ARCore application program interface. So many different AR apps that run on Android phones use this to query the lighting to insert the objects into it. Now, when we were doing this work, we realized that we were actually pretty careful not to have people in the scenes that we were estimating the lighting from. But it certainly begged the question, like, well, if we knew that there's a person in the scene, all human faces are different, but they certainly have some similarities. Maybe if we knew there was a face in the scene, we'd have an even better idea of what the lighting is like. And we wondered, to what extent could we just use somebody's face as the light probe to estimate the HDR lighting? And that became a project that we showed at SIGGRAPH Asia last year, again, led by Chloe Legendre and some of our friends in the augmented perception group here, where we thought that we actually have the perfect way to capture the training data, because at Google, we actually built a light stage. And we had brought in, for actually a different project, about 70 people that were, different ages, genders, skin tones, dressed differently, different hairstyles. We even had people put on hats and make funny expressions and shot them from different angles. And we got a very large data set of diverse people. And for each one of these, we lit them from one light direction at a time in our light stage, 331 lighting directions. They were recorded from a lot of different viewpoints. In this project, we used 6 of them so that we kind of have variability. And even if you're not quite frontal, we still have a good way of estimating the lighting. And these are the photographed reflected spaces images here. So this is 24 out of our 331 lighting directions. And we know from classic image-based relighting that if you've lit a face with every direction light can come from, you can do the forward process of showing what they'd look like under any lighting environment, just through image recombination of scaling the images to the colors and intensities of the lighting coming from that direction, just adding them all up to produce the effect of what, for example, our undergraduate here, HP, would look like lit by the light of Grace Cathedral. And because of this, we can actually generate tons of training data of relit faces that started in our light stage, but we know exactly what we relit them with. So we can tell our network, hey, here's a face. And if you wanted to get the answer right for what's the lighting on the face, that's the light that was actually on that face. So we can generate tons of relit faces. And we also take an image that has like an alpha channel for the face that allows us to composite into the background as well. So these hopefully theoretically look like plausible photos of people lit by the environments that they're being composited into. And then we have, the ground truth in all of these cases of what the lighting really was. So that lets us set up a neural network that you put in a input low dynamic range portrait, and out can come the predicted lighting, and you can look at what the real lighting should have been, create a loss function out of that, and train the network. So let's take a look at some results. These are some input images here Now, these are ones for which we have ground truth. They're not in the wild images yet, but I'll show you those in a second. And we estimated some lighting off of these images. These are other people who we've illuminated with the estimated lighting using forward image-based relighting. And hopefully it looks like, plausibly these two people could be standing next to each other in the same scene, and these two people look like they could be standing next to each other in the same scene. Even better is that since we knew the ground truth lighting that we used to generate these two images on the left, we can look at these images on the right and see what they would really look like if we actually lit them with the correct answer for the lighting. And this made us really happy. It's pretty darn consistent, all the way down to the shading, the color tone, and the specular reflections. Here you can see this is the ground truth lighting here. This is Yunta, who's someone who worked on a lot of the portrait light work at Google. You can see a nice specular reflection in his nose. You can also see a relatively sharp specular reflection in the lighting that was pulled off of this subject's face. And we were pretty happy with this because it seemed like, the fact that we're estimating an entire light probe image, it's not super high resolution, but it has some detail to it. It seems to be like we're doing much better than just estimating like spherical harmonic light off of the face. And we thought we could test that by just lighting the face with the first two, bands of spherical harmonics, the first 9 spherical harmonics in each channel. And you can see if you do that, it's consistent lighting, but it's missing all that specular detail here. Now the nose doesn't have any little shine on it, and people look kind of powdered and maybe not quite as lively as they would. So it's like, okay, we are getting some higher frequency components of the lighting off of folks, which is good news. We can do this on video too. This is one of those algorithms where like, okay, we didn't explicitly try to make it temporally stable, but here's Jay Bush. We're estimating the lighting off of her face, not the sphere that she's holding. The sphere is just to give some reference so that you can see it's kind of consistent with what we're estimating there in the spheres. There's another kind of fun thing. We had like a digital model of this guy, a friend of ours named Andre, modeled by Ian Spriggs. We thought, let's light this digital model of somebody with lighting we pulled off of some in the wild face. So we pulled lighting off of this nice person here. We estimated lighting, and then we thought, let's light our 3D model with that lighting. And yeah, plausibly, maybe they could actually be there in the same scene together. Maybe Andre and this other guy here that we pulled some lighting off of his face could actually plausibly be there in the same scene. And this also could work for augmented reality. Suppose you're trying to make some fun SIGGRAPH balloons float above your head, and you want them lit consistently with the light of the scene. Well, if you can pull that lighting off of your face and then light those balloons with that lighting, then maybe those will look integrated into the scene pretty nicely for them. And lighting on faces, this was a fun project because it addressed like kind of a current concern in augmented reality, but also spoke to a really classical problem we've been working on with light stages for a long time, which is trying to light people correctly with the light of the scenes that we're compositing them into. And the very first concept that we had for what to do with the light stage, we finally got to with the third light stage that we built. This is when we, I guess 20 years ago now, surrounded people with red, green, blue color LEDs to light them literally with the light of RGB light probe maps, and then composite them into a scene. And here, in this case, we use like an infrared compositing system. And we were able to kind of show by mapping that image-based illumination onto the LEDs, lighting the actor with it, and then compositing them into the scene, plausibly showing our friend Emily here what she would look like if she were standing within San Francisco's Grace Cathedral. And one of the projects that I got to continue to work on at USC ICT as an adjunct faculty member was to build this technology out in a full-blown production system in China, actually. A Chinese visual effects company approached us about building a lighting reproduction light stage for them to do visual effects with, and I got to visit that a couple of years ago. And it's an 8-meter stage. It has about 1,000 light sources on it. The lights are actually now are multi-spectral. They have white and amber and cyan LEDs in addition to RGB, so you get better color rendition. Some work that Chloe Legendre did for her PhD thesis showed us how to do that. And here you can see me visiting the stage one day, and visitors, they have this fun trick where they'll composite them into some scene from a Chinese TV show that's already been shot, and they'll make you one of the characters in the TV show, which is kind of fun. So they'll sit you down, they'll direct you. Fortunately, it's a non-speaking role, but you kind of have to react for that. So I'm getting ready to be part of their test, and I'll just show like an image from this here. But this is me added into that scene, and since they can reproduce the light of scenes that have already been shot, they can add new people into videos if they weren't there to be for the original shoot. And it turns out that visual effects problem comes up a lot in TV production and movie production, and they've been adding actors to scenes with correct lighting generated by the light stage for 70 or 80 shots a day for years now, doing a lot of work. This doctor fellow here wasn't originally part of the shoot, and they were able to add him into the scenes because they could reproduce the lighting as accurately as that. This isn't the only professional project that we've kind of worked on lighting reproduction technology with. We had a lot of fun working with the director Alfonso Cuarón with some light stage tests in the R&D phases of a space movie that he made, where they knew they would want actors Sandra Bullock and George Clooney to look like they were actually floating out in space, but in fact they were just being filmed in a studio. And this now is a pretty pioneering use of LED panels to surround actors with image-based lighting, to light them interactively with the light of computer-generated scenes like the space station and the space telescope and the space shuttles and all of that beautiful blue bounce light you get from Earth when you're in space, to light their faces so that when they composite them into the digital astronaut suits, it really looks like Sandra Bullock's out there floating in space, spinning out of control, in genuine peril for all the crazy stuff that happens in this movie, Gravity. And the first time this was actually turned into a large-scale production technique was for a Chinese film called Asura that they started in 2016 and released in 2018. And they put huge LED panels all around the walls of the set. Sometimes they can do an in-camera composite. Sometimes they just put a little bit of blue screen in the camera frustum that they're shooting, so they can do a traditional composite there. But this technique has now kind of taken Hollywood by storm, as what you keep hearing about as virtual production technology. There's even a Disney project called The Mandalorian, which has been shot to a very significant extent in these surrounding LED panel stages. And they can actually produce a lot of visual effects that would be hard to do otherwise without going on location, and do it quicker and more efficiently. And in fact, if you just snap your fingers, then you're on to your next set. Now, one thing that doesn't happen immediately is like the floor. They typically have to build out a little bit of the floor for the actor to stand on. You can see here in China, they built a whole patch of grass and flowers and such for this hillside scene. Because when the part of the environment that the actors are like directly standing on, there needs to be some sort of photometric interaction with that. And LED panels can show you any color, but they don't necessarily react to what would happen if somebody were standing on it. And particularly, they don't tend to receive shadows or reflections. And just for fun, at Google, we were playing around with some LED panels that are designed for you to be able to walk on them. And we had like this kind of like 60 centimeter by 60 centimeter square of them. We put them in the light stage, and we thought, it would be good to actually generate the shadows that you had. I think our future work section of the paper 20 years ago even suggested we should really do like a live 3D scan of your actors and then compute their geometries, shadows that you should have, and put them on the scene. I think getting the lag out of that system can be really hard, but we did have a little bit of fun here with Matt Whalen. We photographed him outside. I kind of put some little squares around so we could know exactly what shape here it was. And the idea was that by shooting him from like 4 angles, we could kind of Photoshop together what the ground looked like around his feet, including the shadows. And then he would just have to stand on those 2 little footprints, and then we could show the shadows that he would get in there. And when you turn the shadows on, it's a lot more convincing that he's standing on the ground. And even more fun, when you reproduce the light, they're using LED lighting of the rest of the scene, the real shadows that you get from that reproduced light are actually consistent with the shadows that are on the ground. So maybe some technology will come out of that. The thing that's particularly future looking though, I think, is that at some point, we won't even really need to light the actors exactly the right way that you need to when you're filming, because, you know, why light it during principal production if you can light it in post-production? And that's a project that using the Google Light Stage we got to explore with a project that we showed at SIGGRAPH Asia 2019 called the Relightables. And this is a collaboration with the Augmented Perception Group and some amazing people there who've worked on depth sensor technology and volumetric capture. And then using our light stage as a computational illumination device, we put time multiplexed illumination into this volumetric capture process in a way that we're not just filming a flat texture map for every frame of their performance, but we're also getting a normal map and to some extent a gloss map for their performance as well. And the way that that works is that we're bouncing between these two lighting conditions that you can see here on the left that are trying to light somebody up like, kind of like a normal map would look. These images, we call them color gradient illumination. And one of them has red light that's bright on the right, and then the lights get dimmer as you go to the left. And green light that's a gradient from top to bottom, and blue light that's a gradient from front to back. And then the other one, shown a 60th of a second later, reverses all that and has the red light go left to right, and the green light go bottom to top, and the blue light go back to front. If the person doesn't move and you just add those two images together, it's white light from everywhere. Your perfect diffuse texture map that you can use for your geometry. But if you align those images, subtract one from the other and divide by the sum, that math actually basically computes the surface orientation at every point, or it computes the centroid of the area of the light stage whose light is most responsible for the radiance going toward your camera. And that's useful as a photometric normal map that you can use for relighting. And the magnitude of that vector actually is acute to surface gloss as well, using some techniques that we did at USC ICT back in the day. So the result is that you can put your colleague Christoph into the light stage. He's got some super nicely engineered depth sensors with infrared noise patterns on them. But you saw those two lighting conditions bouncing across. We get a great geometric reconstruction. And then we can use those measures of gloss and normal and albedo to composite him into some fun environments. This is the cool Google office in Playa Vista. That's actually a place where famed American industrialist Howard Hughes built the Spruce Goose airplane, and now we go there for lunch and coffee. We've added Sergio and Christoph there. This is taking Stephanie, one of our camera engineers, and Jay Bush, our amazing technical artist, and so much more, and Matt Whalen, our camera engineer, and just putting them into some CGI scenes as well. And we can show them from any angle and in any lighting. We probably don't have like 100% perfect like specular reflections, super high resolution frequency, but this is a considerable step up from the kind of volumetric capture that's currently commercially available, and we've been happy to be able to do some projects with this. This technique of relighting, of course, would be even more practical if you didn't have to put somebody in the light stage and magically you could just take a photo of somebody or just take a random selfie and say, I'm not so sure if I like the lighting. Let's see it with some better lighting. And we started to work on that too. And so like the last two little things I've got to show today, one of which is a shipped product, is called Portrait Light. And if you think of that data set that I talked about, where we recorded a bunch of people on the light stage, one light at a time, reflectance fields, different angles, different clothing, different expressions, that actually allows you to train a network with a whole bunch of examples of, here's a random photo in random lighting with the random background that goes with the lighting. Here's what it looks like if you add a bit more key light from this direction, or add a bit more key light from this direction. The first thing you might do to fix a lighting in a photo is to add another light source that either accentuates the key light or fills in some of the fill with illumination. And we trained a network to imagine that based on the subjects we had, so that it can actually work on people it's never seen before and selfies it's never seen before. And this is now a shipping feature in Pixel phones and the Google Photos app called Portrait Light, where after you take your photo, you can go into editing, go for the Portrait Light feature over here, and it gives you virtual control of a light source you can move around your face that will augment the lighting that's already there. You can improve the lighting in your photograph. Tons of people are using this, and it's gotten great feedback so far. It doesn't let you completely start from scratch on the lighting. You can't throw in a different background and start completely anew. But as a little preview of what we'll talk about at SIGGRAPH this year in just a month or two, we worked on just that. We worked on an algorithm called total relighting. And here we're talking about total relighting not only because the lighting that we're going to do is going to allow us to start from scratch and light it absolutely with any HDR map that we want, but also that we're going to replace the background as well. So we have to get a really good alpha channel for this in the wild selfie. And the image here on the left, totally in the wild selfie photo. And we are demonstrating being able to change the lighting pretty much arbitrarily with any HDRI map and any orientation, and then composite it into a new background. So I will leave the co-authors for that project some things to talk about at SIGGRAPH, but it still uses this data set. The real key here is that we're turning our data into, first of all, kind of an unlighting operation where we figure out estimates of the person's unlit appearance of what they would look like under flat lighting and what their normal map would look like and what their gloss map would look like at different roughnesses. And then we train networks to regress to those and then also use those in conjunction with the original photo to predict what the lighting would look like in the new environment. And that brings us to the end of what I have brought to talk about today. Thanks for the opportunity. Let me thank all of the co-authors, some of the people that I've gotten to work with here who help support the work at Google. There's some websites there. And if I left any time for questions, I'm happy to take a couple of questions, otherwise please follow up on email. Thank you very much.
Paul, thank you. That was an incredible body of work. You showed us so much, and I think we have time for just a couple of questions. So one thing that I really loved about all of the things that you showed us was sort of the multiple scales. So we saw these giant light stages, we saw it working on a cell phone camera, we saw you doing things with, little $2 mirrors. And then for your poster, you sort of split the difference really nicely with Brutus, which is like a sort of intermediate trade-off. And I guess I was sort of wondering, there's sort of this idea that we have for most problems of a cost performance space. And it seems like you've really spanned that space really well. But I guess I was wondering, we sort of look for sweet spots in this space, and you've got the perspective sort of from the academic side, from the sort of Google side, but then also maybe from the Hollywood side. Does that space look different from those perspectives?
Yeah, it does, and it varies a lot by project as well. We had an opportunity to potentially work on this TV show called The Game of Thrones at one point, because they have these very large wolves in their story, and they thought that they could do something with like digitizing real wolves in the light stage, and then they could just scale them up by whatever factor, insert them in the scene, relight them, they could do the visual effects. And we did a test to make sure like it wouldn't bother a wolf or a canine to have the flashing lighting. So we did like a little test with them of a German Shepherd to see how they'd react. German Shepherd was fine, and we thought it's like, okay, yeah, let's do it. And it was just the very first season of that show. They didn't have huge budgets yet, and they didn't even really want to spend even $5,000 to capture some wolves. It was like okay, there's no budget. It's like we can't have wolves in our lab for under $5,000. That doesn't make sense. So sometimes Hollywood budgets are small, sometimes they're big. Hollywood definitely doesn't want to spend any more money on anything than they have to. They spend a lot of money on people whose job it is to not spend money on stuff, or to not let anyone else spend any money on anything. At Google, we were very lucky to basically build the light stage of our dreams at Google with the depth sensors, with about 100 cameras on it. We enlarged it so it could be both a body capture system and a face capture system. And it's done great stuff for us. But I don't think we would have felt comfortable just building that as our first version. It helped that the very first light stage had a single light pulled by ropes, and it was, me as a postdoc spending about $1,000 at Home Depot to build that. And there's a saying at Google: solve before you scale. And if there's any maybe a takeaway, there is really a lot of benefit to do the little experiments; those are fun, and then bring it up one notch at a time until it gets to the right solution for the right problem.
Wow, what an amazing and rich history. One other question I had was about sort of the light probes that you use. So I loved the little mock-up you had of just, put 3 spheres on a cell phone camera, and it's just such a beautiful and elegant way to solve this problem. And then the fact that you were able to use a face essentially as a light probe was kind of shocking because, there's self-occlusion, there's subsurface scattering, there's, differences in opacity. It seemed like some of the people you were using were wearing cosmetics, which are almost sort of designed to fool you in that. So is this something where it works because you're just going for something that's sort of plausible looking rather than physically accurate, or is this something where maybe some of those challenges can actually help you? How do you deal with that?
Yeah, it's a good question. The spheres in the cell phone rig, they're just like holiday ornaments, which are super cheap. No one sells diffuse holiday ornaments because those would be boring. So you have to get some Rust-Oleum primer paint and paint those. It's very Lambertian. So that was pretty, straightforward to make. Another nice build by Jay Bush there. We're not always estimating completely the right lighting. Something that was really worrisome about that is that sometimes when you're walking out of a building, you now see a view in your cell phone that's like the outdoors, but the spheres haven't yet gone outdoors completely yet, or they're still in the shadow of the building. So you'll get completely contradictory information as to what the lighting for that scene should be right before the spheres go into the sunlight and then right after they go into the sunlight.
Right.
And you know what? We just threw it into the network, and I don't know what the network does, but it comes up with pretty plausible stuff, right? I mean, we're not competing with anything particularly good in terms of what the lighting estimation algorithms were before. And to some sense, to a person looking at that image, there isn't much information in the image that the person has access to either to see whether it's correct or not. So, that maybe we're doing okay for that. In the case of faces, the biggest concern that we had is that any naive algorithm to estimate lighting off of a face might be proportional. It might estimate an amount of light that's proportional to the reflectivity of the skin. And you might estimate more light in the scene if there's a lighter skin tone and less light in the scene if there's a darker skin tone. And that would not be good in the fairness. It wouldn't be the right answer for it. We trained, we specifically tried to bring people in with a healthy range of skin tones in the light stage. We trained on that. There is some information available, about skin tone in the data, like diffuse specular ratios kind of tagged out a little bit. But we just let the network try to figure it out, and it did great. We saw in those examples, we were estimating lighting off of a person with one skin tone, reproducing it on a person on another skin tone, and then actually reproduced how they would look in the light that was consistent the way they'd look under the ground truth illumination. So we're very happy that machine learning did the job.
Excellent. Thank you. And we have, I guess, one last question from the live chat. Sung Hwan Bak says, thanks for the amazing talk. Could you please talk about your vision on how the future of the light stage would look in terms of its capability?
Oh, awesome. Wow. Well, yeah, I mean, I've been involved in building light stages for 20 years now. And, I mean, maybe I should figure out something else to do. But, the application in the area of virtual production is very interesting because essentially what folks are doing when they're building these LED panels, actors, they're building the form of a light stage. It's higher resolution. The spectral rendition isn't state of the art because these LED panels are designed to be displays, not light sources, not illuminance, and so they don't care about the color rendition. They can produce any color you can see, but they can't produce the color rendition effects of any spectrum of light that would probably light somebody. In particular, they're missing a gap of spectrum, like between the red LED and the green LED. It doesn't produce any legitimately yellow light in between. And that area of the spectrum is where human skin starts to absorb the shorter wavelengths through the hemoglobin. And that's like the one piece of high frequency contact between the reflecting spectrum. And they mismatch in a somewhat biased way. It tends to make people look a bit too color saturated and a bit too magenta. So that's kind of a major minus when you're surrounded by these beautiful LEDs and everybody looks a little too pink. That's actually something that happens. You have to do some color correction. So that would be nice if we could address that somehow. Probably better LEDs in there. Another huge problem is dynamic range, because you might notice that in some of these shows, like in The Mandalorian, they're often trying to set up the scene so the actors just happen to be sitting in the shadow of a rock or a shadow of their spaceship, or it's at twilight. And whenever they need to show people in full sunlight, they tend to actually shoot that on the back lot and not on the LED stage, because the dynamic range of LEDs, to show that little disk of the sun on the LEDs, they'd have to go well over 1,000 times brighter than actually can. So thinking about how to address that problem would be a good person as well. So I think in that context of these, tons of these stages are getting built. It would be great if they covered as many of the production cases as people are really wanting to. So that's something to think about.
Gotcha. Okay, so now with these LEDs that you can stand on and these really nice LED panels that you're going to make, is the future of acting just you go into a little light closet and you talk to yourself?
It could be that, actually. It'll be a little bit more like theater. It sounds maybe attractive, like go on location to Tahiti or Moscow or something and shoot your scenes there. But you're away from your family, you've got jet lag, there's tons of production issues, you're stuck in a hotel. A lot of folks, who are like working actors and directors love the idea that they can, go to a set that's, in the same place every day. They can work from 9 a.m. to 5 p.m. or 6 p.m. or whatever, and kind of turn acting into more of a normal job instead of like a complete life derailment. And the promise of these stages where you snap your fingers and all of a sudden you're in any location that you need to be in is very attractive for that. So I think that that's going to be pushing the adoption as well.
Wow, well, thank you so much, Paul, for sharing and for closing us out. And thank you, everyone, for attending, watching our other speakers, our poster presenters. Looking forward to seeing you guys hopefully in person soon. And we'll just close out with a few comments from our co-organizers. Thanks so much.
Thank you so much for joining CVPR 2021's Computational Cameras and Displays Workshop. This has been an amazing day of truly fantastic talks, and I can't wait to learn more about some of the papers that were shown in the spotlights. Thank you to all who participated throughout the day and asked questions. It is participation like this that brings us closer together and feel more like a community when we are far apart physically.
The next CCD workshop will be held at CVPR 2022 in New Orleans, Louisiana. We look forward to seeing you all there, hopefully in person.